Okay, let me introduce a very warm welcome to you to this already 15th workshop on virtualization, high performance cloud computing, VHPC 20. I will not extend on the move to online, which we're actually quite happy with it at this stage. Let's jump right into it. So first, I'll give you a very brief overview of the program, and then we have our first speaker, Danny Welsh from Red Hat, to give us the first keynote. You should be seeing the program in a separate window. If not, you can go to vhpc.org. Whereby I'm gonna highlight a couple of things. So first of all, of course, we have our keynote introduction to Podman. Podman as a call it a Docker replacement. So something which we've dreamed of in HPC for quite some time. A stable non-root daemon optional container platform. This is what Daniel Welsh is going to introduce to us. This is going to be followed by a talk by Google on autoscaler they have in production, in very wide production, called Autopilot. Major thing. So Christoph will give us an overview on that. We'll go on with a quite interesting paper by Holger Gandikov and others who have used Podman for HPC and for a CAE application. Very interested. So you can also make use of the Q&A features in the tool. Plus, we'll attempt to hand the mic around so that you can ask live questions on their experiences with Podman there. So this is something very hands-on. Going very brief from then on, we have more on, we have Kubernetes quite a bit. So we have got Kubernetes in HPC workloads, then a little bit of Kubernetes in a shared in a setting where you look at the interference from one pod to another. Very interesting paper. Then we look at in form of a lightning talk the usage of Kubernetes in a setting presented by Jamie. More Kubernetes by David in a pipeline at the EBI. And then we spread out a little bit thematically. So we have in-depth heterogeneous hardware with real-time aspects by Tommaso, which is an invited talk. More invited talk from Dimitris on the various options in HPC virtualization as such. Then we go into a thematic cluster on unikernels. So unikernels with Unicraft, which is a construction kit by Simon from INEC Europe. Rusty Hermit by Stefan Lankes. Needless to say, it's written in Rust. Another unikernel presentation, a paper. Another paper on HPC and cloud technologies by Yanis. We have an SRIOV paper, then in networking from Andreas et al. From Tübingen. We have from IBM Watson, Sitarami who talks about AI accelerators, cloud-based ones that is. And then as a last talk, we have a lightning talk on GPU scaling as a service, followed by a discussion round. And I hope many of you will be participating in this discussion round. which is quite late in a Central European time. But if you're located in westwards, it's much easier for you. Still, we will hold a hopefully lively discussion round at this hour, which is then bringing us to a conclusion. So we have quite a long program ahead of us. That being said, let me introduce. We have got now from Red Hat joining us. Danny Walsh, and let me just give you a brief bio of him. Danny has worked in the computer security fields for over 30 years. He's a senior distinguished engineer. This is quite a senior title at Red Hat. He joined Red Hat in August 2001. That's a long time ago. Dan leads the Red Hat container engineering team since August 2013, but has been working on container technology for several years. Dan helped develop SVirt, secure virtualization, as well as the SE Linux sandbox back in RHEL 6 as an early desktop container tool. Previously, Dan worked on Netcat, BindView, on vulnerability assessment products at DEC, and working on the Athena project, Alta Vista's firewall tunnel products. Dan has a BA in math from the College of the Holy Cross and an MS in computer science from WPI. That being said, we pass the token now to Dan. And as this is the first token passing, we need a little bit of a delay in there. So 1 second. So then you're good to go.
Can you see my screen? Can you see the slide?
Yes.
Okay. So thanks for introducing me, and thanks for listening to the talk. I'm going to be introducing Podman, and we're going to talk a little bit about HPC stuff that we've added to Podman. But usually when I talk about this Podman, most people come in with a knowledge of Docker. So I'm going to go through a quick presentation that we have on how do you replace Docker with Podman. And the basic idea is you do a DNF install of Podman or a yum install of Podman, and then you do an alias of Docker equals Podman. And at that point, we ask for questions. So it's kind of a joke, but not really. So this is a tweet from basically almost 2 years ago now, or 2 years ago now. I completely forgot that almost 2 months ago, I set up an alias of Docker equals Podman, and it has been a dream. And if you go down to the bottom, someone asked him, what reminded you that you were using Podman instead of Docker? And he said, I did Docker help. And of course, Podman help came up. So let's a little history of where Podman came from. Basically, if you sit down and look at what it means to run a container, the first thing you need to do is identify what a container is. And what usually when people say they want to run a container, they'll say specific things like I want to run Nginx, or I want to run Fedora or Alpine. And really what they're referring to there is what is called a container image. Some people sometimes still call it a Docker image, but basically Docker invented this concept of where you create a directory on disk, you put some content into the directory. The directory tends to look like a root of a Linux operating system, so we call it a root FS. But you'll have things like /user and /var and /root and /etc inside of this directory. Then they tar it up and they create a JSON file associated with that tarball that basically allows the developer of the application to define things like, what is the executable to execute? What is the environmental variables? That whole thing is called an OCI image or a Docker image. And CoreOS led to a standards body being developed called the OCI Open Container Initiative, and that defined a standard for that. So now if you go out to any container registry like Docker.io or Quay.io or Artifactory, what are sitting there are basically OCI images. And so now we have a standard of what it means to be an OCI image. And I often tell people that OCI, Open Container Initiative, is not the same thing as carrying around open containers of alcohol. And I was actually asked one time when I was wearing this jacket if that's what it meant. And no, it does not. So the next thing we need to do after we want to run a container, we'd find what a container is. We need to pull the container to the host. So several years ago, we started working on open up a pull request with upstream Docker to allow us to basically, instead of pulling down the entire image, that entire tarball, all we wanted to do is get down the JSON file, and the JSON, just to look at what the JSON file. The problem with the images is the images can grow to massive size, and if you guys work in HPC, I've heard that some images you guys use are many hundreds of thousands of megabytes in size, but you might want to just pull down the JSON file and sort of examine it and figure out if you really want to use this image. So we opened up a pull request for Docker to do a Docker pull, Docker inspect -- remote, and they rejected it at the time, saying that just complicated the CLI too much. Command line interface too much. So, but they said, all these are is JSON files sitting, basically a container registry is nothing more than a website. And you could just pull down the JSON using standard HTTP type calls. So they said, build your own tool. So we did, called Scopio. And could everybody mute their lines? Hearing feedback. So the basic idea, we built Scopio, and Scopio was a tool originally just to be able to inspect remote images. But over time, the developers, basically built up the tool to be able to pull images and push images and basically implement everything you'd want to do to move in images back and forth between a host and a remote machine. But it was later decided that we'd split that tool into both the library and the tool, and we decided to create a library so other tools could pull and push images, and that library is called GitHub Containers Image. So now I can define what an image is. I'm able to pull it to a system. The next thing I need to do is be able to basically take that image and put it onto disk, or to explode it onto disk. Well, images, I've sort of simplified a little bit, and that the standard image is one tarball, but actually images tend to be the concept of layers. So you could have, I usually think of like a wedding cake, where you'd have a sort of a base image, and then you have the differences on top of that. So imagine you had a UBI image from Red Hat UBI 8, and you wanted to run Apache on top of that. So you might have another layer that has Apache, and then you might want to run JBoss on top of that. That'd be another layer. And then finally, you'd have your application. And each one of these layers would be differences from the prior layer. So when I pull down an image, I might be pulling down multiple layers. Those layers have to be stored onto what's called copy on write file systems. And a bunch of these copy on write file systems were originally written by Red Hat and given to the Docker upstream Docker project. And we decided to pull those out and make it into its own library, and that's called GitHub Container Storage. So now we define the image, we can pull the image to local machine, we can store it on disk. The next thing we need to do is be able to run the container. So run a container based on that image. And turns out that there's a standards body, the standards body OCI also standardized on what it means to run a container. So when I want to run a container, I need to take input from the user, I need to take input from the container engine, and input from the developer, that JSON file that defined the image. And then we combine all three inputs together, and we create yet another JSON file on disk. That JSON file describes things like, what are the capabilities, what is the security context, what are the namespaces when you use, different things like that are all defined in this big JSON file. And that JSON file, what the fields are in that JSON file are specified in the OCI runtime specification. And what the goal there was to have executables which would read that JSON file, basically figure out how the user wanted to run a container, and then it's going to instrument the Linux kernel to run the container. So the default tool for implementing the OCI runtime spec was called runc, and so that was also put into the OCI. So basically we can define an image, pull an image, store it on disk, and instrument the Linux kernel and basically start the container. So runc is the default implementation that almost everybody that runs containers in the world is now using for launching containers. A couple other things we needed to be able to run containers in our environment is we needed a mechanism for basically setting up networks, so different types of virtual private networks in the environment. And CoreOS, again, created a standard called the CNI, or the Container Networking Interface. And this is a thing that's used by Kubernetes and other tools for setting up different types of VPNs. It allows basically people to plug in different types of VPNs and be able to use with containers. So we take advantage of that tool as well. Finally, there's since we're not going to have a daemon in our tool, we needed something that would sit out there and monitor the containers. So we built a small C program called Conmon, Container Monitor. And what it does is basically sits out and watches the container. When you have an OCI runtime, the OCI runtime sets up the container, basically creates the first process and then exits out. So you really need sort of a program that just watches the container. If the container exits for any reason and wants to catch its exit code and write that out. It also holds open things like standard out and standard error. So that if you want to reconnect to a container, there's a mechanism for reconnecting, and the tool we use for that is called Conmon. So if you notice, when we talk about our containers, all the things I said you need to do to run a container, the one thing you don't need is a big fat container daemon. You don't need a root running daemon to be able to run these containers, right? Containers are nothing more than regular Linux processes on a Linux operating system. So what we wanted to do is avoid and allow us to experiment with more ways of running containers than just using the Docker daemon. So out of these tools, using those libraries and commands I talked about earlier, we wanted to take a look at what Docker was and basically break it up into individual projects or products to be able to run containers in different ways. So we really looked at Docker. The way I looked at Docker was sort of performing 4 different tasks. One of those is what most people do as developers that are playing, sort of developing containers, playing with containers, running a container on a local host. And the tool to handle that is called Podman, and I'll get into that a little bit in the rest of this talk. But also we mentioned earlier Scopio. So a lot of things that people do with containers is they move them from one registry to another. So in a Docker case, you do a Docker pull and a Docker push, but by doing that, you're actually interacting with a root running daemon. You're installing stuff on a local machine. And by us moving to Scopio, you can do a non-root process and just move from, say, an external registry to an internal registry. Another thing that a lot of people do with Docker is they do Docker builds, right? They're creating the OCI images. So we created a different tool called Builder, and our goal with Builder was not only to support Dockerfile, but also to allow people to experiment with new ways of building containers. So Builder is a tool that we use to not, as I said, it supports Dockerfile, but also you can just create a directory on disk and just start putting content into the directory, and it'll Builder will basically package that up, push it to a container registry, and then tools like Podman, Docker, and Scopio can all use that image just as if it was built from a Docker build environment. Podman build, which is the equivalent to Docker build, uses Builder code to actually do the builds. Lastly, the last tool I'm going to talk about is a tool we have, a small daemon we do have, which is called Cryo. And Cryo is a daemon that we call for running containers in production. So we believe that you don't want to be playing with containers and you don't want to be building containers when you're running them in production. So the goal here is to be able to build and use containers with a lot more security. So when we go to a Kubernetes workloads, we run with Cryo. But the bottom line in all these tools is they all share the same underlying libraries. They share the same tooling underneath. So they all can work together to be able to get the purpose done, but also we can run them separately and then use and investigate new ways of doing things more securely. So again, going back to Podman, Podman is a tool for managing pods and containers based on the Docker CLI. One of the other people have built container engines over the years to compete against Docker, and but they did not match the Docker CLI. And in my opinion, when we first started building this tool, we decided that people are going to say, how do I do this with a container? And they're going to get a Docker command line. So we didn't want to have, oh, you do it this way in Docker and you do it this way in Podman. So when we started out, we basically wanted to copy the entire Docker CLI. So the command the commands would be exactly the same. And basically we get lots and lots of bugs when we vary from this. So if someone comes, basically if you have your script written for using the Docker CLI and you just change all the Dockers to Podman, or do the alias of Docker equals Podman, it should be able to run perfectly well with Podman. So I think doing a demonstration is probably much better use case of time than actually just talking on it all the time. So here I am. Oop, if I could remember my password. Okay, so I'm going to do a quick demonstration on Podman and give you some of the key features of it. Right now I'm just doing Podman version, very similar to Docker version. We just released this week what's called version 2.0, and it looks very much like what the output you would get from doing the Docker version. Now that's Podman info, which is similar to Docker info. It shows you the some information, but there's a couple of interesting differences between Docker and Podman here, in that Docker supports a single registry. So one of the goals of Docker was to lock people into just using their registry for what they called short names expansion, but it really drew everybody to just to go to Docker IO. And what we did when we first started experimenting and working with containers, we wanted to make sure that any registry could be specified to be used. So we actually have a search list of registries, so we can move from one registry to another and be able to expand short names. Down here, you'll see that we're using storage drivers overlay, which is basically the same type of driver, but basically you can start to see some differences between what Docker does and Podman does. And remember, I talked earlier about Builder being embedded inside of Podman. Here you see the Builder version in it. So now what I'm going to do is, so one of the cool things that we're able to do, because we broke apart the products, is to start to combine them in different and interesting ways. So here I'm about to demonstrate, I'm going to run a Podman container, but I'm going to actually run Builder inside of it. So this is doing a build inside of a container. And this is doing it a lot more securely. And usually when people try to build containers inside of other containers, what they're doing is they're leaking in the Docker socket. And I wrote a paper several years ago saying that the most dangerous thing you can do in Linux is give someone access to the Docker socket. It's worse than giving out the root password or giving sudo without password. So there I just ran a build of a container inside of a container. And if you saw at the beginning, I basically pulled down an Alpine image here, and I ended up building an image based on top of that, and that was all within a lockdown container. So now I'm just going to remove it, clean it up, but basically that's the end of that first part of the demo. But the sad part of that demo is I did everything with sudo, right? So I was running things as root with Podman. Podman can duplicate pretty much everything Docker does as root on the system. But the really cool thing about when we broke apart these tools is we figured out ways that we could actually do things without being root. So to not be on the roots on the system. So now I'm not running sudo, and what I'm going to be doing is I'm actually just running Podman in my home directory, and that's going out right now, and it's going to pull down an Alpine image onto the machine, and now I'm actually going to launch a container. So I just launched an Alpine container and did ls and /. So I was able to run a container in my home directory with no root privileges. So I'm not doing any sudo magic or anything like that. And if you look, you'll see all sorts of different containers that I've run over the weeks in my home directory. You also see these are all the images that I have in my home directory. And if I go to sudo podman images, you'll actually see a different list. So the idea here is that in my home directory, I have my images, and if I would ran as root, I would have a different set of images. Or if I had multiple users on the system, each one of them would have a set of images in their home directory. So now I'm going to explain how this works, what the magic is. So in modern Linux there's a thing called user namespace. And what user namespace does is allows us to associate multiple UIDs to a single user. So my UID on the system is 3267, and inside of the Etsy sub UID, the user ad program has allocated 65,000 additional UIDs to my account. So here you see D Walsh basically has starting at 100,000 and then gets the next 65,000 UIDs associated with that. So when I run a container, I just ran, now again, I'm doing podman unshare, and it looks like I just became root on the system, but actually what happened is I entered a user namespace on the system, and what I can do, so I am not real root, I'm still running as my UID on the system. But if I look at proc self UID map, you'll see that this is the user namespace that I'm in. So as I said, my UID is 3267, and we've done with the kernel is we told the kernel that to map UID 0 to UID 3267 for a range of 1 UID, and then starting at UID 1, I'm mapping 100,000 to that. So if I basically sued to UID 1, the process on the current operating system would actually be UID 100,000. If you looked at the contents of my home directory now, you would see that it's reporting that all the files in my home directory are now owned by root. And what's happening there is that's user namespace magic going on. So let me just, so if I went outside of the user namespace and looked at that, you see everything is actually owned by D Walsh, the exact same files. So this is sort of the magic of user namespace, and that's really what we're taking advantage of when we're doing these containers. So let's take a quick look at some additional features of user namespace. So one of the really cool things about user namespace is that I could run multiple containers, each one in a different user namespace. So here I'm going to execute a container, and that container is just running sleep, but using a special podman top command, I'm able to see that inside of the container it thinks it's root, but outside of the container it sees itself as UID 100,000. Now I'm going to run it, and you can actually see the process running on the system is 100,000. Now if I do a second container, the second container I'm running with a different user namespace, and it's running as UID 200,000 inside of the container. And so if here I'm running, so I've run 2 sleep programs, one in one user namespace, and inside that user namespace it thinks it's root. Outside the user namespace it sees itself as 200,000. If I look for the sleep program, I see it as 200,000. So if those containers broke out of containment, they'd be able to attack it. They might be able to attack each other, but they'd be treated as different UIDs. So if you can follow at HPC, this is sort of the key thing about HPC was always you guys have been relying on UID separation. So we can get the same type of separation using user namespace, but still allow you to have sort of root inside of the container. Another key concept that Podman does that's different than Docker is that Podman supports a fork and exec model. So the way I demonstrate that is there's a special field on Linux systems called the login UID. When you log into a system via SSH or a graphical login, what happens is the login program tells the kernel that this is going to be Dan Walsh logging in or 3267. That field gets set in the kernel, and then every process the kernel, every process that's ever executed by the login process always records that it's 3267. So in the next command, you see that I'm running sudo, so I'm becoming root. Then I'm executing podman, and then podman is executing a container, but all the way down into the container, you see that I am still running as, the process is still running as 3267. Now, if I run the same command with Docker, you'll see that the UID came up and said that it is running as 42 billion something. Well, that translates as -1 inside of the range of UIDs. And what's happening there is Docker did not get logged into, right? The Docker is a client server operation. So when you run a client server operation, Docker client is talking to the daemon. The daemon starts by the init system, so it's running as -1. So why is that important? If I go in, I'm going to use the auditing subsystem now, and I told it to put a watch on Etsy Shadow. And what happens when I put a watch on SC Shadow, I'm actually simulating in this line here a breakout of a container. So I ran a privileged container with slash mounted as slash host in the container, and I actually modified SC Shadow. So if we go into the auditing subsystem now, it's reporting, the auditing subsystem reports that Dan Walsh here modified Etsy Shadow. If I ran a container with Docker and I was able to break out of the container and modify Etsy Shadow, then the auditing log would basically say that the person modifying Etsy Shadow was never set, so it doesn't know who modified Etsy Shadow. And this is why access to the Docker daemon is the most dangerous thing you can do on a system, because what I can also do is I can remove all the logs and remove the fact that I broke in using Docker into the system to cause havoc. Couple of last features of Podman that are interesting is Podman actually has all sorts of cool features in Podman Top to reveal what's going on inside the containers. So I can actually look at, what is the PID inside of the container versus what is the PID on the host. I can actually look to see what the SE Linux labels are running inside of a container. I can actually look to see whether seccomp filtering is turned on. And lastly, I can look at what capabilities are running on processes inside of the container. So these are all revealing sort of really cool security features of the operating system. So everything I've shown up till now has been doing pods. It's been doing containers, but Podman also handles pods. And a pod is a Kubernetes concept where you basically have one or more containers running in the same pod. So what I'm doing here is I created a pod, and then I added 2 containers to it. And what this allows you to do, pods allow us to manage multiple containers at the same time. And so what I just did is I did a Podman pod start of the container of the pod I created, and you see both containers have started. And now I'm going to actually stop the pods basically, and that kills the containers. So it allows you to sort of manage the life cycle of a group of containers in the same type of environment. And pods share things like C groups, control groups, and other concepts. So if we go back to the presentation here, so what we did when RHEL 8, which came out 1 year ago, we decided to drop Docker support altogether from RHEL 8. And as of RHEL 8, Docker is not included in RHEL 8, but for working with containers, you need to use Podman, Builder, Scopio, or Run C if you want to get support from Red Hat. But these tools are fully supported inside of all versions of RHEL going forward. There are versions available in RHEL 7 as well. So this is an HPC talk. So once people started to, probably the most popular feature of Podman is its ability to run as non-root. And suddenly we started getting contacted by people at the national labs in the United States and different places, and they were interested in, using Podman in HPC environments. And basically looking at it as a potential replacement for Singularity. So we started working with them, and the first request we got was to basically, a lot of people in HPC environments didn't like the idea of the Etsy sub-UID, where you had multiple UIDs associated with a container. They basically wanted to follow what Singularity was doing, which was run all processes as a standard user inside of the container. So we'll only have one UID for all the processes inside of your container. And the problem we had with that is that a lot of OCI, if you wanted to use OCI images, so these images out at the container registries all have usually have more than one UIDs inside of them. So if you pull down an image with more than one UID, it would blow up when you pulled it down, because your user namespace would only have one UID map to it, and you wouldn't be allowed to write those files. So the community members wanted us to add a feature to container storage to basically say ignore chown errors. So when an image gets pulled down and stored in storage, it actually gets written down as the root of the user namespace that you're running in, or if you're not running a user namespace, it gets written as root. And then after the fact, after the tar balls get extracted, part of the tar process is to chown the files to the correct UID. inside of the user namespace. Well, if those chown commands fail, then we blow up the image store. Well, if you set an ignore chown errors flag inside of your storage.conf file, it will basically allow the, you'll just leave the UID as the original UID that pulled it down. So that's what this this change to Podman was about. Another thing that we found that users of Podman found is they were able to use Podman, but the so Podman has sort of its hard-coded defaults inside of it. These are things like what namespaces it's going to use, what volumes it's going to use, what security labels, what C groups, and a lot of people wanted to change those. And so the normal way to change those was on the command line, and so those command lines could grow very, very large. So there's lots and lots of options available to Podman. But it became fairly cumbersome in an HPC environment to basically add those. So one of the features we wanted to add for basically running Podman was to move its configuration, instead of like Docker where the configuration is pretty much hard coded into the executable. We wanted to create a configuration file that could be that users could change the default, users, distributors, or whatever could change the default configuration. So we created in Podman 2.0, we have containers.conf, which is basically a mechanism for you to modify the default way that your container is going to run on your system. HPC environments are encouraged to customize service to run Podman commands with minimal command line differences. So we have 3 different supports for containers.conf. We have at the distribution level, which is usually stored in user share containers, containers.conf, and then we have administrators. If you want to change in an administrator, you can just make small changes in etc containers.conf, and then if users want to change in their home directory, they can change it, put a containers.conf, and these containers.conf are mergeable, so that you can make just small changes in one and still use the greater distributions. So what I'm going to do now is I'm going to switch to a different window, which I call HPC, and let's do a quick demo here. So what I'm doing right now is I'm going to pull down the Fedora minimal image into my home directory, just like I did before. Oh, that was supposed to blow up and it didn't. Great. Anyways, not just sure why it didn't, but let's pretend it blew up, changing changing a UID. So now inside of this user environment, I basically set it up so that it only has one UID mapped to the environment. And so this, even though I am again inside of user namespace and the system thinks I'm root inside of it, I'm able to do it. So what I would do to create the, to basically tell it to ignore chown, so that I could just go into storage.conf in my home directory and just uncomment that line, and that would tell, that would allow me to run containers without being root, even though I don't have more than one UID. Even if the image had multiple UIDs inside of it, I would be able to modify the default way that I ran containers to be able to pull it like HPC want. Some people in HPCs work. So another interesting thing where containers.conf comes in is here I am running a container, and if you see, I'm inside of the PID namespace. So that means that I don't see the processes on Linux system. So I might, I'm only going to see one process. But what I could do is go into containers.conf and basically change PID namespace here. And what I'm doing here is this is going to change the default PID namespace to say use the host PID namespace. So basically don't create a PID namespace inside of my container. And I could run the same container, and now you see hundreds of all the processes running on my Linux system being listed. So just by changing the containers.conf, I'm able to make drastic changes on my system And I could basically run any container I run from that point on would be sharing the PID namespace. Sharing the host PID namespace. If I wanted to, run a container as private, now I could do it at the command line and specify it, but the defaults would be changed to that. So other features of Podman that are really interesting, in my opinion, is that Podman has proper integration with systemd, and that we can fully integrate with the way systemd is intended. This is something that Docker could never do. So you can run systemd inside of containers. We fully support SD notify. We support socket activation. Since Podman is a fork exec model, it works more like how normal processes on a Linux system work. So it's easily trackable. If I put Podman inside of a unit systemd unit file, the container actually runs inside of that unit file as opposed to running as a child of the Docker daemon unit file. We also build tooling into Podman to be able to generate unit files directly from containers. So once you have containers working the way you want, we will generate sort of best practices for running Podman inside of containers. Another thing we wanted to do with Podman is to sort of bridge the gap to Kubernetes. A lot of people understand how to run containers underneath, sort of in the way that Docker described, but as soon as they make the leap, they get 2 or 3 containers running well on their system, but they want to move towards running containers underneath something like an orchestrated environment like Kubernetes, and suddenly they're editing YAML files, and how do I translate from what I did with the command line to something that works with Kubernetes. And so we basically have a tool called Podman Generate Kube, which will take your running environment, your running containers or pods, and actually will generate the Kubernetes YAML files for you. So it converts Kubernetes YAML file ready to be used with something like OpenShift to Kubernetes. We also go the other way in that we can take, say you're running containers or pods inside of Kubernetes and they're not working right, and you just want to basically see how they run locally. You can actually take the Kubernetes YAML and play it through Podman, and Podman will translate Kubernetes YAML back into sort of traditional containers. As of 2.0, which, as I said, was just released, we added REST API support. So this basically allows you to connect to we don't have a daemon, but we can do socket activated Podman containers. So you can connect to a Podman socket or even to the Docker socket with Podman listening, and actually kick off containers based on based on the Docker API. So this is our effort to, one of the things we did originally was Podman was supposed to just replace the Docker CLI, but a lot of people have things like Docker PY and Docker Compose that are all talking directly to the Docker socket and different tools. And so now we have Podman able to listen for those APIs and able to generate containers based on them. We also have Python, Go. Podman's all written in Go, but we wanted to have other languages be able to support. So using the API service, now you have Python binding, so you can actually launch containers using Python. We also have remote support for Podman, again, using the API. So we have Mac support. So you can run a Podman command on a Mac or a Windows box and have it talk to a Linux system, either a VM or something out in the cloud or on your local network, and actually launch containers on behalf of users running on Mac and Windows systems. Windows also has support for WSL2, which is really embedded Linux virtual machine on top of Windows. We also support Cockpit, which is a tool that uses Java and JavaScript for managing Linux systems. And so Cockpit is using JavaScript to talk to our API to launch different types of containers on the system. Docker Compose, as I mentioned, can use API v2, but Docker Compose is tied just to the way Docker works. So the community, upstream community, has created a Podman Compose to be able to support things like pods and different advanced features of Podman that don't exist inside of Docker. So there is a full effort, not but led by Red Hat, but led by community to build Podman Compose. So things that we don't do with Podman are things around auto starting because we rely on just system D to automatically start when a machine reboots. We don't do Swarm, so we don't support Docker Swarm because we think Kubernetes is basically what we want, and we want to drive people towards Kubernetes. Right now, we don't support Docker Notary. We have a thing called Simple Signing, which is a similar tool for signing images and setting up trust relationships. We're not against Notary, but we don't plan on using it inside of our products. So if an upstream community wanted to add Notary, we would take it. And we have limited Docker volume support at this point. Most of the volumes that you probably usually use for inside of Docker work, but advanced Docker volume features like people building volume daemons, we don't currently have support for. There is some advanced features that we continue to work on, and I have written a coloring book on this. But at this point, I would like to, I guess, open up for a few questions. We have 10 minutes left in the session. Anybody have any questions?
We currently have 2 questions in the Q&A queue. I can read it out, or let me see. We have a question from Shuji Takahashi. The question is, when we use Podman on HPC, can we use InfiniBand device on host and communicate with another Podman container on other nodes, even if it's rootless? Question mark.
So, yeah, basically Podman will support any devices on the system. The device needs to be added to the container. Some rootless environment, when we're talking about Podman, we usually have to talk about rootless or rootful. There are still some things in rootless environments that will not work without setting up proper permissions in the Linux kernel. So Podman is not like some way to break standard protections, so that if the devices are able to be used by a non-root user, then Podman can use them, and on both the client and the server operation. So yes.
Okay. There's a second question from him, which is Docker itself has a rootless mode, bracket maybe experimental, bracket closed. What's the difference of rootless Docker against Podman rootless? Question mark.
Well, I actually think one of my big issues with Docker all along was the daemon, and Docker doesn't run one daemon now; it runs 2 daemons. So if you, first of all, Docker upstream doesn't support it, but basically, if you wanted to run a container, if you want to run a single container like I just showed inside of my home directory, I can do it with a single command with Podman. In order to set up Docker to run rootless, I have to set up container D running in my home directory. Then I have to set up the Docker daemon running in my home directory, and then I can finally execute a container. And the container, again, is not, it's not really a child, of the single process. So you're adding a lot of complexity when you go with Docker daemon versus Podman for running containers. So, my opinion, almost no one in the world uses the Docker daemon for running rootless. It's they actually built the tooling that's to do that is all built on top of some of the tools that we've built to fuse overlay file system and Slurp4 and NS. But basically, I think it's kind of ridiculous to have to run 2 daemons in order to run a single container in your home directory. But your mileage may vary.
Okay. Let me now do something which... Can you still talk, Danby?
Yes.
Okay, very good, because I reclaimed the host. So the next question is from Theofilos Manitares. HPC systems use NFS-type file systems which don't work with user namespaces. Is there a solution to that? Very good question, yeah?
Yeah, so to give you an idea, a lot of, well, first of all, I'm not sure that's true, okay? If what doesn't work when you have an NFS home directory is having multiple UIDs inside of a container. So if you imagine you're sitting in a container and you're doing that pull command that I was showing earlier, and you have, I pulled down a image which has 2 UIDs inside of it. What happens in the user namespace is the root of the user namespace actually chones the file to a different UID. NFS enforces that procedure on the server side, so that will be blocked by an NFS server. If you're running as a single UID inside of your user namespace, so that we're doing the ignore chown errors, then it should work on top of NFS share. Now, that being said, I've never tried it, but I believe that that should not be a problem in a NFS type environment. Another option we could experiment with would be if you have any local storage on the machine, you could store your images on the local storage, and then just use NFS for your volumes and stuff like that. Another option might be to have a memory resident file system for your images, or to have a blocks and we could create a device on top of NFS and then mount that, basically a loopback device on top of NFS and use that to do it. But I believe that as long as if you're going to run with NFS and we go with the ignore chown errors, then Podman should work on top of it.
Okay. Any more questions? We've got only 3 minutes left. Any more questions? Maybe let me put additional emphasis on this NFS question before. So we really, as a collective, we really need performant NFS. Might it be bridged? Might it be even the device path for whatever works? It's really really essential, and there's no way about it. Yep. Any more questions?
So one of the questions was many HPC systems rely on older Linux kernels, less than 4.18. So Fuse overlay is not an option. So we do support the VFS driver, but I'm not sure which version. If you're using RHEL or CentOS for your RHEL and CentOS 7.8 now supports Fuse overlay. So I'm not sure. We backported the support for Fuse overlay into those versions. So if your systems can run on top of a RHEL 7.8 system, then you should have support for Fuse overlay. And you can use a VFS driver. VFS is a very disk sensitive driver, but you could use the VFS driver as well.
Okay.
Another question was around, can you talk about Podman and MPI jobs? I really can't, but I believe there's a talk coming up later and this is going to talk about MPI. I know that people have run Podman with MPI jobs, but you're going to quickly realize I don't know that much about HPC to really answer that question well.
Okay, we basically are out of time. If you want to add anything on Kubernetes in the last minute, or
yeah, I mean, as I said, our effort, Podman wasn't originally developed for HPC environments, but it turned out that we seem to have a fairly good match for it, and we enjoy working with HPC. So these questions that come up and different ways people want to change the way Podman works, we'd love to talk to people, and even better, we'd love to get pull requests to modify it to be able to work better in that environments. As far as Kubernetes Kubernetes, what I didn't mention earlier about Podman also is what really makes Podman work in my opinion, for HPC is that it allows you guys to bridge the gap. So most of the world is moved to OCI and container image and Kubernetes, and this allows you to, if you start using Podman and tools, it's going to make your the ability to get to Kubernetes that much easier, because you're already going to be starting to use images in the way that most people in the world now are using containers, as opposed to using singularity method for doing it. So I guess that would be my final sales pitch on using Podman for your work groups, workloads.
Well, indeed, we are very much looking forward to this rootless, highly stable, I could add more attributes to it, facility going forward. So thank you, Daniel, for your presentation. Are you going to stick around a little bit for questions from attendees?
Yeah, I can. I think you want us back at my lunchtime here, so I can come back for that.
Okay. So copy if anybody has questions. So thank you again. You should be seeing the program on a screen share. So for those people who have just joined, we are just at the second start of the second talk now, which will be by Christoph from Google. We just had Daniel Walsh from Red Hat, and afterwards we'll have more on Podman, hands-on aspects from folks who have put it onto CAA HPC use, which will be hopefully highly interactive with what worked for you, what didn't work, this kind of questions. So we invite lots of interactivity then. Going forward, we have lots of Kubernetes for you, Kubernetes, and then a cross-section of HPC from networking to unikernels to more on cloud/cloud provider related topics. So at this time, Christoph, you should be able to speak.
Yeah, can you hear me?
Yes, we can indeed.
Excellent.
Let's see that you can share your screen. So I will now stop my share.
And I'll start my share. Okay, can you see my screen now?
Yes, indeed, we can.
Okay, great. So
well, the floor is yours, the electronic one.
Thanks, and thanks for inviting me here. So my name is Krzysztof Rządca. I work currently as a visiting researcher at Google Warsaw, and I'm also an associate professor of computer science at University of Warsaw, Poland. I'm going to present Autopilot, a tool we developed at Google to automatically scale the workloads in Google internal cloud. So Autopilot's core focus in Google Cloud is on serving jobs. We call them high availability, latency sensitive jobs. Picture serving YouTube or Gmail to millions of end users. So you need to have high availability because if the job fails, end users very quickly see that something is wrong, and you need to be very sensitive to latency because user experience quickly degrades when the latency is increased beyond, let's say, 100 to 100 milliseconds. But the core problem, so this is like a different job category from what's typically done at HPC. But I think that the core problem in how to set limits for containers at runtime is generic, and I think it would be interesting also for this HPC audience. And this talk is based on a paper we had this year's Eurosys. So I acknowledge the help of my Google colleagues, including my co-authors here, but also many people who worked at this to implement this tool. So in our internal cloud, a job can serve YouTube or Gmail to millions of end users, but it also can be a batch computation, like recalculating database indices. No matter what is the type of the job, to launch it, we pack it in a container and then ship it to 1 or 1,000 production machines where it is executed. And the key feature of the shipping container is this metal box that surrounds the payload. This metal box protects the payload from the outside, among others from the payloads of other containers. And similarly, a Linux container isolates workloads by setting limits on the maximum amount of resources, processes running in the container can request. And the actual usage is usually much lower. And what's left is the slack, which is this CPU or memory that is wasted. It is claimed by the container, but it cannot be allocated to another container. We have an internal scheduler called Borg, and basically this scheduler uses container limits to pack containers onto machines. It's solving kind of a bin packing problem. You have boxes and you have machines and you have items, containers, and you want to put items to machines. And for at least for this category of jobs, we are concentrating on this high availability, latency sensitive jobs. Borg makes sure that there are sufficient resources on each machine to fulfill all the requested capacity. So so the limits are very fine-grained. You request computational power. I mean, if you're internal Google customer, you request computational power in millicores and memory in single bytes. And as you can see from this chart, it's a CDF cumulative distribution function of tasks by the requested limits. So as you can see, our internal users actually make use of this very fine granularity. And it has been shown in this paper, Eurosys 2015, that if we rounded up the limits to nearest nice looking values, such as 1, 2, 4, or 8 cores, we would need much more resources. So these very fine grained limits make sense to save the capacity of the infrastructure. However, it is very hard to set accurately, to be accurate in these limits. I mean, this presentation is running in the cloud, and our meeting is also running in the cloud. But it's very hard for us to estimate how many bytes of memory or how many cores, millicores, this setup uses. As with shipping containers, you pack machines by the size of the external box, right? The limit, and not the actual payload. So what you see here is a machine that executes 3 containers. And the limits turn out to be just about right. They are slightly higher than the actual usage of the containers. There are 2 kinds of problems that imprecise limits might have. First, limits can be too conservative, as on the left. In this situation, jobs are safe, but the resources are wasted. The machine cannot accommodate another container, yet the actual utilization of the machine is really low. On the other hand, if we are too aggressive in setting the limit, as on the right, a container could request more resources than its limit, or even more resources that are available on the machine. And if this resource is CPU, this container would be throttled, which for latency sensitive job is not so great, because the throttled job would increase latency for the serving latency. And if this resource is memory, it's even worse, because it's out of memory error, so the container would be killed. So Autopilot, the tool we developed, is a tool to automatically set these limits, and also the number of containers a job is executing. So on the very high level, Autopilot is a controller working in a feedback loop. We have recommenders on the left that compute resource limits for each job. And these limits are forwarded through this Autopilot service and actuator to Boardmaster, which is the head scheduler for our cluster. The Boardmaster in turn contacts boardlets, or the agents, scheduling agents running on each physical machine in a cluster, and these boardlets actuate on these new limits or decisions to start a container or stop to stop a container by setting C group limits or starting or killing a container. It's a feedback loop, so we are continuously monitoring how the containers actually use the resources. We feed this data into a database called the resource usage log, and then this input from this database is fed to the recommenders. So the most interesting part is this business logic part, or the Autopilot recommenders, the part of Autopilot that is responsible for calculating resource limits. And I would describe two main types of recommenders that we are currently using at Google. And the type is the simple moving window recommender. Basically, it's a simple time series / signal processing methods that take a time series of the historic usage, and then have a moving window over some length of a history, let's say 24 or 48 hours, and compute some percentile of the requested resources from this moving window, such as the 98th percentile. And we then smooth this response by adding exponential decay. This is basically to smooth the response for that was previously for like some abrupt spikes of the usage. And finally, we add some safety margin just to be on a safe side. And it turns out that this simple mechanism is sufficient to show significant savings over the limits that are set manually. And I will later show you the savings. And this was in production for some time, and rather quickly we realized that different categories of jobs, different types of jobs inside this high availability latency sensitive category require different, slightly different safety margin and slightly different exponential decay rate. For instance, if a job has very unstable usage, we would smooth this job more than a standard, than a more stable job. So we have another type of recommenders. We call them machine learning recommenders. And they basically use ideas from reinforcement learning to automatically tune the parameters of this moving window algorithm. So on a very high level, this machine learning recommender runs a certain number of models, and each model is a parameterized moving window algorithm. So it is parameterized by two variables. One is this rate of exponential smoothing, the decay rate, and the other parameter is the limit. The difference between the safety margin. Sorry. So each model internally has a number of limits, and it picks a limit that is basically argmax, that optimizes the cost function according to these two variables. And then we have a meta algorithm that picks appropriate model according to the historic performance. And we make sure that we don't switch models too frequently, and we also don't switch limits too frequently, because it would impose some cost on the infrastructure. For instance, if we increase limits too frequently, we would need to kill, for some nodes, there won't be sufficient space, so we would have to kill jobs. So we don't want to do this too often. So to evaluate how it works in practice, we conducted observational study of a random sample of production jobs running in our internal cloud. And this observational study, we focus on memory, because out-of-memory errors are harder to cope with than CPU throttling. We measure two aspects. One is efficiency, which is the slack. And basically we measure the slack in two different ways. The absolute slack is the difference between the total limit of a container and the total usage summed over a day. So the absolute slack of 0 translates to the limit, which is always at every time moment exactly equal to the container usage, which is a very ambitious target, as you could think. We also measure the relative slack, which is the fraction of allocated but unused resources. And here, to measure what was used, we take the 95th percentile of usage during a day. And this is 95th percentile because it somehow connects to our accounting system. As you can see, so here is again a cumulative distribution function that shows relative slack of jobs in 4 different categories, and we have 5,000 jobs in each category. So we have 5,000 randomly chosen jobs that are driven by autopilot with machine learning recommender. We have 5,000 jobs driven by autopilot with moving window recommender in yellow. We have 2 categories of jobs that have limits set manually, and one category has hard limits and the other category has soft limits. So as you can see, the relative slack of autopiloted jobs is way smaller than relative slack of jobs with manual limits. The average slack of autopiloted jobs is 23% compared with 46% for jobs with manual limits. To see the absolute slack, we measure absolute slack in machines. So this is a capacity. So I can't tell you the exact number in bytes, but this measure of capacity in machines corresponds to capacity of a single memory capacity of a single large machine in our cloud. As you can see, that the total slack of autopiloted jobs is roughly 500, where the total slack of jobs with manual limits is 12,000 machines. So this comparison is not exactly fair, because you might think that maybe the manual jobs are larger, or manual jobs are more difficult than autopiloted jobs. There is some selection bias. So we did another study. We measured, so we picked 500 jobs that migrated to autopilot in a certain month. And we compared the relative slack 2 months before the migration. This is these dashed lines, manual M-2 and manual M-1. And the relative slack for the same jobs after the migration in these solid lines. And you can see that before the migration, the average relative slack of these jobs was 75%. And after migration, it was reduced to 20%. And the reduction in absolute slack, so the slack measured in machines, was similar. So it really helps. It's not only selection bias. It really helps if a job is migrated to autopilot, it will save memory. We also measured reliability. Basically, we measured how frequent are out-of-memory errors. And we weighted the number of container terminations by the number of containers in a job. So the idea is that the job with 100 containers is less affected when we kill a single container, the job that has like 3 or 4 containers. And first of all, out-of-memory errors are very rare. For autopiloted jobs, 99.5% of jobs days are without any out-of-memory exceptions. And but you can see that still autopilot performs better than jobs with manual limits. So essentially, this shows that autopilot is the two results, that we reduce slack and we reduce the frequency of out-of-memory events, show that autopilot is Pareto better than manual limits. There is no trade-off. It's simply better algorithm in both factors. And you can see here that it seems that autopilot with moving window is slightly better in terms of frequency of out-of-memory events than autopilot with memory with machine learning algorithm. However, we conducted additional analysis in our paper that showed that the frequency is higher, but these errors are not so severe as autopilot with moving window. By severe errors, we count if there are too many containers killed for a single job during a single day. Autopilot has also a significant DevOps impact on our infrastructure. Currently, autopiloted jobs consume over 48% of Google's fleet-wide resource usage. And of course, autopilot reduces toil on the users, because you can just submit your job and don't think about setting these limits. But I will also, at the end, I'd like to show you another perhaps unexpected feature of autopilot, that the fact that the limits are set dynamically and automatically could help to mitigate the impact of bugs that are in the code. What you see here is a screenshot from our monitoring system that shows postmortem of a problem in our with one of our serving jobs. And you see on the left, so there's time on the x-axis and memory consumption on the y-axis. And you can see on the left that we have a job whose memory usage steadily grows. In fact, there was a new version of the job that was released to the infrastructure, and this new version had simply a memory leak. This job had manually set limits, so Autopilot was running in dry mode. It means that the limits were calculated and logged, but not actuated upon. So you can see here that Autopilot would increase limits, seeing that the consumption grows, but it was running in a dry mode. At some point, the containers start to hit the manually set limits, and they start to be killed with out-of-memory exceptions. And what you see between 5:30 p.m. and let's say 7 p.m. is that our DevOps engineers were trying to make this job running, and they were trying to find the root cause. In the meantime, the job was restarting, trying to serve, then ending with an again. And finally, SREs, as DevOps engineers, managed to do a rollback to the previous version of the binary just after 7 p.m. And then, just in case, they increase the limits just before 8 p.m. But still, there was this large gap that the service was not serving correctly. So to summarize, I mean, in this case, Autopilot would help. The limits would be increased temporarily, and they could give more time for DevOps to find the root cause. So to summarize, Autopilot shows the gain from automating cloud resource management. Humans are very bad at setting the limits precisely. And with Autopilot, our fleet runs more efficiently. The relative slack, the amount of claimed but unused resources, is reduced by a factor of 2. But additionally, the risk of out-of-memory errors for individual jobs is also reduced. This risk of hard or significant errors is reduced by a factor of 10 compared to manually set limits. So that's all I'd like to present. Thank you. And if you have any questions, I would be very happy to answer.
So thank you, Christoph. If you can see at the Q&A panel, there are a couple of questions.
Sure.
The first one is from Navneet Gupta about whether Autopilot is under development or in production.
Yes, so Autopilot is in product. I mean, it's continuously under development, but it is also used in production. As I mentioned, 48% of our resources are under Autopilot control currently. Production resources.
Okay, so there's one other question.
Sure.
From Gabriel Ara from Scuola Superiore Santa Ana, Pisa. Does the actuator in the loop leverage the deadline scheduler inside the Linux kernel to both reserve and limit the amount of computation time or millicores available for each container? Or are they scheduled only using cgroup and CFS scheduler?
I'm not sure about that. These containers have so containers have limits, but containers driven by Autopilot have soft limits. So it means that the container can briefly go over their limit, its limit, if there are sufficient resources available on the machine. But if it does it too frequently, or if the resources start to, if there are insufficient resources, we start to kill containers. And I'm not sure about how it is translated into Linux kernel or C groups. I think that the Borg paper could help here. The Borg paper from 2015, I guess. And there is another question I see from Sitaram Silam. What happens when there are no resources in the node to scale up? Yeah, this is a very good question. So a node is typically shared by many jobs, and so many containers belonging, and each container has some priority. So if so, the highest priority are these high availability latency serving jobs, and but we also have some lower priority jobs like best effort jobs. And if there are no resources, we kill. So, for instance, if Autopilot decides to increase the limit of a certain container, and then it happens that there are insufficient resources at some nodes, we start to kill containers from jobs with lower priorities. And we do this until there are sufficient resources. So the idea is that there are it's very improbable that we will have so many house jobs, so high availability latency sensitive jobs at a single node, so that they would start to kill each other when scaling up. Okay.
Okay, I think we're a bit over time. Thanks very much for your presentation.
Thank you again for inviting me.
The questions. Our next speaker is Holger and Stefan, I guess, from Atos. They will be presenting rootless containers with Podman for HPC. Holger, can you share your screen?
Yes, I'm working on it. Just a second.
Great. We can see your screen.
And there we go, perfectly. Thanks for having us. So the talk, the paper we're going to talk about today is our experience describing we had with rootless container with Podman for HPC. And as we've seen from Dan's talks before, there are quite some questions around this. We hopefully can contribute a bit at answering these, and we'll also have another round of Q&A afterwards. So who are these guys talking to you today? 2/3 of the team are working for the Atos part of, for the part of Atos that used to be called Science and Computing AG in Tübingen. And we deal with automotive customers from all over Germany and worldwide. And there's the third person who cannot be with us today is Christoph Reich, who is professor at Furtwangen University and head of the Institute for Data Science, Cloud Computing and IT Security. And then with me, we have my colleague, Steffen Walter, and of course me, Holger Gantiko, and Steffen and I will, do this talk distributedly. So what have we planned for today? First of all, we give an overview with what we were aiming to do with this work. Then we provide a brief introduction to the key features of Podman, hopefully refreshing some of the things Dan was talking about before. And then we'll share some details of how we evaluated Podman in our environment. And then we'll also share the limitations of rootless Podman we came across and what the current state of these limitations is. And before heading over to the pre-recorded demo session, we give a brief summary of the key outcomes of this work, and then I guess we'll have plenty of time for another round of Q&A, to which we would also like to invite Dan and our favorite Podman developer, Valentin, who should also be in the room as well, I think. So how did we come this far? What has happened in the world of containers over the last couple of years? Very briefly, containers improve the mobility of application and delivery of user-supplied code to meet the demand for flexibility in a converging future of compute. This means we have novel software stacks and workflows to support data science, for example, including AI and machine learning, and additional to traditional MPI-based workloads, the world we are coming from. And we also, most customers are looking for a way to have simplified use of distributed resources across multiple locations. And of course, everybody wants the cloud these days, the cloud as well. And the containers can help quite easily, and they help as they decouple applications and the dependencies from the underlying operating system and encapsulate them in an easily redistributable unit. And while this abstraction is, often not fully true given the special requirements of HPC environments, there's been a nice paper on this at SC last year. And due to the hardware, HPC specific hardware and related libraries, such as the MPI libraries, the current state, in my opinion, still represents quite an improvement over the last couple of years. And this is also thanks to the interoperability that came in by the Open Container Initiative specifications. And as of now, there are plenty of HPC workloads around. We have Shifter, we have Singularity, we have Charlie Cloud, we have Saurus. And those runtimes are great for HPC centers, but sadly less often, at least except Singularity, adopted by enterprise users. So, and beyond that, enterprise users would rather prefer unified solutions suitable for a variety of containerized workloads, including and not being limited to HPC, as it would be the case if they went with Shifter, for example. And Podman, in my opinion, fills this gap to a great extent. It provides support for strongly isolated regular container workloads as you have them in enterprise environments, and feels much more natural in an HPC environment than Docker ever did, and given Podman's implementation. And as Dan previously pointed out, Podman bridges the gap for going from single node runtimes to Kubernetes. And given these attributes, we investigated the suitability of Podman in the context of HPC and identified current limitations. And therefore, we concentrated on the performance of the container engine with both run C and C run as runtime, compared it to native bare metal performance and the HPC-focused Singularity runtime, which you often meet in enterprise HPC environments as well, besides HPC-focused data centers. And we were especially interested in the overhead introduced when processing a real-world workload by using the finite element analysis application LS-DYNA, which is more or less the bread and butter application of our customer. And this application is widely used in the automotive industry for crash test simulation. And beyond that, we completed our investigation by a series of industry standard benchmarks. And what about Podman? Just a brief summary of the key aspects. Dan probably covered all of them in greater detail than I ever will here. So first of all, Podman is a daemonless container engine for developing, managing, and running OCI containers on your Linux system. And one of the fun things about it is that some of the Docker environment, that for most of the smaller Docker environments in which users don't rely on advanced features such as Docker Swarm, setting an alias can already be enough to make the transition and switch over to Podman. And I guess this might take some users weeks or months to come across this change. Then typically they just find out about it if they read the man page more carefully and only find references to Podman. And it comes from the enterprise breed of container engines, meaning that by default it provides as much isolation as possible. This includes a wide use of namespaces, the support for ZComp filters, which however we also have in Singularity, but to restrict the available system calls, we have support for Linux security modules such as SE Linux and AppArmor and much more, and all the tools needed to isolate containerized workloads from each other and the host as well, and which is, however, not necessarily ideal in HPC environments. So, but most importantly, it supports rootless containers, which allows the execution of containers without privilege escalation mechanisms such as a root daemon or ZUID binary. Podman, like Charlie Cloud, uses the user namespaces functionality for this. And this means that the process inside the new user namespace has different privileges and user IDs than those outside and require corresponding configuration of etc, ZAP group ID and UID, but this is something Stefan will cover a bit more in detail. And another nice thing about Podman is that you can either use run C or C run as a container runtime. Run C is written in Go, is also used by other container engines such as Docker or Cyrus, and but it also supports the state-of-the-art and C implemented runtime C run, and this is best described by the developers as a fast and low memory footprint runtime, and C run is currently used as the default runtime in Fedora, as it already migrated to the resource limiting feature cgroups v2, and which is only supported by C run as of now. And our version of Podman we use for evaluation shipped with run C, but we also went and tried C run. And as the name Pod Manager implies, Podman supports the concept of pods, which is a set of applications being closely tied together and forming a more complex application. And the nice thing about it is they are not completely isolated from each other, but share several namespaces, which simplifies the communication. And this, for example, would allow to have purpose-specific sidecar containers, such as a data container along your application container, and to support a job. And yeah, as Kubernetes is based on pods, this provides an increased flexibility in a converged environment to either launch suitable workloads in Kubernetes or use Kubernetes workloads with Podman. And Podman also supports the concept of OCI hooks, a mechanism used fairly well by Zaros to extend the runtime functionality. For example, they use it there to provide a mechanism for improved synchronization with Slurm as workload manager. And we have also the nice feature of Builder integrated to build OCI compatible images from Dockerfile without having root privileges or any background services running, and which is a notable improvement over Docker-based build processes. And this might be something that might be also interesting for other container engines, such as Shifter, that currently still rely on the Docker build process to create the images. And beyond that, we have support for checkpoint and restore in user space. This, however, sadly cannot be used in combination with the rootless containers and when using MPI and InfiniBand-based workloads as of now, but hopefully we'll see a bit more about this. And taking the enterprise perspective for a second, Podman's development is driven by Red Hat, which guarantees a certain reliability and as well leads to the state that Podman is included in the RHEL-based distributions such as CentOS, which many HPC sites rely on. And of course, enterprise users are happy to make use of such a single vendor strategy where everything comes shipped in one box and is ready to go, and you don't have to deal with plenty person here. So if Podman is usable for HPC, it provides an interesting path towards a shared environment where available systems get used for different workloads and more towards Kubernetes. So briefly comparing Podman to Docker, Docker started the whole container hype. Despite LXC being around for years, and container engine is nowadays just something that is not super new anymore, but rather a necessity expected by many researchers and power users to be able to bring the user supply code into the compute environment of their choice. And some of these environments are already taking the next step, hopping over to Kubernetes, bringing Kubernetes in their environment, something we will also hear a bit more today, I think. So Docker had quite a bit of a head start, but sadly lacked the interest in the HPC environment. But beyond that, HPC clusters operated typically were quite assistant to implement the Docker architecture and process model, which is something we already had in Dan's talk, as it poses a source of security concern. It restricts the auditability. And just to refresh your memory, I included this diagram from Thorsten Memhus that visualizes the process model quite well. And to be able for the user to use the Docker command, a user either needs sudo privileges or needs to be part of the Docker group. And then, as Dan described, we have two daemons in action. The Docker client communicates with the Docker-D by using a Unix or network socket. Docker-D instruments container-D, also by using the Unix network socket and then container-D. Uses a fork exec to tell runc to spawn up a container, and especially the switch from the user to the root context and the socket approach is seen a bit problematic, although the later setup is more natural for distributed environment where Docker originally came from. And on the other hand, if a user uses Podman, all steps required to spawn a container stay in the user context, which is far more traditional and rather expected behavior. And previously compared to Singularity, based on the described necessity for the researchers and according to Greg, some threats and bribes as well. This is how Singularity came into being, and it's currently the HPC-focused container runtime with the largest user base and has also several commercial users, and can be considered the de facto standard for HPC-focused container runtimes. And as it comes from the HPC-focused breed of runtimes, it uses only as much as isolation as necessary, which translate on the one hand into almost transparent experience for the user by reducing the difference of being inside and outside the container. But on the other hand, implies the use of less namespaces and another isolation mechanism. So for regular containerized non-HPC workloads, this approach is a bit less ideal, as this high level of visibility of the host system is typically not designed for strongly isolated workloads where you want to hide the workloads from each other and even from the host system. But for HPC system where there's only one user having his job on one node, this is something we can agree on that it's okay to do, but not for if you want to have a shipload of containers running on a single system. And the required steps for privilege escalation is implemented by setuid binary approach. I mean, not everybody is a big fan of, but has been audited previously, and there exist alternative approaches, but the setuid approach is still the most frequently one used. And due to the transparency of the host system, Singularity is comparatively easy to integrate into workflows and job submit steps where the engines need a stronger modification of the call, and the Singularity specific image format is also quite beneficial in terms of performance. So enough of the refresh. What did we do to evaluate Podman in our environment? And in the end, we came up with 4 distinct runtime environments or execution environments. So the baseline of everything is the bare metal setup, which is the traditional way of computing, is done since basically ages, and the procedures are well understood, and it uses a proven infrastructure. And we opted for Singularity as best non-HPC focused container engine that is easy to integrate into existing workflows and can be installed on a node by using a single RPM without further dependencies here. And then, of course, there was Podman that makes it harder to get HPC workloads up and running. As it's a bit more complicated to get this going than Singularity, but at least the installation was quite easy, as it was part of the CentOS 8 installation used for all execution environments here. So this slide shows the configuration of the test environment. We will not go into that much detail, but the environment is part of an automotive industry environment with several hundred nodes used almost solely for crash simulation, aerodynamics, and a few other CAE workloads. And the test environment consists of one cell consisting of 8 nodes, and as the rest of the cluster is interconnected using FDR InfiniBand, the nodes are equipped with SSD-based local storage used for the OS installation, for the container images and scratch space, and it uses CentOS 8.1 with permissive SE Linux, but beyond that, no additional tweaking of the, or major tweaking of the setup here. And we also use a local evaluation user. Why this? A bit more later. In order to increase the reproducibility, we also listed the components and versions we used. And as MPI implementation for LS-DYNA, platform MPI is used, and the versions used represent the latest versions available at the beginning of the time of the evaluation, at least in regards to the kernel and everything regarded to the containerization layer here. So a few remarks on the application LS-DYNA. And it's a finite element analyst software, and it's used to simulate the impact of crashes, explosions, and sheet metal stamping, and it's widely used in automotive industry for crash test simulation, and as mentioned before, the core application that is used at the site we operate. So basically, every engineer there knows this application and relies on it. And as input model for LS-DYNA, we use the car-to-car model, a widely used testing workload originally published by the National Crash Analyst Center to measure the performance of DYNA. And the model includes 2.4 million single elements and simulates the frontal crash of 2 mini cars, each running at the speed of 35 miles per hour, which you can see a snapshot here. And the larger model covers the first 120 milliseconds of the crash, and for quicker turnaround times of the simulation, we also created an additional model that only covers the first 20 milliseconds, and we refer to these workloads later as short run. This is the 20 millisecond run, and the long run, which is 120 millisecond configuration. So Stefan will this cover as well later in the demo, but just for having it on the slides, there were quite a few adjustments required to be able to have an MPI application running, and the adjustments had to be made here in this case where inter-process communication and shared memory access required the sharing of the PID and IPC namespace. The net namespace must also be shared between the container and the host, so that MPI on the host can manage inter-node communication. And yeah, these adjustments are achieved by appending the command line parameters -- net equals host, PID equals host, and IPC equals host. And furthermore, we also use env equals host to pass the host environment into the container. And we use we bind mounted volume as a shared working directory, and we also had to pass the InfiniBand device into the container to also confirm the question from the talk before. This is possible, and in my opinion, we came up with quite a few interesting results here, and these results are based on the elapsed time to normal termination as reported by the application. So the application always tells you in the end how much compute time it required, and this is this figure here. So the key points here was that all container runtimes introduce a certain amount of overhead compared to native execution to the simulation. However, this is only in the range of 1.85% up to 5.10% for the arithmetic mean of the short and the long run here. And in my opinion, this overhead might be negligible for many workloads, or the benefits you get with containers, especially as 2 out of 3 runtimes here, naming them Singularity and C-Run, only at 2.04 or less overhead here. And although Singularity causes the least overhead, the differences of Podman in combination with C-Run as runtime compared to Singularity are quite minor, especially for the long run of the LS-DYNA application. We saw an overhead of 1.61% versus an overhead of 1.6.2% with Podman C-Run, and translated this into overall runtime. This is less than 1 second difference between the two container runtimes. So the overall run of the distributed MPI run here was 6,521 and a bit more seconds, and the other one, the result for the Podman C run was also 6,521 seconds. And so the difference is roughly a half-second difference here. And compared to Singularity, the performance of RunC is noticeable slower here. And we are currently still in discussion with the Podman developers, and according to them, there's indication that the slight difference of Podman with crun compared to Singularity might be related to Podman's isolation mechanisms, which are active by default, such as ZACCOM profile, or even if there's only this very basic default profile, he needs to do the checks, and so on and so forth, and more extensive use of namespaces here. So now I can take a sip on a tea and hand over to Steffen.
Okay, can everybody hear me?
Yes, confirmed.
All right, so I'm gonna go ahead and talk a little bit about the standard benchmarks that we have done additionally to the LS-DYNA. So to round off our work on the performance measuring of benchmark containers, we ran some industry standard benchmarks to ensure comparability with other evaluations, like, for example, the paper of Torres et al. That has been presented at the Supercomputing Conference last year. We used the stream benchmark to measure memory performance and the sysbench for CPU speed measuring. To make sure to actually measure the memory bandwidth and not use the CPU caches instead, it is necessary to increase the size of the array that is used for the vector operations. In our case, we increased the elements per array to 3 billion by modifying the corresponding preprocessor definition when compiling stream. With sysbench, sysbench calculates the prime numbers between 1 and a limit that is passed as a command line option. And in our evaluations, we used 40 million for this limit, so that sysbench can, in one run, sysbench calculates all the prime numbers between 1 and 40 million. The results that we came by with our benchmarks are that the differences within the container environments and the native execution of sysbench only differ by 0.4%, which makes it quite hard to make any kind of conclusion out of the values. So the only thing that is safe to say when looking at the numbers and the graph, by the way, which is the upper one, is that that there seems to be no added overhead by containerization, and the differences are so small that I cannot read anything into it. The results of the stream benchmark differ by a slightly larger amount of about 1%. And when looking at the copy part, which is the far most left of the lower diagram, we can see that there are similarities to the results of the LS-DYNA benchmark that we saw earlier. And we suspect that the overhead measured with the containerized LS-DYNA is at least partially connected to the memory intensive operations, because even though the differences are very small in that we measured with stream, the looks of the diagram is very similar. And from our point of view, however, the overhead of 1% does not impose a considerable overhead when using containerization. Okay, can use. Thank you. Okay, so when we used the Podman command line interface and program, we came by some limitations and problems. And most of them are related to rootless Podman. What was the only thing we were testing, because this is like a hard demand for production HPC managing. Okay, so Podman uses, as we heard earlier by Dan, and uses sub-UIDs and sub-GIDs to separate container processes from the users and groups that are known to the host OS. And this adds security, because if a container process gets hijacked by an attacker, there is no corresponding user known to the host which the ID of the process is connected to. Since Podman relies on this feature in many ways, the mapping of the IDs must be set on the host, because otherwise some Podman commands will fail. For us, this was we ran into this problem because when we work with MPI jobs, we cannot make use of this feature, because when we want to use shared memory access and shared file access, then the set UID and set GID feature breaks the access modeling. So we set it up anyways, because as I told before, some commands will fail if it's not set up. And this is done by editing the etc sub-UID and sub-GID file as stated out, as shown on the slide. Okay, so when trying to configure the IDs with a network-based authentication system like LDAP, this produces this procedure, like I told you here, will not work, because such systems do not utilize the configuration file sub-UID and sub-GID. So at the moment, it is quite difficult to get this set up, which is why we didn't do it and went with the local user. But fortunately, according to the Podman developers, the addition of new directives in the nsswitch.conf is made to support the sub-UID and sub-GID databases. So this is, as we are told, work in process. Okay, so another thing we more on accident came by is the startup and teardown time. So what we wanted to know is the difference between the time that is given back by the LS-DYNA application as total elapsed time, and the actual time that is consumed from hitting enter with MPI run and closing up the command line command, whatever.
After the application returns.
Yeah, exactly. So MPI run itself needs some time to connect to all the nodes and start the application. And what we measured was that this delta is roughly 3 seconds for the native execution of LS-DYNA. When using Singularity, another 2 seconds are needed to start up and tear down the containers, which sums up to 5 seconds in total. But Podman, however, produces a delta of 25 seconds, which means that 22 seconds are needed to start up all the containers and in the end tear them down and do some cleanup work. So the most probable reason is that this is due to the layered file system of the OCI image that needs to be set up and torn down again, combined with an image size of 2 GB roundabout. And the Singularity uses one flat image, which is supposedly easier to set up. Okay, now some other limitations that did not affect our evaluation, but can be relevant to other HPC environments. It is that there is a lack of direct Slurm support, and it is not possible to bind to ports greater than 1024 because they are privileged ports and should not be utilized by users. So this is, it works as intended, but can be an issue though. And also an issue is that the inability to run from home directories on NFS and GPFS, like we heard in the Q&A of Dan's talk. In addition, rootless Podman does not support CREU's checkpoint and restore feature and cgroups version 1 yet. So the issue with cgroups will be solved in the long run by moving to cgroups version 2, which is already supported in Fedora 31 for crun at least. A comprehensive list of all the limitations that apply to rootless containers is maintained by the Podman developers on GitHub, and I find it very informative. This is it for the limitations, and now Holger will take over again and tell us about.
Before we head over to the demo part, just a brief summary of what we heard so far and some conclusions. So Podman is essentially suitable for use in HPC environments. The performance we observe with the application is on a very similar level to Singularity, especially when used with crun as a runtime. We are currently also in contact with Lukas Benedicic from the CSCS Zaros team to further investigate our observed benefits of crun over runC, as Zaros currently relies on runC as OCI compatible container runtime. And as of last week, he stated that the Zaros team will be spending quite a bit more time soon on crun in the coming months. However, Podman does definitely not render all the HPC specific runtimes obsolete, at least as of now. They have just special strengths, such as the simplified integration with Workload Manager and, for example, Singularity, special image format optimized for shared storages in HPC environment, and at least in the current version, the several limitations that still apply to Podman, and we heard about just of now by Steffen, especially the NFS topic and the problems when accessing directory services are just some points that are rather painful. However, Podman supports features quite beneficial for newer workloads and converged environments, such as the concept of pods and the possibility to use stronger isolation. And both topics we want to take a closer look at in future work, and how we can benefit from them. And by supporting the pod concept, Podman also bridges the gap towards Kubernetes here. And another feature we consider quite beneficial is the ability to create images with user privileges only using Builder. This might be quite interesting to include with other runtimes that still rely on the Docker build process, because basically anything an OCI image nowadays, and even Singularity supports OCI images, even though they transform them into the flat ZIF images format. So before I hand over again to Steffen for the demonstration, thank you very much for having us. And in case you should have tomorrow or whenever have any questions, feel free to contact us, and the contact info are also in the paper. So I'm going to stop sharing my screen now and give the screen control over to Steffen.
All right, so now you should see the VLC player. Is this working?
Yes.
Okay. So what I'm going to show you now is the run of a short run actually of an LS-DYNA benchmark car to car that we performed. And first of all, I'll show you the bash script, little bash script that I created to start those jobs. Okay. So what we see here is the pretty long command line that we need to get everything right for the MPI LS-DYNA to run.
But still more simple than the YAML file, Steffen.
Yeah. Okay. To make sure I've got the environment right, at the beginning I source a file that sets some environment variables, such as the path, the library path, information that is needed by LS-DYNA to verify that there are valid licenses, and also some information for the MPI communication that MPI communicates over SSH in this case. Then we see the MPI run call. As we heard before, platform MPI is used in this scenario, and it is called to force InfiniBand as interconnect for the cluster nodes, and to source the host file that contains the host names of all the 8 cluster nodes and the number of processes that are started on each node. In our case, this is 24, since each node has 24 CPU cores. For each of the processes on Podman one Podman container is started with the following options. So since we had better results with crun as container runtime, it is also specified here by the -- runtime option. To make sure that the environment is set that I set up earlier is present within the container, I use the --env -host option, and this basically maps the environment of the host into the container. I'm sure there are other ways to get the environment as I wanted to be in the container, but yeah, in this case, we went for this way. Like I told you earlier, it is not possible to use usual mapping of sub-UIDs and sub-GIDs when working with MPI jobs. So to suppress the use of the ID mapping, the option user NS equals keep -ID is used. So this is an option for the user namespace. Also, to make shared memory access and inter-process communication possible, it is the containers need to share the PID and the IPC namespaces. And for MPI to recognize to organize internode communication, it is also necessary that containers and hosts share the same network namespace. To provide a shared directory on each host of the cluster for all the containers on one node, the local home directory is mapped into each container. We told you earlier that Podman has problems with home directories that are located on NFS and GPFS. In our case, this is not a problem because also, like I told you before, we have local home directories with the local user on each cluster node. Besides sharing the net namespace, it is necessary to map the /dev/InfiniBand directory into each container. This is necessary to use the InfiniBand interconnect from within the containers. Since in the demo environment we do not have a container registry, I imported the LS-DYNA image into the local registry. So we can see here the image that is called is localhost LS-DYNA. And what I am going to show you now, or what you see after the image call, is the call of the application with some options that, well, are not so interesting right now, I think. What I show you now is the start of the application. When calling the script, the containers are created on all compute nodes and the application is started. At the beginning, it prints out some basic information about the software, the distribution of the processes, and some license informations. What we see here is in the last line, open include file. There we see that the model of the first minivan that is about to crash into the other one is loaded. And when we go further, we see that the other one is loaded as well. Before the actual calculation begins, LS-DYNA prints an estimate of the time that will be needed to finish the workload. We can see it right here. 1 hour and 58 minutes. If it would be one host divided by 8, we will have about 20 minutes to finish the job. And because I don't want to let you wait that long, I increased the playback time a little bit. What we see is the steps for the calculation. Yeah. Okay, so what you see there is I needed to obfuscate some of the output because it contains host names of the cluster and I'm not allowed to share those. So what we would see here are the stats about the processes on the cluster. So how much time one process needed and so on and so forth. So, but what I can show you again is the final messages. We see in the end that the total elapsed time is 1,121 seconds, which corresponds to 18 minutes and 41 seconds, which is quite good. And we also see that the calculation has been done in 192 parallel processes and that the application terminated without an error code. At the very end of the output, we see some error messages from Podman that originate from a bug where Podman tries to close a namespace repeatedly, even though it's already closed. But this bug already has been fixed in a later version of Podman. Prepared another video where I also start Podman, but put the output into, or redirect the output into a file and put the application in the background to watch what's going on the host system. For that, I'm calling the program htop. And what we see here is the spawning of the containers. We see 24 processes of LS-DYNA, and the system goes into full utilization. We also see at this point that hyperthreading is active since we have 48 threads. Moving down the process list, we can also see there are some processes of Fuse overlay FS that are used to serve storage to the containers. When looking at the whole line here of the process, we see that the LS-DYNA application is called with the parameters that we saw earlier in the script that I specified in the end. Now we take a look at the containers from the Podman perspective, and we see that there are a bunch of active containers. And yeah, since I zoomed in a little bit so you can see everything, we cannot see the whole list, but if we could, we would see exactly 24 LS-DYNA containers that are started. Here we see round about a minute ago. The last thing I want to show you in this demo is the list of the images. We see, like I told you before, there is on the local registry, there's the LS-DYNA image that I created some time ago, and also another image that I downloaded to play around with pods a little bit. This is it with the demo. I think we have 10 minutes left for questions and discussions, so please go ahead.
Thanks very much for the talk. There are a couple of questions. There's one left from Dan Stock. So Thomas Aliaga mentioned, have anyone tested migrating sub-UID mappings across different VMs, different kernels, or a way to migrate a Podman container to a different VM?
I think this could be achieved with the CREO, the checkpoint system, but I have never used it before.
But luckily, among the attendants, you have one of the developers. I think Adrian Reber is still doing work on CREO, and maybe you can get in touch with him, or even invite him to the panel as well. I think, yeah, CREO should be the way to solve this here. But this also brings us to the question of CREO and. Maxim, to get your question right, you were asking about support for InfiniBand-based workloads. Does this refer to InfiniBand-based workloads in combination with Podman or in combination with CREO? Because at the next question you ask is that rootless CREO does not work. So Podman plus CREO plus InfiniBand, right? Okay, I'd be hoping for this. To be honestly, from an HPC operator's perspective, this would be perfect. Just moving your if you have like a planned downtime, yeah, shift your workload around and have everything going and coming up on another machine. But I think we're just not there yet, and I'm the wrong guy to answer how long this will take, but I guess Adrian might be able to answer this.
So Adrian, you're now a panelist. If you want, you can unmute and comment on the two issues mentioned.
Yeah. Can you hear me now?
Yes, perfect. Welcome, Adrian.
Okay. So the question was about container migration of InfiniBand processes, right? Or processes using InfiniBand?
Yes.
Okay. So you mentioned in your talks that you cannot migrate containers as non-root. This is currently correct, but it's interesting that you come up with it right now. I actually posted Linux kernel patches last week, which are currently under discussion to make CREO work as non-root.
Wow.
So we are working towards non-root process and container migration. This can work in the future. The big problem here is InfiniBand, and I think every checkpoint restore implementation has the same problem with InfiniBand, because as far as I'm aware, you're not able to get the state of the InfiniBand hardware out of the InfiniBand hardware. So you cannot really migrate an InfiniBand connection. So what you have to do somewhere at the MPI level, make sure that the communication, the InfiniBand communication is actually stopped, that there are no more in-flight messages. And if your MPI layer can handle that, then with the ongoing work to support Creo as non-root, and once this might be integrated into container runtimes like Podman, it can be possible. Yes, but it's probably a long way to go. Especially the integration into MPI, I think is the most complex part here.
Yeah, and these are things not moving that fast. Thank you, Adrian, for pointing this out. And I wasn't aware that you're currently working on exactly this perfect topic, but thanks. That's really cool to get this going. So are there any more questions here? In case you came up with another Podman hardcore related question, we also invited Valentin Rothberg, our favorite Podman developer, and go shoot at us and shoot at him as well. And one thing I also wanted to mention is a big thank you to everybody working at Red Hat and who had to deal with all the GitHub issues we had to open and had to take care of them. Thank you really much. And there's another question regarding InfiniBand migration. There's also a problem that the user process is exposed to a physical ID. This makes migration even harder because you would need some InfiniBand overlay network. So more work to be done here.
I think we have a couple more minutes if there's any other question. I guess there isn't. Thanks very much for the talk and the demo and the Q&A session. Michael, the floor is yours.
Thank you very much for having us.
Thanks for having us.
Thank you. This was a very good talk. And again, are you gonna be around for any direct questions from the attendees? Very good. Very good.
I'll be probably around until the hard end at 1 a.m. So
very good. So you will be with us for the final discussion. That is.
I'm planning so at least.
You're planning,
if I should fall asleep at the desk, probably not, but not as of now.
Highly recommend chocolate. It's it works. Yeah. So now we have a little bit of a shift in the program. That is, we're going towards Kubernetes. But before that, let me just wrap up the Podman side of things, and I'm sharing a slide deck here. We'll make it available later, but one hacking point, so to speak, if you want to get started with Podman for HPC, is to use a MPI sample and Adrian has written a short MPI ring demonstrate Open MPI through Podman. You can either scan the QR code up here, or I'm gonna send the URL directly to the code into the chat as we speak. So well, the view has changed. 1 second, chat, there we go. This is indeed recommended to get started with it. A deeper reason is it's a good thing if you build a little bit of a community around it. So needless to say, HPC is always a little bit assembly required if you go to the higher scales at least. So the more people use it and try things, the better it is. So that being said, let me show another summary here. So no share. Now this one here. There's also here you have got a little bit of a summary of what the Red Hat the prior talks also touched on. So rootless, of course, was a key point. Builder, so that's something to consider if you have lots of Docker files, Docker scripted things, just to slowly but steadily consider that there's not only Docker. And of course, Kubernetes is coming up. Having said that, we're going to Kubernetes as a topical area. So let's quickly bring up the agenda again. The next talk is gonna bring us into the intersection of HPC and Kubernetes, whereby this is not an easy topic, as it's been going on for a long time. You should be seeing the agenda. Yes, there it is. It's been going on for a long time. What happens if you have an existing HPC, Slurm, etc., a scheduler environment, and there you have got this uprising container environment, in plural. How do you, are these two islands, how do you bring them together? For instance, I've done it so that the Slurm calls then it was some time ago with the Docker calling on Docker, but as the next paper is gonna present, which is called which is called Seamlessly Managing HPC Workloads for Kubernetes. It will demonstrate that that state can actually be held not by the HPC scheduler, but by they call it workload side of things. So by the Kubernetes, going into the classical legacy HPC schedulers. The paper is being presented by Sergio. And again, maybe we can also change a little bit in this coming section from pure Q&A at the end. If you have questions during the talk, there is a raise hand feature. You can just write something to the chat, and I'm sure we'll manage to pass the audio to you so that you can ask questions as it's being presented. This being said, I will pass the token to Sergio. Please go ahead.
Hear me?
Yes.
Okay, I will share my screen. Do you see my screen? Okay. I don't hear anything. I don't hear anything. Well, I will start. This work has been in collaboration with two of my teammates at UPB, Ignacio Raquel and Jose Damian, and with two persons from Krakow and Sefer, Malika and Maria. The presentation has this index. I will start with a motivation of our work, then I move to the requirements that we identified for. Okay. Can you hear me now better? Okay. I will try to improve the audio. Now you hear me?
Yes, it's much better.
Perfect. So let's continue. The index of the presentation is the following. First, the motivation, then the requirements that we identified. Next, we move to our proposed solution to deal with this problem. And finally, we show how our solution works, and we conclude. Will conclude with some conclusions. So, there are a lot of scientific workloads that combine requirements that could be efficiently addressed using high throughput computing and high performance computing. Depending on the workload, you can use an HPC infrastructure or a cloud platforms. Cloud platforms provide access on demand, and they are much more flexible than HPC systems. The application portability and delivery are a key issues in cloud and now also in HPC. And containers, as we are here, we can see that containers are the most popular technology for application delivery. There are a lot of container technologies and runtimes like Docker, Singularity, Podman, and a lot of them. We will use in our demo Docker and Singularity. Also, there are a lot of job schedulers, and as you know, job schedulers manage the remote execution of application on the resources. Regarding cloud job schedulers or container orchestrators, we have Kubernetes, Mesos, Docker Swarm, and Noma. We will use Kubernetes. Regarding workload managers on HPC infrastructure, we will use Slurm. A lot of institutions can take benefit of employing an hybrid processing platforms composed by an HPC system and a cloud infrastructure. Also, we have institutions that have cloud infrastructures currently used. So they want to add a new, or they gain access to can use an HPC infrastructure, but this is integrate the access to a new HPC infrastructure with an existing cloud infrastructure are very complex, because you have to take in account, consider a lot of aspects, and commonly you don't have administrator privileges in the HPC infrastructure and the cloud infrastructure. So the problem that we face up is to combine an existing cloud infrastructure with an HPC infrastructure. Generally, in the literature, there is no general approach to handle this problem. So we identified the following requirements. We think that the users must use the same method to submit or cancel the jobs to the explicit infrastructure than the cloud infrastructure, the same method that are using now. The job scheduler used in the cloud infrastructure must manage the full job life cycle in the HPC infrastructure. Also, the data required in the executions in the HPC infrastructure must be accessible. Another requirement is that the user does not need any special privileges in both environments, in the HPC and in the cloud. And of course, the solution that we want to provide should be extensible to deal with the different job schedulers and other than Kubernetes and different workload managers and other than Slurm. So we thought about solutions, and one option could be to develop plugins or extend functionalities on the cloud, in the cloud job scheduler and in the HPC workload manager user to make them compatible, to make compatible the Kubernetes pods to the job in Slurm and a lot of the things that they need to be compatible. We identify some disadvantages because you must have administrator privileges in both environments. This is absolutely very complex because if you have 3 or 4 different HPC infrastructures, you must integrate these 4 HPC infrastructure with the cloud job scheduler. You should deal with the job schedulers updates and in the cloud and in the HPC. But this is the perfect combination of the job schedulers. Another option is less strong, is only to adapt the cloud job scheduler, because in this option, the institution only have to have administrator privileges in the cloud environment. But we have the same problems that in the option 1. You should deal with the job scheduler update, and you have your job scheduler totally adapted to the HPC workload manager. Our solution is a very simple approach, follows a very simple approach. Yes, and it's to create a layer between the cloud job scheduler and the HPC workload manager and do all the changes in this layer. This layer is our tool, which is called HPC connector. The idea is the following. Basically, first, instead of the user launch an HPC job to the HPC system, they submit a mirror job, which is HPC connector, to the cloud, like a normal job to the cloud, with the HPC job specification. Then HPC connector submits the HPC job to the HPC backend. Afterwards, the HPC connector monitors the HPC infrastructure, well, the workload manager queue, until the end of the execution of the HPC job, or until the cancellation by the HPC workload manager. At the end, when the job finishes, the true job, the job that is running in the HPC, the HPC connector get the logs if it is possible. Summary, the HPC connector is an open source tool and which is implemented in Python. So it can run on bare metal or inside a container. Besides, HPC connector can catch the operating system signal SIGINT of the cloud job scheduler in order to trigger the cancellation on the HPC job. So we can stop the job if the workload manager in the HPC infrastructure cancels the job, and if the user cancels the job using the cloud job scheduler. So we have here the job scheduler, the cloud job scheduler manage all the life cycle of the job. And how we can do that? The idea is to create a superclass named backend to bring together all possibilities. We use a backend superclass, and each HPC backend will implement their subclasses, or they will extend the backend class. And what things we have to extend? We have to implement the job submission or cancellation, get the state of the job, and if you want the HPC backend allowed to do it, get the logs. For example, HPC connector supports the access to the Prometheus supercomputer, which is a supercomputing of the top 500 that is in Krakow, Poland. The workload manager used in the supercomputing is SLAR, but they provide two services: the robust remote process controller, or RIMROC, to manage the execution. So we don't have to interact with SLAR, we have to interact with RIMROC to manage the applications. And another services, which is PLG data, to interact with the file system, all with via REST API. Here we can see an example of the implementation for the Prometheus supercomputing backend. The function for job get the job state. So our option also have to deal with the HPC job scheduler updates. We have, besides a small overhead, because we have two jobs. One job running in the cloud environment, which is the execution of HPC connector, and the true job, the job that is running in the HPC infrastructure. The solution does not require any special privilege, because you are running a normal job in Kubernetes, and you are running as a normal user in the HPC infrastructure. If your institution wants to use other backends, or the HPC backends, you must implement a new backend. You must implement a new extension of the backend class, but it's easier than implement implement functionalities of the job scheduler. And with this approach, the users are submitting and canceling jobs using the cloud job scheduler. To demonstrate our tool, we execute this use case. The use case consists of a training of a neural network using TensorFlow to perform an automatic segmentation of neuroblastoma tumors. The system The cloud infrastructure is a Kubernetes deployed in our private cloud based on OpenStack. We are using Docker, and in the HPC infrastructure is the Prometheus supercomputer that I said before. They are using SLAM, and the container technology installed there is Singularity. So first of all, we have to define a config map, which is an Kubernetes object to configure HPC connector. This is the configuration of to access the HPC backend Prometheus, and we have here the endpoint and here the authorization to the authentication to enter Prometheus. After configure HPC connector for access to the Prometheus, we have to create the HPC job configuration. Rimrock uses a SLAM script in plain text. So we have here the text, the plain text of a SLAM script. We can see here the Singularity execution of an image. After that, we have to submit the job. The normal user will submit this job. This is a Kubernetes job, and here we can see the arguments of HPC connector, which basically are the variables are linked here between the config maps to these variables, and we have here we are indicating HPC connector that we want to print logs, and we configure this job to send a SIG-int signal to the container if the user cancels the job using Kubernetes. So this is the information about the job. We can see here how that we are submitting the job. Here the job is submitted, and now HPC connector is monitoring the job until the end. For finishing, we can see here that the job is finished. Then we are printing the logs. So this is a demonstration of our tool. So to conclude my presentation, HPC connector is an open source tool for integrate current your cloud infrastructure with an HPC backend without requiring any special privileging and in an easy way. HPC connector fulfills all the requirements identified in the previous slides. So users can submit or cancel the jobs using the HPC infrastructure. No special privileges are required, and this is very and easy extendable to another HPC backends and for use it with another job scheduler. The experiment that I show you demonstrates how the user runs an HPC connector in a Kubernetes cluster and that trigger a job to the Prometheus supercomputer in Poland. So this is all for me. We have 7 minutes for questions, so go ahead. Thank you for having me asked.
So thanks very much for your talk. Are there any questions?
Yep.
Hello, can you hear me?
Yes.
Okay, this is Tommaso Cucinotta from the Scuola Superiore Sant'Anna in Pisa. So about the integration with the operating system signaling infrastructure, you mentioned that you can stop the jobs that have been started by catching the Ctrl-C signal, the SIGINT signal. So I guess this is from the client/console where you are launching the job. So my question is, don't you normally need actually to run these jobs? I mean, probably these are long-running jobs. So you actually need to detach your console, your terminal from the job, you know, leave it running, maybe come back later after a few hours or perhaps a few days to double check whether it finished or if you want to stop it later. So in case you just, you know, sent out the job in a batch way, can you still catch it and stop it using this framework?
With this framework, the HPC connector will catch that signal. So if you press Ctrl-C, you send this signal, and the HPC connector can catch that signal. But I don't know if you are saying that.
Yeah, for example, if you launch your job, if you launch that with the no hang up because you just want to leave it running in the background, maybe you want to come up a few hours later or the day later. Do you have like a way to list the currently running jobs and you can kill selectively some of them, or do you have such an interface into this HPC connector framework?
HPC connector does not has a daemon. So HPC connector basically is like a mirror job. You are running in the HPC backend, and when the HPC backend is running, HPC connector is running. And if you have 3 or 4 HPC jobs, you have 3 or 4 instances of HPC connector running in 3 or 4 terminals.
Okay, thank you.
You're welcome.
Any more questions? Then one from me is, what if the job which is then running, let's say long-running job even, which is then running on the HPC side, it accepts in one or the other way. How do you rediscover state from your scheduler side? And if you cannot, what do you do short of rebooting nodes, this kind of thing?
If the job ID changes and we don't receive a notification of this change, the specific connector only says the job doesn't exist and stop. But we cannot find the job on the workload manager in the HPC infrastructure. That can be a future work.
Okay. Slurm has got a SQL database, by the way. Are there any other questions? We still have 2 minutes to go. Then a very last one to Sergio is, will you make the code, the Python code for this work available?
Yes, this is in GitLab, so I forget to put the link here, but I will put the link in the chat of this webinar now.
Okay, very good. Then passing on. Thank you again for the talk. So it's common to do this, so we cannot do this. This is a feature they still need to implement. Passing on to Tassos for the next talk. Thank you again, Sergio.
Thank you.
Thanks. So our next talk is a paper that we have promoted to Keynote about interference-aware orchestration on Kubernetes. Our next speaker is Achilleas Gemetopoulos from NTUA Greece. He's a PhD candidate. Achillea, can you hear us?
Yes, yes. Hello. Hello and good afternoon. Can you hear me?
Yes. Can you share your screen?
Okay, I will start the sharing and I will open my camera too.
Perfect, we can see you.
Okay.
And we can see your presentation. Great. So the floor is yours.
Thank you. Well, hello everyone, and good afternoon from Athens. I hope you're doing well. Unfortunately, due to those emergency circumstances, this presentation is virtual. So, my name is Achilles Zenetopoulos, and I'm an electrical and computer engineering graduate from National Technical University of Athens. I graduated last November, and I conducted my diploma thesis in microprocessors laboratory in National Technical University of Athens. In this presentation, we will discuss our thoughts about any possible intersection between HPC and cloud technologies like Kubernetes. Also, I will present to you our paper with title Interference-Aware Orchestration in Kubernetes. At this point, I would like to thank National Technical University of Athens and Microprocessors Laboratory for giving me the opportunity to contribute as far as I can in works like these. Also, it is an honor for me to be accepted and invited for an extended talk in the 15th workshop on virtualization in high-performance computing, hosted during the ISC High Performance 2020 event. And I hope this talk will be the reason for further discussion regarding virtualization in high-performance computing. So let me first introduce our team working in National Technical University of Athens in Microprocessors and Digital Systems Laboratory. The team is consisted of many members, but in this work contributed the PhD student Demosthenis Massouros, the assistant professor in Harokopio University of Athens, Sotirios Xidis, and the professor in National Technical University of Athens, Dimitrios Soudris. So this is the outline of this presentation. We will start talking about the Kubernetes timeline and the research we conducted here in DUA regarding Kubernetes. Then we will discuss any possible synergy between high-performance computing and Kubernetes. And finally, I will present the interference, our work with title Interference-Aware Orchestration in Kubernetes. First of all, I would like to talk briefly about some Kubernetes highlights. In 2003, Google introduced the Borg system, driven by the needs of different teams inside Google. After that, trying to build Borg from the ground up to have a more principled architecture, Omega was born. In Omega, Borg's functionality has been broken into separate components. Later, by the time Google had already started selling public cloud infrastructure, Kubernetes was born. Kubernetes, in contrast to the previous projects, was open sourced. And this was the time when a new whole ecosystem was born. In fact, many technology leaders like IBM, Red Hat, and Docker had been early joiners in this ecosystem. As the years passed, Kubernetes started growing rapidly. It is now managed by the Cloud Native Computing Foundation. It has seen many improvements, and more features were added. The ecosystem and the contributors community were becoming more and more popular. Also, plenty of supplementary projects such as Helm, the package manager, Istio, a service mesh, and Kubeflow for machine learning have come up. Today, Kubernetes has become the de facto solution for cloud infrastructure across multiple organizations. Many providers like Google, Amazon Web Services, Microsoft Azure, IBM, and Red Hat have developed their own managed Kubernetes services. It is remarkable to point there that Kubernetes is second to Linux as the most popular open source project. Our team has been studying Kubernetes since 2015. At this time, the ECLI project started. Through this project, Konstantina Demosthenis had researched the usage of accelerators over Kubernetes. These are some indicative works presented in this slide. Also, Demosthenis in 2019 published his work with title Runtime System Predictability, Leveraging LSTM Neural Networks. For anyone who may be interested to learn more about this work, you can also find this in this year's ISC High Performance event under PhD Forum posters section on the past Monday's program. Currently, our team is working on Evolve, an ongoing European Horizon 2020 project. Let's spend a few minutes to talk about our contribution in those two projects. EGLI is a European Horizon 2020 project. EGLI aims to promote data-driven research across Europe and to serve as an enabler technology platform, enabling business growth in the field of big data analytics for healthcare. In EGLI, our team built the infrastructure where an acceleration and the conventional cluster coexisted under a federated Kubernetes system, which still remains an open challenge for the community. In 2016, when Project EGLI started, FPGA and GPU virtualization was a primitive field. Our team managed to virtualize GPUs and FPGAs in order to be accessible and used by Kubernetes. Today, there are multiple device plugins provided, developed by NVIDIA, Xilinx, and other organizations. Additionally, in this project, as I also said before, a federated Kubernetes over different subclusters was implemented. Currently, we are working on Evolve. Our goal is to build an infrastructure that will integrate HPC, cloud, and big data worlds, able to efficiently serve different use cases providers' needs. Those use cases will include agri-production, maritime surveillance, satellite images, automotive services, and more. In order to achieve such integrations, we need to apply HPC and big data features into Kubernetes. Starting from end-to-end workflows, we need to create the infrastructure that will be able to translate the HPC feature, this specific HPC feature, into Kubernetes. On the other hand, we are working in a heterogeneous cluster. Except for CPUs, and the orchestrator needs to be aware of GPU and FPGA nodes and leverage them when needed. At the same time, use case providers, developers, and data scientists need to be able to run their models without worrying about underlying infrastructure and hardware specifications. We are trying to address those requirements by implementing storage and topology-aware scheduling, and by simplifying the execution of workflows by automating the whole deployment process, starting from the source code up to containerized multi-step deployment. I'm not sure if you know where was that picture taken. It is from the city that will host HiPeak 2021, Budapest. You may wonder, why is that picture here? Well, Budapest was initially split into 3 settlements: Pest, Buda, and Obuda. Buda and Pest were separate, independent cities. Since the bridge was built, the 2 cities united under one with the name Budapest. Someone could think that those 2 cities may be cloud computing and HPC. They are 2 independent worlds that are thriving at its own territory. However, no one knows the outcome of a bridge connecting them. That bridge would let them continue to exist as individuals, but would also enable their synergy when needed. So, could Kubernetes be that bridge? Now let's discuss about HPC and Kubernetes worlds. As HPC Wire claims and Forrester predicts, cloud and high-performance computing are getting closer every year. In 2020, HPC in public cloud will grow up to 40%. Needs for analytics, bioinformatics, and AI have led to that migration. Kubernetes could be the bridge connecting these those two words as IBM through HPC wire claims. So indeed, HPC step-by-step migration to the cloud is a trend. There are multiple works trying to provide a solution that integrates HPC and Kubernetes. In industry, IBM and Google have already started providing ready-to-use tools. On the other side, there are open source projects and published works proposing such integration. So, the HPC workload managers are tuned for speed, throughput, and scalability. Slurm is an open source, fault-tolerant, and highly scalable cluster management and job scheduling system. The preferred way to use a supercomputer is through submitting batch jobs to a scheduler system which governs access to the compute nodes. The basic goal is to maximize the utilization of the system. Slurm key functions are resource allocation to the users and contention of resources arbitration by managing a queue of pending workloads. It also handles sets of possible parallel tasks within a job. IBM Spectrum LSF also key functions are the following. The management of SLAs between different users, groups, and projects. The allocation of resources based on hierarchical sharing policies, and the resource reservation for workflows that run periodically. Kubernetes, on the other hand, is built for containerized microservice applications from the bottom up, as well as load balancing and self-healing. Its goal is to ensure that any incoming workload will run in the most viable node. Kubernetes and HPC workload managers intersect in areas such as data analytics and AI. A deep learning environment might use an HPC scheduler for model training because of superior GPU-aware scheduling and workflow automation features. On the other side, it would use Kubernetes to deploy trained models for scalable inference in the cloud. HPC and Kubernetes, by definition, are two different worlds. Starting from the kind of workloads, HPC environments usually host run-to-completion jobs. Kubernetes' purpose of creation was to host continuously running jobs, like services. The deployment models also differ. In HPC, there are binaries described in the workflow. In Kubernetes, there are containers inside pods. Application containerization ensures portability in contrast to HPC, where system dependencies can make any kind of migration hard and time-consuming. Additionally, in HPC, MPI jobs and multi-step workflows are requirements that should be also addressed. In Kubernetes, there are mostly running cloud-native microservices communicating through an internal virtualized network. Finally, the features between the two of them differ as well. HPC requires and addresses resources reservations, topology-aware, and backfill scheduling. On the other side, Kubernetes focuses mostly on scalability and self-healing of the running application, ensuring redundancy. Management operations like scaling deployment are much simpler to implement and execute in Kubernetes. As HPC wire states, what Kubernetes lacks at this time is a proper high-throughput batch job queuing system with a sophisticated rule system for managing resource allocations. However, they both have a common ground that could act as an enabler for the convergence, the virtualization technology. The usefulness of containers are one thing HPC and Kubernetes agree. In Kubernetes, microservices architectures use minimalistic containers for speed and modularity. However, HPC users are more interested in encapsulation and portability. While HPC applications involve multiple libraries and complex dependencies, HPC users prefer to stuff everything into a container. And as a result, those containers are usually large. An example of the necessity of this coexistence is a research program in Barcelona Supercomputing Center. There, researchers are trying to simulate the human heart in their HPC cluster. However, when this tool will be needed to scale so as to run multiple simulations at the same time, a cloud migration will be needed. They are already trying to use cloud technologies, and as Alfonso Santiago claimed in the new stack, they are planning to use Kubernetes for scalability and redundancy. Another possible use cases are any emerging situations. For example, in cases where global medical issues, such as COVID-19, occur, where the computational demands for genomics and bioinformatics radically increase. In such cases, the existing HPC infrastructure may not be enough for solving the problems quickly. However, if HPC environment is portable enough and the cloud able to address HPC workload needs, those two worlds could unite against such problems that need to be solved as soon as possible at any cost. So what factors or actions can be the enablers towards this direction? Well, one solution would be to have separate infrastructures, the Kubernetes managed and the HPC managed. Another would be to containerize the HPC applications and configure the existing workload managers in order to orchestrate them. A third approach would be to use the Kubernetes scheduler for every kind of workload. Finally, there could be the coexistence of two or more Kubernetes integrated schedulers, each one serving special needs. In this case, a highly configured Kubernetes cluster could govern both cloud and HPC infrastructures. Next, we will talk about our work with title interference-aware orchestration in Kubernetes. Okay, let's open this discussion talking about the cloud growth nowadays. Lately, cloud computing has seen an explosive growth. Cloud data centers offering greater agility and cost optimization are now addressing both business and consumer needs. It is simpler than ever to buy virtual machines in the cloud with the hardware of your needs. According to Cisco, hyperscale data centers which benefit from virtualization and cloud computing will quintuple their traffic by 2021. As we know, today this high density of workloads deployed and executed in the cloud may be a problem. This multi-tenancy could also be observed in HPC, where different partners or workloads are using resources at the same time. However, those workloads, even isolated in containers, can interfere with each other. As a result, while some resources of the system are shared, interference phenomena may cause significant performance degradation. First of all, academia has identified such issues, and there are multiple works trying to prevent interference phenomena by application profiling and affinity. However, such approaches are not widely adopted by industry. Kubernetes, for example, relies on typical metrics for its scheduling decisions. Here on the right, there is a quotation from Burns, which claims back in 2016 that Kubernetes lacks of low-level resources interference awareness. At this point, we will focus on a major Kubernetes component, the scheduler. Kubernetes scheduler follows a two-level approach. In the first level, it filters out any nodes that are not feasible to host the incoming applications. This may be because of memory pressure or CPU pressure or disk pressure. Then, by applying different priority functions, it selects the most viable one among the remaining nodes. So, what we did was, by utilizing iBench, a micro benchmark suite, we were able to stress different low-level resources. We used 2 virtual machines. We scheduled CPU-intensive workloads in the first and last-level cache-intensive workloads in the second. Then, we assigned Kubernetes the task to schedule the scikit application. Kubernetes, taking into consideration the virtual CPU usage, favored every time the last-level cache-stressed node. However, the interference caused by the cache misses to the scikit-learn application resulted to a 0.68 times slower execution time, as you can see in the figure. That fact had been a motivation for us to dive deeper and research what would improve those results. So the scheduler is currently unaware of shared resources interference, and this contributes to application performance degradation. Our experimental setup is consistent of the server referred to as H1 from host 1. H1 is consisted of 2 sockets with 24 logical cores per socket. On top of host 1, we deployed 5 virtual machines. These virtual machines consist the nodes in the Kubernetes cluster. The machine Kube00 is serving as the master, while the rest of them are the worker nodes. We print the cores of those machines into separate sockets of the server in a way that all the cores of each virtual machine belong to the same underlying socket. We use Intel performance counter monitoring in order to extract useful low-level metrics. Those metrics were extracted from the server and were shared to Kubernetes virtual machines via a network file system. Currently, we are in the process of redesigning the system using an external time series database for metrics storing. Our target applications belong to 3 classes: scikit-learn, Spec 2006, and Cloud Suite, covering different areas of applications like machine learning, scientific, and cloud native, respectively. Next, we applied different levels of stress on various low-level resources, and we measured the performance of the aforementioned target workloads. It is important to say here that we ran those tests in the same socket of host 1, and all the applications were deployed as pods, which is the minimum Kubernetes unit. The figures depict the relative or normalized performance of all our target workloads when co-scheduled with different number of specific resource stressing iBench micro-benchmarks. The solid line in each plot shows the estimate of central tendency of the relative performance, while the surrounding area illustrates the confidence interval for that estimate. From these plots, we can discuss the trend for each resource. For CPU, according to our experiments, the performance is vastly degraded when no other cores are available. For the level 2 cache case, we scheduled a level 2 cache-intensive iBench application in the same hardware thread as the target application, using a different logical CPU. The delays at this level can be impactful as well, but they don't seem to get any worse while the load increases. Regarding the level 3 cache stress, we scheduled level 3 cache intensive applications in one virtual machine and the target application in another, both belonging to the same underlying socket. We observed a great degradation in the performance as the level of stress increases. Finally, following the same setup as level 3 cache, we applied memory bandwidth stress. The impact in performance is huge again. Such delays can be explained by the fact that last level cache misses require data to be fetched from the off-chip memory. Memory reads and writes are the request for data on behalf of last level cache misses, as well as DRAM traffic due to prefetching. A simple metaphor that comes to my mind is the following. Last level cache is the border between the cores and the main memory. Any operation taking place beyond that border generates additional delays in higher order of magnitude. Following the previous metaphor, memory bandwidth would represent the width of the pipe connecting operations within and beyond that border. As last level cache misses increase, the number of operations that will take place in the memory side also increases. So if the ratio of such operations is higher than the one the memory bus can serve, memory contention occurs. At this point, we tried to correlate the delays in the application's execution time with the system state before the target application scheduling. In those radar charts, this correlation is depicted for different metrics such as level 3 cache misses, memory reads and writes, IPC, and C state. Regarding the C state, each CPU has several power modes, which are called C states. These states, starting from 0, which is the normal CPU mode, and the higher the number is, the higher the deeper into sleep mode the CPU goes. So C6 state is when the CPU is in idle mode. Regarding the chart, the figures, the wider the circle is, the most accurate is that metric in the application performance degradation. We present 3 different scenarios. On the right, we apply memory bandwidth and level 3 cache stress. And then we measure the execution time of the applications. While C0 state seems to achieve great results in those 2 cases, this is proved a coincidence. In mixed stressing scenarios where different low-level resources were stressed at the same time, even C0 state is not accurate enough. For that reason, we tried to compose an additional custom stress score, which we also plot. This metric is reads plus writes divided by the instructions per cycle. Since we identified that most of the delays were caused by interference in level 3 cache and memory bandwidth, by using the reads and writes, we were able to capture this kind of traffic. IPC also acts as an extra factor when the memory traffic is not able anymore to provide useful information in high stress cases. As you can see in the radar charts, this metric achieves great correlation with the target application execution time across different stressing scenarios. Similar to Kubernetes, we approach the node selection problem with staged filtering. After extracting all the required metrics, we select the socket in the first level and the virtual machine or node in the second. Here you can see the Kubernetes architecture. In our work, we dived into the scheduler. So this is the part when we applied some changes, the scoring functions. Our problem is modeled using different sockets. As you can see in the figure, each socket S is identified by the server it belongs and is characterized by a couple of the last 20 seconds weighted average of several low-level metrics. This weighted average is calculated giving more importance or weight in the recent metrics. For example, in 50 metric extractions over the last 20 seconds, the latest one will be multiplied by 50, while the earliest one by 1. More specifically, we use C6 state of processor. This metric describes the percentage of the cores that are in idle state. We also use IPC, reads and writes. On the other hand, applications are modeled as a tuple of their average extracted metrics. Those metrics definition can take place in the first time of the application execution. As we also explained earlier, the first level of filtering in our approach is the socket selection. Since level 3 cache and memory bandwidth, two critical resources for the performance of the system, as we explained earlier, are shared between the cores of the socket. So we need to balance the load horizontally across the different sockets of the system. Using the aforementioned custom scoring function and considering core availability at the same time, we select a socket. We only divide our custom metric, presented before, by C6 state percentage in cases that less than 1 core per socket is available. Secondly, after selecting the socket, we need to select the virtual machine or node. Our only criteria for this selection is the core availability for each candidate node. In this stage, we examine only the nodes whose cores belong to the selected socket from the previous stage. In order to evaluate our logic, we first stressed one of the two sockets of server H1 using IBENs. After that, we scheduled several workloads in random intervals, letting the scheduler decide where to schedule them across the whole system. In this figure, after applying level 3 cache stressing, we plotted the difference between the monitored level 3 cache misses during the target application's execution. As you can see, the blue area, which depicts the imbalance during the native Kubernetes scheduler decisions, is greater. That means that while the one socket of the system was highly loaded in that specific resource, the other had that resource available. That fact led to performance degradation of applications scheduled in that overstressed socket. On the other side, our custom scheduler achieved a more fair load balancing. Applications were equally placed between the two sockets, depending on the score our custom metric assigned to them in first place. In this figure is plotted the imbalance in the instructions per cycle. Again, the system sockets during the Kubernetes default scheduling are imbalanced. While the first socket has high frequency, the other has none. Again, in cases that the overloaded socket reaches the system limits, the second one remains unexploited. Finally, we also plot the difference in C6 state percentage. This time, the difference between the plotted areas is even bigger. That means that our proposed scheduler managed to balance the core utilization between the two sockets of the underlying system much better. Next, we wanted to measure the performance of the deployed workloads when compared with Kubernetes. As performance, we define the isolated execution time of the application divided by its actual latency in runtime. In this experiment, we scheduled different amount of workloads deployed in random intervals. We conducted this experiment using both Kubernetes default scheduler as well as our proposed approach. In this figure, we plot the distribution of the scheduled application's normalized performance. The higher the value, the greater the performance of the application is. As you can see, our scheduler results illustrated with green, have a more stable and as a result a more predictable performance. This claim can also be verified by the fact that the standard deviation is by 11.57 smaller on average. At the same time, the median of the distribution, which is illustrated with the little dot inside the figure, in our proposed approach is by 20% higher on average. So, in this work, we discussed the need of data centers to tackle multi-tenancy and co-location of workloads. Kubernetes Scheduler also uses typical metrics for its scheduling decision, and there seems to be much room for improvement. We also proposed a custom metric that seems to be able to depict the system state. After that, we designed a scheduler integrated with Kubernetes that uses the metric, and we achieved encouraging results that urge us to work further towards this direction. So, some possible next steps are to improve the node selection model, taking also into consideration HPC workloads. Also, we could expand the scheduling decision, leveraging core level metrics. This way, we would be able to avoid lower level of cache interference as well, like level 1 and level 2. Another idea would be to take into consideration heterogeneity as well in systems, in diverse systems like GPUs and FPGAs, containing GPUs and FPGAs. Our current work aims to a closer integration of our solution with Kubernetes in order to be used as an additional scheduler in Evolve's advanced computing platform. So thank you, and I will be happy to answer any questions you may have.
Thanks, Achillea, for the talk. It was very interesting. Are there any questions? Attendees, I just say that in case you want it online, attendees can post questions through the Q&A feature. All the panelists can just unmute themselves and ask.
Hello, can you hear me?
Yes, yes.
I have actually a quick question. So the problem I see in trying to get the impact of the memory behavior of the application is that in presence of collocation of workloads on the same cache segments, the memory, actually the cache miss ratio could change significantly from when an application is benchmarked in isolation versus when it is collocated with something else. So, I mean, an application may not get into kind of cache thrashing problems, you know, when it has all the cache available, but when it is collocated, it might get into that problem. So I'm not sure if, do you think you have, like, say, conclusive results here, or maybe the problem is actually more complex than it seems?
Okay, that's a great question. Actually, the impact the interference has in different benchmarks depends on the kind of benchmarks. For example, there exist benchmarks that depend heavily on the cache and data transactions with a memory. However, in this slide, we didn't pre-schedule events stressing before scheduling our workloads. So there is no previous stress. However, the amount of workloads is big enough indeed, but there was not artificial stress induced in those experiments. I don't know if I answered your question.
Yeah. So the fact is that you just know what happens once you are observing applications collocate in some way, but you don't have a means for assessing. I mean, I understand you can benchmark offline things in many different combinations, but in a real settings, you just know what you are observing about your workload, right? You don't have any possibility to make any preliminary benchmarking, profiling, checking, what is the collocation interference. So the doubt is, can you spot, I mean, can you do something on the fly in real time while the applications are running and detect, this need for replacing, displacing applications while they are running, but of course, without any need for doing a comprehensive set of profiling benchmarking action?
Okay, the only thing that the current system needs to be profiled is the average target applications metrics. So this could also happen in the first time of its execution. For example, we can extract the core metrics using PCM, Intel Performance Counter Monitoring. And by extracting the metrics of the core, this application was first scheduled, we can take the average and use it for the next runs of this application. So when an application is used for the first time, yes, it will not be placed in the most efficient way. However, regarding the benchmarking, yes, we did the experiments in a certain system, but we are currently trying to apply heterogeneity in the decision making. So I believe that we will be able to take decisions regarding different systems and residing under a Kubernetes cluster, not just one server.
Okay, thank you. By the way, very interesting work.
Thank you very much.
Okay, are there any other questions? I actually have one myself. I'm wondering, I think that you mentioned about not having any tests about heterogeneity or GPUs or FPGAs, that it's part of your future work. I was wondering if you have an estimate of how this will affect the scheduling scheme.
Yes. Regarding the heterogeneity, I have already conducted some experiments, but not for GPUs and FPGAs, just for different CPU versions of different servers. I believe those experiments and this model needs to be improved. But regarding the GPU and FPGAs, I'm not sure how close is how soon such an integration would be.
Yes, because I suspect the challenging part is to integrate the increased latency that there is between spawning a job in the CPU and on the FPGA or the accelerator. There's a huge difference there.
Yes, I believe that this is a work that should be started from the ground up, and I don't know how close is with the current one. But in any case, we will work towards this direction in order to make Kubernetes more topology aware, and who knows, maybe take decisions regarding the scheduling in such an heterogeneous cluster. with GPUs and FPGAs. But I believe that that will need a more complex model, maybe applying machine learning for that outcome.
Sure. Okay. That's it.
And I'm sorry, and a lot of experiments as well.
Yes. Okay. Are there any other questions? So there is a question. The project collects data using an Intel utility. Is there a technique to make this framework work with other CPUs such as AMD EPICs?
Well, I think that recently Prometheus also can extract such low-level metrics very recently. So I'm not sure if Prometheus can extract those metrics from other kind of processors too, because as it is, Prometheus is an open source project, many of its plugins are contributed by organizations. So I believe there are many chances that there is a plugin designed for other processors like AMD for Prometheus. Okay, I suspect Prometheus is a higher level tool. So since it's yes. So yeah. Yes. That is what I also we also thought until a few days ago, where a partner in the project discussed about Prometheus and low-level metrics. Honestly, I haven't done any research. I don't know what low-level metrics Prometheus can provide, but I think that maybe it will lead towards this direction. Okay, sure. Thanks. If there are no more questions, we have something less than a quarter of an hour until our next scheduled talk. Maybe we could take a break, short break, and resume 2 or 3 minutes to 7. Thank you very much. Thanks.
Okay, I think we're ready to resume. Our next talk is a lightning talk. It's about scaling Kubernetes for high throughput computing with Armada. The speakers are James Poole and
Jan Kaspar.
Jan, yes, I'm sorry about that. And Jan Kaspar from G Research. James is the manager of the compute platform engineering team at G Research, and Jan is a developer working on the Armada project. Whenever you're ready, you can share your screen, and the floor is yours, guys.
Okay, thank you very much. Jan, if you're there, could you share your screen? There we go. Okay, I take it you can hear me?
Yes.
Brilliant.
Yeah.
Okay. All right, well, we'll get started then. So yeah, thank you for coming and attending this conference, everybody. Hope you're all well in your various states of lockdown around the world. Just a reminder, please submit any questions you have in the Q&A and we'll do our best to answer them. Want this to be quite interactive. We're going to do a brief talk and then a demo. So yeah, so today myself and my colleague Jan Kaspar are going to talk about how we're scaling Kubernetes inside our organization to run large amounts of containerized batch jobs using a new open source tool we're building called Armada. So in terms of introductions for me, my name's Jamie Poole and I'm the manager of a team called Compute Platform Engineering. We're responsible for building and running our Kubernetes infrastructure in G Research, as well as the associated tooling around it. Jan is a senior engineer in the team and the principal architect of the Armada solution. So firstly, I'm going to talk very briefly about G Research and what we do, and then I'll hand over to Jan to give an overview of the Armada solution itself. And hopefully, demo gods willing, we'll do a live demo in AWS, and we can take questions during that as well. So next slide, please, Jan. Thank you. Okay, so quick background about G Research. We're a fintech company based in London, and we build and run a large research platform that allows our teams of quantitative researchers to apply scientific techniques to find patterns in large, noisy, real-world data sets. We've been going since the early 2000s, and we've grown quite significantly in that time. We're currently undergoing a migration of software from a legacy Windows environment, and this includes a large on-prem batch compute infrastructure, historically run using HT Condor. We felt that if we could bring the Condor-like benefits of queuing and fair share to Kubernetes, then we could also benefit from all of the best-of-breed container management and scheduling that this brings. So that's enough from me. I'll hand over to Jan now to talk about what we're doing specifically with Armada. And just a reminder again, if you have any questions, please just pop them into the Q&A and we'll be happy to address those. Okay, thanks. Over to you, Jan.
Yeah, thank you, Jamie. Hi, everyone. So basically, as Jamie said, we are migrating a lot of our workloads to Linux, and we use Kubernetes successfully for services. And about in the middle of last year, we started experimenting if we could run HTC jobs on Kubernetes as well, if we could stop using Condor, which we use on Windows, and move some of the jobs to Kubernetes, because that would allow us to use the same infrastructure and would simplify a lot of overhead for us for managing two different platforms. We quickly found out that if we want to use Kubernetes for a lot of jobs, it's quite problematic, because Kubernetes itself is all built around basically getting desired state. And if you throw an enormous amount of jobs in one Kubernetes cluster, it will get slower and it won't be that performant anymore. And also there are some limits in having one cluster. So we started building Armada, which is basically a queuing system for multiple Kubernetes cluster. It maintains queues of jobs for users, and it can send jobs to different Kubernetes cluster just when there is resource available. So we take most of the jobs which would otherwise be in the cluster and we would be overhead for Kubernetes, we take it out. But at the same time, we reuse all the other components of the Kubernetes. So we use Kubernetes scheduler. We use basically the whole Kubernetes, whole vanilla Kubernetes, but we built one component in front of it. and why we really want multiple clusters. So we found out that even running Kubernetes clusters has a limit where the documentation say is 5,000 nodes, but in real world is a little bit less, or we found out that 1,000 nodes is fine, but then it starts to be problematic, and you need to do a lot of tuning to make large clusters. So instead of that, we make multiple clusters. We firstly examine some of the existing schedulers. There are different schedulers you can plug in into Kubernetes, and we are actually thinking the Armada can be used with different scheduler. It's not competition. It supplements it. But there are some schedulers which actually focus on batch computing, like Cubase and Volcano, but they are all focused on just managing one cluster. And we want to scale more. We want to be able to let's say queue million jobs, which just kills one Kubernetes cluster, at least unless you do real lot of tuning and adjustment to Kubernetes. And we don't want to do that. We want to just use Kubernetes as it is. And another thing which is not provided by Kubernetes, which we wanted, is to be able to enforce fair share over time, because in classic Kubernetes setup, you have quotas on namespaces and you can set limits which are fixed. But in HPC world, you might want to allow some user to use half of your compute in the whole company for a limited amount of time, but then you want to penalize this user later and allow others to use the same compute. So instead of enforcing limits just now as it's done in Kubernetes, we have built priority concepts similar to what HD Condor have when users has priority, which gets higher with how much resource you use, and then if you have higher number, you are less likely to get your job scheduled. So over the time, it's much more fair than it would be with just enforcing limit just in time. So how is Armada solution structured? It's quite simple. To each Kubernetes cluster we want to use, we deploy a component called Armada Executor. This component communicates with API server in Kubernetes clusters and observe how much resource there is available and request jobs to be run from Armada server. These jobs are actually leased, which means that the executor needs to renew the leases and report back progress if in unlikely event the cluster was completely destroyed or something wrong happened there, the job leases will expire and different cluster can start running them again. Armada server keeps all the information about job queues in jobs database, and we have also separate database for events which records everything would happen, so we can then trace where different job starts and ended, and users can actually request this information. This pool-based model has a big advantage because we can really easily plug in new clusters or remove clusters in the live system, and it allows us to do quick and easy upgrade and so on. So from user perspective, Armada has three concepts. We have a queues, which is basically an entity which receives fair share of resource over time. It can be either user or project, and users of the system submit jobs to the queue. Then we obviously have jobs, which is just unit of work. It's basically pod specification with a little bit of extra information. And then we have job set, which is logical grouping of jobs, because most of our jobs are actually collection of jobs, and users need to observe progress of collections of jobs together. We provide some command line utilities which are quite similar to what you are used with kubectl. We have Armada CTL, which allows you to submit jobs, and the jobs are specified in the YAML files similarly as in other Kubernetes resources. And we basically use the Kubernetes pod specification, so you can anyone who understands Kubernetes will be able to submit to use Armada without much learning curve. And now I will go to the demo. I just started before the demo 5 Kubernetes clusters in AWS. Each has 99 worker nodes and 3 nodes for control plane. And I submitted some workloads to them using our load tester tool, and we can observe how they will behave. So on the screen, I have progress of these jobs. I can observe how what's happening in Armada. So these are my queues. In the beginning, I submitted 60,000 jobs in 5 different queues, and underneath you can see 5 different clusters: the CPU, memory, usage, and number of pods in different states. And you can see that each cluster receive approximately similar amounts of jobs from different queues, except this green one, which is user which has Alice has higher priority, so her jobs actually they almost finished now. And what I wanted to show now is if I submit some really important user jobs, you'll see that this user will overtake almost all of the compute, and his jobs will finish really fast. So let me just run similar one, so I can actually show that here we go. So this important user has different queue priority factor, which means that it's basically multiplier which modifies his priority, so he will be much more preferred. And so his jobs are being queued here, and we will soon see that he will get most of the available resources in the system. Yeah, I can just show the jobs I'm running is really just CPU stress tester with random time around 2 minutes. And then now you can see that this user thread is overtaking most of the resource.
It's probably worth noting that, so we're now actually starting to run this in production. So we've had Armada in production at our organization probably for about 3 months now. The production environment is still relatively small, so we've got something like 4 executive clusters with sort of order of, I think, about 10 nodes each, something like that. But yes, we've got a much larger staging environment where we're still doing lots of performance testing, and we're just sort of starting to accept more jobs as more workload within our organization get migrated over. This Michael, oh yeah, it's gone now. This demo only shows CPUs, so this is running in AWS, and I think this demo is expensive enough actually. But if we also support GPUs or anything Kubernetes supports really. So within our organization, we have a small GPU. Well, we use GPUs a lot actually, but within Kubernetes, we now start to have a bit of a small GPU estate. So that's quite interesting as well. I think, yeah, Jan, you can see now that this high priority user's job's pretty much consuming the whole farm. This demo is relatively artificial in the sense that all of these jobs are pretty quick. They're just stress testing CPU for some relatively small number of seconds. I think in the real world, our jobs range from anything to small number of seconds through to, well, some take days actually. But yes, normally the order of hours, I would say.
Can you see jobs that impact others in a sense of shared environment, I/O weights, something like this?
Noisy neighbor type thing.
Noisy neighbor, yes.
Yeah, we've done a bit of testing around that actually. Yeah, Jan, have you noticed anything specifically around that? I guess CPU and that kind of thing?
And nothing surprising. We recently have done some tests with different CPU affinity. So Kubernetes has some support for basically fixing CPU affinity, which can actually improve some things. But actually found a bug in it, which I think we just reported, and we are trying to get it fixed. But essentially, if you fix the CPU, you can get much better performance. But that's just basically the same thing you can observe in, for example, any other HPC shelling system like HD Condor or anything like that. We have also observed something which might be quite specific to our environment when we had some problems with file shares where certain jobs mounted a lot of similar file shares on one node.
Yeah, so we have lots of integrations back with Windows because of the legacy of most of the estate, running on Windows historically. So we're big users of Kerberos for authentication, and as anyone who's ever tried to sort of mount Windows file shares from Linux knows, it can be, with Kerberos specifically, it can be quite tricky. But we do seem to have it relatively stable now, which is good. Any other questions? I mean, we're happy to sort of poke this demo a bit more or explain more what you're seeing here. I mean, I stare at this dashboard all day, so I'm kind of used to it. But if anyone else wants to know what's going on, please feel free. No stupid questions. I mean, sorry, there's no such thing as a stupid question, not not the opposite. Nothing in the Q&A. I think we've got stunned silence.
I guess this is in the proprietary world, right? It looks pretty good, that is it.
What you mean, the software, or
yep.
No, so well, Armada itself is open source.
Okay.
We've got it open source from the beginning, so it's out on GitHub. I think at the end of this we'll put up the last page, which has
very good, very good. Yes, yep.
The GitHub repo. So please do try it. All you're looking at there is just Grafana, and in terms of those sorts of metrics, we use we're really keen. We wanted to use as much built-in vanilla Kubernetes as possible. We didn't want to have to be sort of doing too much bespoke Kubernetes-ness, I suppose. So all of this is just using Prometheus data, which is using like Prometheus, kubestate metrics, all sort of open source tools in Kubernetes. So you can do all this for free, apart from the fact with this particular demo, you have to pay AWS quite a lot of money to run it, probably. But for us, I mean, all of our environment is on-prem for now. We may end up doing some stuff in public cloud as well, but if that's the case too, that will also help us, because this system will also help us because this allows us to add clusters arbitrarily. So we could even sort of burst out into AWS or GKE or whatever, so long as it's just some variant of Kubernetes, it should all be fine. And from the on-prem stuff, we're running on OpenStack.
Any other question, anyone?
Take that as a no if we have no other questions. Michael, you're the host. Do you want us to do any more, or should we wrap up?
I think we're fine. I think we're fine.
Okay, thank you very much for listening. And yeah, check out Armada on GitHub. It's open source. There is actually a quick start guide where you can very quickly get 2 clusters using kind running with all the Armada setup, and obligatory as we are G research and we are hiring. If anyone is interested in our project, you could be working on Armada if you'd like to.
That's it. Brilliant. Okay, well, yeah. Thanks very much for listening, guys.
Thank you.
Okay, thanks very much, guys. I guess we have about 10 minutes until the next talk. I would suggest we keep the schedule in case someone wants to join just for the specific talk. So let me just share my screen.
Okay, in, what is it, 6 minutes from now, we'll go on, whereby our next talk will be by David on a pipeline in bioinformatics. So experiences from using Kubernetes, cloud-based Kubernetes in a biopipeline at the EBI. David, I believe you're here. I unmute you now. Ask to unmute. You can already join if you want to. No. Well, still 5 minutes to go, so I'll introduce David ahead of time with his bio. So David Yuan is a cloud bioinformatics application architect working at the European Bioinformatics Institute, EBI, European Molecular Biology Laboratory, the EMBL. He is driving cloud adoption onto both private cloud, in brackets OpenStack, and public clouds, in bracket all of it, the Google Cloud Platform, AWS, and Azure at EBI and in various EU projects. His research interest is the application of container orchestration for HPC batch processing in the cloud. So we're right on topic. David has a PhD in molecular biology and a BSc degree in software engineering. A good combination because molecular biologists tend not to have an easy time with some of those things. David, are you here by now?
Yes, I'm here.
Very good. We don't start early because as Tassos has mentioned, we do need to stay on the schema if anybody joins for this particular talk. But okay.
Okay, so you want me to start at 2:45 as the original schedule?
No, as we have scheduled, which is at at Eastern time at 2:30. So it's 3 more minutes to go for us.
Okay, sure. I'll do that.
If you want to, you can share your slides already.
All right, I'm going to do that.
Very good. We can see it. Yes.
All right. So you can see my presentation now.
Yes.
What about now? Is that right?
No. You might want to switch screens. This looks like you're on a different screen.
Okay. Okay, I'm going to do this then.
I saw EBI and Sanger. I'm sorry to say, if you want to talk about how not only the EBI but Sanger is handling cloud and containers, that would of course also be interesting. Yes. Yeah.
Okay, yeah, I'm going to talk a little bit about whatever I know about Sanger, but yeah, okay, I'll do that.
Yep. Okay, we have got 1 minute to go.
All right, I'm in the full screen mode.
Okay, countdown 40 seconds. Five seconds and you're good to go.
All
David,
right.
Yep.
Okay. Hi. Hi, everybody. Thank you for giving us this opportunity to report our investigation for applying the container orchestration for HPC processing in the clouds. This work is done by me. My name is David Yuan, and also my colleague, Dr. Tony Weldish. We are the Cloud Bioinformatics Application Architects in European Bioinformatics Institute. We're the second largest site of European molecular biology laboratory located in Cambridge, UK, which is, let me bring this pointer, which is this building in the middle. We are specialized in bioinformatics on the same campus in Kingston that also Sanger Institute is also on the same campus. These two institutes that we closely relate to each other, and we have close interactions with each other as well. As a matter of fact, we have a monthly cloud roundtable, so-called roundtable meetings, that we share the experiences and tell each other how stupid I was that last month, so we can learn from each other's mistakes and to get better in adopting the clouds. Tony and I, together with the rest of the team, we are responsible for driving the cloud adoption at EBI and also in various European Union projects. Bioinformatics pipelines make extensive use of HPC batch processing. The rapid growth of the data and also computing complexity imposes significant challenges. In our particular case, we have 27 petabytes of data, and also that the data is doubling every 2 years. So this is really troubling to us. And our pipelines tend to run for a very long time. And I'm talking about weeks to months, not days or hours. And also it routinely takes hundreds of steps. And also we also started experimenting with the machine learning. So the machine learning algorithms adding additional demand and making more resource intensive requests. So we have been using the HPC in the cloud solutions. And those existing solutions have some inherent overhead of creating and destroying the worker nodes on demand. And the pipelines have to be designed carefully to pack the jobs efficiently into VMs. But our end users don't always follow the best practices. So the solutions are tightly locked into the underlying cloud platform. So this makes the cloud agnostic deployment really difficult or nearly impossible. Kubernetes has become the de facto standard for container orchestration. A lot of speakers before me have discussed the various aspects of making use of or improving Kubernetes, as well as giving people a good overview of what Kubernetes are, or what Kubernetes is. So yeah, that really helps me that set the stage. I'm really grateful for that. It is the only real infrastructure as a service technology supported by all the major cloud providers. And so in theory, that the Kubernetes job framework can be used to create efficient bioinformatics pipelines. But in reality, nobody is going to do that because it's really demanding to rewrite everything with just the Kubernetes job framework. So we decided to find something better, and we are using Kubeflow to bridge the gap. As you can see on this slide, that we have been using or investigated a lot of HPC in the cloud solutions. On Google Cloud Platform, we use Slurm. On the Oracle Cloud Infrastructure, we use the custom Terraform scripts. And on Azure, we looked at the Cycle Cloud. And on AWS, we are currently investigating with Nextflow. As you can see that we are all over the map. That's not good for enterprise, for a large institution. And we desperately need a platform to unify all our cloud solutions. So the Kubeflow gives us this promise to unify our cloud stacks for batch processing, and also to improve the runtime efficiency with Kubernetes. And also that the Kubeflow, that's probably the most important thing to attract us, is that the Kubeflow that supports machine learning natively. I'm going to talk a bit more about that in the next few slides. In this study, we are reporting here that we tried 2 pipelines. One is machine learning pipeline. The other one is a non-machine learning pipeline. For this machine learning pipeline that we use Kubeflow, which is designed for machine learning. And this particular study we've done is with microscopic image classification with convolutional neural network. And as we all know that machine learning pipelines are memory hungry and GPU intensive, and also a lot of pipelines, machine learning pipelines require a lot of storages. In our particular case, image classification, it tends to use gigabytes to terabytes of the storage. And if it's a time series image classification, we're talking about petabytes of the data to have to go through the pipeline. And so we decided to investigate the possibility to use Kubeflow to switch the implementation, to move the implementation from laptop to OpenStack with CPU and to public clouds with GPU without changing the implementation. The reasons being that machine learning pipelines usually start with a quick prototype on the laptop. If the idea is promising, the researchers need to scale out and scale up with more and more data, with bigger and bigger model. But they usually run into problems that when they switch the environments, and they have to re-implement a major chunk of the implementation, which makes the scale up and the scale out difficult. So we're trying to reach this goal with Kubeflow. For the non-machine learning pipelines, we noticed that Kubeflow enhances the Kubernetes job framework. So that makes the creating a classic pipeline relatively easier. And in this particular study, we use a variant calling of the whole genome sequence from the 1000 Genomes project as an example. And this is a very typical classic genomic pipeline. And the pipeline uses two popular tools. One is called SAM tools. The other one is called Freebase. So I may refer to these names later on. So I just want to point out here. The goal for this study with the non-machine learning pipeline is that we want to port this pipeline freely among 3 different clouds: OpenStack, Google, and Amazon, to make sure we have the nice portability, cloud agnostic implementation, and also make sure that if we want to reduce the cost, and this is an option to us. Okay. Let's discuss the machine learning pipeline first. Kubeflow is a workflow platform designed to support machine learning natively. It runs on existing Kubernetes, as you can see here, and can keep the consistent behavior from laptop to OpenStack to public clouds. It has many built-in operators that to integrate a lot of popular machine learning tools. In fact, a lot of tools are bundled with the platform. You don't even have to install it by yourself. And it's tool for hyperparameter tuning, metadata tracking, and also supports the distributed training that could improve the model development and training and validation significantly. So that's a really good plus to us. A two-dimensional convolutional neural network is a well-known classifier or well-known algorithm to classify the macro daily objects such as cats and dogs, vehicles, flowers, etc. It's also showing that great potential in transfer learning to classify new images without extensive training. As we all know, you can also see here that the microscopic images that bioinformatics take care about have very different characteristics from those macro daily objects. So we have run this workflow on notebooks in the 3 different environments. And the result clearly demonstrates that with the training and the verification, it becomes significantly faster from a single machine to private cloud with CPU only and to public cloud with GPU. Without making any changes to the Python scripts in the notebooks, we are able to make use of more resources on the bigger and bigger environment. And that accelerated the training and the validation significantly. With much improved throughput, we were able to experiment with various things such as image augmentation, many different models, and with and without transfer learning. And hyperparameters, we were able to tune the hyperparameters quickly as well in the cloud, in both private cloud and public cloud, with different, and even with different GPU models. So to achieve these goals, we started by creating the cloud agnostic deployment, or mini-KF, Kubeflow. This is a virtual image running on macOS or Linux laptops. The reason we choose this instead of a native Kubeflow is that this has some good usability enhancements that gives researchers a good starting point, reduce their learning curve, as well as that get them ready to go to a little less friendly environment in the clouds. And then on both OpenStack environment as well as Google Cloud environment with GPU, we use cloud agnostic deployment. And if you're familiar with Kubeflow, and this deployment tends to refer to the kubectl and istl and DEX. And this is a multi-user and authentication enabled deployment. Has good potential to be production ready. Right now, they reached the version 1.0, and a lot of the components starts to be getting mature, and there's still beta and alpha components in this deployment. we created a Jupyter Notebook instances with the built-in images or the custom images with distributed training enabled. So the resource images was again microscopic images of the cardiomyocyte tissues from the image data repository, which we access them with the REST interfaces from this repository, as well as Python APIs from TensorFlow and Keras. I'm going to talk about it a little bit in details in the next slide. And later, we improve the data allocation and store the images that split into 4 tiles in a S3-like storage bucket. So the intermediate results and notebooks were stored on the persistent volumes, which can survive the notebook deletion and pod eviction. So with various enhancements, we built a highly portable and robust platform for machine learning based on Kubeflow. So the training time was significantly reduced from 37 seconds per epoch to 14 seconds on OpenStack, CPU only. If we use a really the cheapest GPU model, it reduced to 4 seconds per epoch. And I just want to remind everybody that during this process, we don't change anything in our implementation. And also the accuracy and the training loss was very different. We're starting from 70% being improved to, let me see, 85%. And with much stability, you can see the stability in the beginning, when naive model is not so good all over the place. And this is almost tracking with each other, the training and validation, almost tracking with each other in a line. Okay, let's switch gear to talk about the non-machine pipelines. This is a classic genomic workflow that the input comes from the 3 different sources. One is the human reference genome from a public FTP site, and another one is a query file that for one particular batch run. This is stored in a private S3 bucket. And then the actual genome sequence, the over 1,000 genome sequences, are stored in a private disk storage. And the output for long-term storage was sent back to a private S3 bucket. The whole system was monitored by Elasticsearch. The reason we picked Elasticsearch is that we want to have a consistent user interface, as well as the ability to monitor all the different clouds, OpenStack, Google Cloud Platform, as well as Amazon in a consistent manner. This pipeline that is implemented in Kubeflow, which is turned them into the Kubernetes pods. So the same tool takes the input and parse them, do a pre-processing, and store them into the persistent volume. And the sidecar, it's a custom utility pod that we created, and to take the input from the S3 storage and store it under the persistent volume, which makes the data ready for the Freebase to actually do the take the alignment to call the variant. And the result is temporarily cached onto another persistent volume for Freebase. And then with our own uploader, that is a custom utility pod that we created to send the result from the temporary cache to the S3 bucket. for the long-term storage. Oh, I forgot to emphasize one thing, that it is not scalable if we first try to download things, everything onto the local file system for freebase, and because the genomic sequences are generally big, and it's over 3 megabytes each. So we use something called OneData, which is a fuse-based utility to map the remote file securely onto the Kubernetes with as if it's a local file, as if the files are presented on the local system for the bioinformatics pipelines to consume. Due to the historical reasons, almost all the bioinformatics pipeline utilities assumes the input and output are on the local system or the shared file system that are accessible locally. And the output is also stored onto the either local file system or shared file systems that are accessible as if it's a POSIX file on the POSIX file systems. So which is why that we want to do the pre-processing, put into the persistent volume, and do the create a cache space that to store the temporary results and then upload it into the S3 buckets. Here's some more details of gaps and enhancements. That bioinformatics pipelines almost always assume the direct access to the POSIX-like file systems to read and write intermediate results on the shared storage. The only common persistent volume that we can use is NFS. But due to this limitation, as we all are aware that there are certain security limitations, performance, scalability, and to a certain extent, the data integrity issues. So we are very cautious. So we only use it to pass small amount of the intermediate data between tasks, and also use the other storage classes and access modes, for example, read, write on once for containers in the same pods as much as possible. It is not very convenient to forward node pods. So by default, that kubeflow creates the network interfaces to allow users to access it through node pods. So we enhanced it a little bit on the public interface. Sorry, on the public clouds, we changed it into the load balancer services. And on OpenStack right now, we're still using the node pod, but we have a plan to tend into the load balancers, so to make the environments very consistent. Most bioinformatics pipelines, I already talked about that, run due to historic reasons that run on the HPC clusters. So they always assume the POSIX-style file systems. And if we need a cloud agnostic batch processing, that we have to assume that the files are stored on the file servers as well as the object stores. We use OneData for a large amount of data. And fortunately for us, bioinformatics data tend to have smaller numbers of larger files, which is a very sweet spot for OneData. With caching and prefetching and streaming, this kind of things enabled, it can give us decent performance to fetch these data for the bioinformatics applications. So with those enhancements, we're able to run the handcrafted non-machine learning pipeline for classic variant calling on the platform. In particular, we created various utilities utility containers for cloud input and output. And the directed acyclic graph was expressed as a function calls in Python, and the Python scripts are compiled into the Argo manifest. Then the Argo manifest will call the underlying Kubernetes to execute jobs. And this platform is designed for machine learning, but as we were able to demonstrate, it's also good for any other pipelines. And here is a small run for this non-machine learning pipeline. In fact, just because of, in fact, although we call a small run, it took us 40 hours on OpenStack platform. So in Kubernetes, sorry, the Kubeflow is a new machine learning platform that enhanced the Kubernetes job framework. We have thoroughly investigated the opportunities and challenges to use it for bioinformatics. We have successfully run it with both machine learning pipeline and a non-machine learning pipeline. And with the fuse-based utility, we were able to fetching the remote bioinformatics pipelines just in time. We call it just-in-time data ingestion. And we also create the utility containers for cloud-specific input and output. And also that we use a single monitor for all the clusters in different clouds. This gives us a single pane of glass to monitor the behavior of all the clusters in different clouds at the same time. We scaled up the machine learning pipeline from laptop to private cloud to public cloud without changing the implementation in the notebooks. We also ported the non-machine learning pipelines among the OpenStack, Google Cloud Platform, as well as Amazon Cloud Services without changing the implementation of the pipeline as well. So looks like that we have identified an efficient platform to unify our cloud stack for batch processing. Here's a reference of all the major references we use for this study. That in particular, I want to thank the authors that shared their data in the image data repository that we were able to use for machine learning. And we are really grateful that Kubeflow community is creating a wonderful platform that for us to further develop our use cases on, and also as well as the OpenStack, as well as the one data that we were able to handle the large amount of data, transfer large amount of data between different clouds. Between the clouds and on-premise, as well as allow us to freely move the computing among the clouds. And the very last Git repository is our own implementation. Now it's open sourced, and we're hoping that they will share our experiences with the rest of with the community here that. To create the pipelines that in the cloud environments. Thank you for the time and for your attention.
Well, thanks very much, David, for the talk. It was an interesting presentation. We have little time for a couple of questions. So one of the questions is, instead of network file system for sharing, would a message queue application such as RabbitMQ or Apache Kafka also be suitable?
Okay, let me see. Oh. Yes and no. The message queue and Kafka tends to deal with a large amount of small data. If your use case is that's a perfect fit. For the bioinformatics pipelines, we tend to deal with a smaller number of the large files. And these files that and also the bioinformatics applications always assumes that we so-called, in our term, we so-called database are really the files, plain text files on the file system. So that using message MQ and Kafka to deal with that is not the best application to use those technologies in our particular case. But if your use case is like that, definitely yes, go for it.
Okay, and there's another question. In your opinion, what do you feel could be a potential bottleneck for the ML pipeline that you have described?
The bottleneck for this ML pipeline in our study, I would say that still the file input and output. There's a limitation on both kubeflow and also the one data. That the one data requires a root access in able to get itself initialized, because it's a fuse-based utility to get the client side initialized. But the kubeflow, the Jupyter Notebook pods does not allow the root privilege. From their own perspectives, they both have the reasonable justifications, but when we try to integrate them together, they don't work with each other. Right now, there are certain investigations going on in the Kubernetes community, in fact, Kubernetes storage community, and try to create the storage class to access the remote file systems and also access the S3 storage buckets, and then to present to the applications as if they are on the local file system. So if that work gets done, that's going to be really handy for the bioinformatics research, in particular in this case. We just need to mount the S3 buckets, for example, as a persistent volume to the Jupyter Notebooks instance. And in that case, the bottleneck would be removed. Because right now in this study, we still have to use the REST API to download the data and upload the data. That really impedes our ability to scale up to further the study to classify the time series images. Right now, we can only deal with the static images. Because of this reason.
Makes sense. Okay. So thanks very much for the talk and the Q&A. Our next speaker is Dr. Tommaso Cucinota from the Santa Ana School of Advanced Studies. It's an invited talk. He will be talking about model-based engineering of high-performance embedded applications on heterogeneous hardware with real-time and energy efficiency constraints. Tommaso, whenever you're ready.
Thanks very much for the introduction. Do you hear me well?
Yes, we can hear you.
Okay. So good evening or afternoon, everybody. As Thanos was saying, I'm from Scuola Superiore Sant'Anna. in Pisa from the Real-Time Systems Laboratory. And we do research on real-time systems, especially on the bottommost level of the software stack. So specifically at the operating system level and the kernel level, with a specialty on, we specialize in process scheduling for real-time workloads. Now, in this talk, I'm going to introduce you some of the work we are carrying out in the context of a European project called Ampere, as you can see from the logo, which is an acronym that stands for a model-driven development framework for highly parallel and energy-efficient computation supporting multi-criteria optimization. And this project, this European project, is being carried out in collaboration with all the partners you are seeing here in the slides, particularly the Barcelona Supercomputing Center that is coordinating actually the project. So we are a partner, along with other academic partners like ETH Zurich and Instituto Superiore di Ingegneria do Porto. And there's also industrial partners, as you can see, Bosch, Thales, Cisco, and Evidence. So first of all, a bit of motivations and introduction. So as you know, cyber physical systems are going towards higher and higher computational performance and reliability requirements. So there's a use of increasingly heterogeneous and interconnected platforms, which are very often mobile and battery operated in these systems. So as you can see in the picture, in the bottom right picture, it's not only about having multi-core systems, but the embedded system world is going really fetching some from some of the characteristics of high performance processing environments. So we are seeing non-symmetric multi-core architectures because that's driven mostly by energy efficiency reasons due to the battery operation, but not only. With, for example, big little or dynamic ARM architectures where you may have cores specializing in high performance workload as opposed to other cores specializing in energy efficiency. And you have other accelerators, of course, which are graphics processing unit and general purpose GPUs for accelerating graphics and also computations, as well as tensor processing unit when you want to accelerate specifically machine learning or AI computations. And also an increasingly interesting trend is the one to see more and more often FPGA accelerations. So the capability to have a little bit of programmable hardware, which can be available in a separate chip or in a system on a chip. So it's architectures like this are becoming increasingly frequent in embedded systems. And particularly, we can see this in a number of use cases, which are the traditional use cases of the embedded domain, particularly soft and hard real-time use cases, ranging from automotive, railway, and aerospace, where we have also the safety criticality, all the way down to robotics and gaming and multimedia, where we are landing onto soft real-time use cases, where missing a deadline doesn't cause a life loss, but it's just, a system that doesn't work well. So moving forward, what are the problems and challenges we are dealing with in this project? So the main issue is that under such a complex underlying hardware architecture, developing embedded applications is becoming really cumbersome. So it's not only about making an optimum usage of the underlying hardware parallelism and acceleration that is, as you know from the high performance domain, there's a lot of tools and frameworks and middleware that can be used from the high performance and parallel computing community, for example, OpenMP, MPI, and others. But it's just making really a good use of the underneath hardware, because on an embedded platform, we might have performance versus energy consumption trade-offs. So for example, we may want to, let's say, squeeze any possible bits of performance given some maximum energy consumption. We cannot go beyond otherwise the system doesn't work, or otherwise the fans start kicking in and making too much noise or whatever else. Or we may have really harsh real-time constraints because we may have this application that doesn't make computations, batch computations, to be ready in 1 hour or a few hours, or you know, the day after. But we need computations in real time, interacting with the environments. So the classical loop where we use embedded systems, including the recent trend of high performance embedded computing platforms, is one of quite advanced logic controllers that are reacting with the environment, the surrounding physical environment, by having a set of actuators able to check and read whatever is going on around the system, and making some computations and reacting by by actuating on the actuators, so manipulating the actuators and giving the correct output to the motors, the engines, the stabilization tunables, or whatever else our cyber physical system has. Now, especially whenever in this control logic, we need to embed a complex application that is made of several components, that is made, I mean, we may have several logic units that are interacting in our complex embedded application. We may have safety and certification constraints because we may not be able to, pick an extremely programmed piece of software, just deploy it on an automotive car, on a braking system of a new brand car model, and just pretend to put it on the market. We need to certify that. So there's a lot of these constraints that come really from many of these embedded systems applications world. So this makes development on these systems particularly complex. Now, as from the tradition of development in embedded systems, we have tools that are, of course, helpful to handle the software lifecycle development. So going all the way from the functional and non-functional requirement specification towards system specification, architecture definition, and implemented software. And as I say, the criticality here is to keep a gap that is as little as possible between all the various phases. So ideally, we would like to have a zero gap. We would like an implemented software that is sticking to the specification we have provided from the beginning, both functional and non-functional. So in the embedded systems world, there is the model-driven engineering paradigm that aims at filling this gap. And it basically makes use of a number of tools, including formal specification languages for the requirements and system specification, as well as model transformation engines for manipulating system specification and architectural definition, and going towards, splitting the architecture into various components and doing a lot of checks, a lot of verifications that can be automatically carried out, so that the refined definitions do not break the properties that have been stated on a formal level from the beginning. Then, thanks finally to some automatic code generation blocks, ideally we should be able to generate automatically software that is perfectly compliant with its specification, so that we can be sure that this gap is really reduced to the minimum. In other words, with this set of tools, we can try to achieve a correctness by construction in our high performance embedded system. Now, the problem is that traditionally, this kind of paradigm has serious problems with multi-core parallelism and even a heterogeneous hardware. So there's basically, this model struggles really at coping with nowadays complex heterogeneous embedded architectures, as the ones I was talking about earlier. In this project, we aim at basically filling the gap we are seeing nowadays between these traditional model-driven engineering techniques used in embedded systems, which have some limited support for parallelism, versus the parallel programming models we are seeing flourishing in the area of multi-core programming and GPU accelerated environments. but considering additional heterogeneity in hardware as we are observing nowadays. So not only supporting, you know, multi-core hardware, that's okay, we can do that with OpenMP and others, but, you know, supporting properly non-symmetric multi-core processing elements, GPUs, tensor processing units, FPGA accelerators, and how we can basically provide a comprehensive set of tools to software developers and engineers that need to create these systems, so as to keep into account our performance constraints we have on the system. So if the system should be designed, realized, architectured, and implemented in a way that it will have, would be supposed to have a given throughput, for example. Or if we have real-time constraints, we are building a microcontroller, it has to answer, make computations in 100 milliseconds or maybe even less, whatever it is. So if we have real-time constraints, how can we be sure we're not violating the constraint? How can we be sure we can pick a configuration of the system that is energy efficient, given our knowledge on what the system is supposed to do and what are the computations to be carried out across the platform? And also considering other non-functional constraints like fault tolerance. So the Ampere vision is one that we want to basically enhance the synthesis methods for an efficient generation of parallel source code while keeping non-functional and composability guarantees by basically mixing them with runtime parallel frameworks that guarantee system correctness and exploit the performance capabilities of the parallel architecture. This can be done by basically integrating these parallel frameworks into the MDE engineering methodology. The way we can do that is, for example, shown in this slide. That this is a glance into how we are trying to address these challenges. So on the top of the picture, you can see some of these high-level description languages that are used, for example, in our use cases. I'm going to say a few words in a moment about our use cases. So which are in the automotive, for example, AutoSAR, Amalthea, or Capella, and these meta model driven abstractions specifying components, communications, timing characteristics, integrity assurance, and other constraints. These should be enriched in a way that we can encode all our additional timing constraints, including the capability of the components into this level. You know, in order to know what are the parallelism degree that we can exploit. I mean, what is parallelism degree of our functionality, so that we can exploit parallelism we are going to find down in the hardware. And the way we can exploit the underlying parallelism is by applying some model transformation engines so that we can map and allocate basically the data flow and the processing pipeline stages from the underlying hardware in a way that we consider parallelism according to the typical programming models that you have underneath. So for example, if one of these high-level functions can be parallelized by means, you know, because it can use OpenMP code, we should be able to bridge this gap and be able to consider a parallel piece of software, a parallel component properly, that is properly integrated into the pipeline, so that we can make also all the real-time analysis, schedulability analysis, including the latency estimations. Normally in the real-time world, it's about making worst case estimations, so that we can be sure that when this thing will be deployed, it will meet the specifications. In order to get there, we plan so basically to make modifications to the high-level abstractions, to make modifications to the model transformation engines, to deal with code generators that can also properly handle parallelism according to the specifications we find above. And we need parallel runtime frameworks that is able to conjugate all these different pieces of parallelism coming from the high-level specified system by putting together all the pieces of, properly into the underneath hardware architecture underneath. And specifically here, one of the challenges is to consider possibly both software accelerators and GPU accelerators and FPGA accelerators. So you can imagine that in the most complex scenario, we might have even the same function, the same high-level functional block that can be accelerated in multiple ways by using multi-core parallelism, by using GPU, or by using FPGA. We may have a hardware block that is already encoding our functionality, or at least a part of it, and we may have these different options. So in our design exploration stage, we need to optimize the platform configuration and to choose the right things to be deployed at runtime. This is just a sketch of the software tools that are involved in this project. These are software tools that are handled. Some of these are normally modified by various partners of the project, and include the components of the software stack that you can see sketched out on the left. From a general architectural viewpoint, we aim at basically supporting on the very top of the hardware, we're going to have a hypervisor and an operating system that are two very typical components that are being increasingly used in complex embedded system software stacks. And on top of that, the runtime parallel framework was mentioned earlier. And here we're going to use a number of compilers and the tools that are used for design and development of the system. So in this picture, we have the top of the picture that is basically the tools used at design time. The bottom half of the picture is the runtime environment where the final applications get deployed. So overall, we have a resulting workflow in Ampere that is something like that. So at least in our vision. So there is this high-level description and of the functionality, as well as the high-level description of the platform. And through the MD engineering techniques, we get into code synthesis tools that make use of parallel programming constructs. So there we can use standard compilers, and we can take advantage of extensions that are already currently widely used, like CUDA or CUDA kernels or OpenMP or others. But these two are the two that are likely popping out in our final use cases. Then we have the resource allocation that will pick the proper configuration. So resource allocation includes optimization of the platform. And therefore, we will be able to run our applications on our runtime framework, including the operating system, hypervisor, and application middleware and everything that I was mentioning earlier. The use cases by which we plan to validate this European project, by the way, this project started in January this year, so it's going to take us busy for the upcoming 3 years and possibly even more. So the use cases are around the obstacle detection and avoidance system. Let's say, it's a use case in the context of the automated driving automatic driving assisting systems, the others that basically are in the context of railways rather than cars. Okay, and the predictive cruise control, which is the use case by Bosch, that instead is located in the automotive context for basically handling advanced adaptive cruise control functionality by actually providing a cruise control that has intelligence embedded within that considers a number of additional things. So it's not a simple speed controller, but it takes into account a lot of the information coming from the sensors, even maps or geolocation of the car, and everything that is known about the upcoming road segment ahead, etc. Specifically in this context, our university is going to focus on issues that are related to handling FPGA acceleration. And FPGA is increasingly promising in this environment because we can easily host, you know, a very flexible piece of processing hardware where we can deploy any function we like, you know, given the constraints we have on the FPGA fabric. So area, mostly the area constraints we have underneath. But the system on chips are integrating more and more interesting functionality nowadays around FPGA. So if you consider the Xilinx Zinc UltraScale Plus, this is one typical board that has, you know, non-symmetric multi-core capabilities, integrating also GPU acceleration, and integrates also dynamically reprogrammable FPGA slots. So all of these elements are also very, very interesting for embedded real-time applications. For example, because the FPGA can implement a timing, can implement a functionality with a timing, with a preciseness in timing that may be impossible to achieve in software. So even if you run in software a single task without any interference, it can be impossible to reach certain very precise timing. So in FPGA you can do that, and this is very interesting for a number of use cases. So predictability is also usefully facilitated by the use of FPGAs, because we can control the hardware that is deployed. We can control the state machine to which the hardware evolves when it realizes its functionality. And what is more, we can even control the interconnect. There's often this functionality by which we can deploy on the FPGA or even customize the interconnects that can be designed to properly handle quality of service, and specifically given, you know, a given access time, or, you know, access slots to shared DRAM memory. For example, if we have an external DRAM to the FPGA, we can access it with in a controlled way from several hardware functions by customizing the interconnect and providing basically an intelligent arbitration. After all, it's a real-time aware arbitration of the bus. Just let me skip on this because I don't want to run over my time. So I'm just mentioning that we are exploiting dynamically reprogrammable FPGA slots, basically to create an area virtualization of the slots, so that we are able to reconfigure in real time the hardware function that is deployed inside an FPGA slot. And we can do that with a very high frequency. So, for example, we have a use case, a demonstrator that is actually a prototype that I could not prepare it to be showed here, but it is basically making video streaming, real-time video streaming, by accelerating the image processing function, by basically scheduling temporarily the hardware functions that we are deploying on the FPGA slots with the frequency typical of the video stream. So imagine every 40 milliseconds, we are going on using, you know, reusing the same hardware slot on which we have been rescheduled a different hardware logic, because we are scheduling a different task, making use of that acceleration. So especially, this is one of the challenges we are taking in this project, how we can deal with this, with these real-time applications that make use of accelerators in FPGA or other types of accelerators in such a way that we can, you know, obtain another system that fulfills our timing requirements. So something that can be useful in case some of you is in the FPGA geeks and is curious, we have some open source software here which is available at the address fred.santanavisa.it, which is this software framework by which we can, which is this you know, mixed software hardware framework by which we can consider a software task that at a certain point needs to make a call to a function that is actually deployed in hardware, And so with a code skeleton similar to the one you see below, we can basically make it resembles a kind of remote procedure call to the FPGA fabric. So it's just a remote call. We have to prepare data in a precise way. We need to put data in a specific buffer, in a specific memory region. Then we can make a synchronous call to the other task and wait for it to finish. Once it will be over, then we find the final output of the task in another memory region. And all of these, all of these memory regions and synchronization with the other fabric and deployment of the custom logic you need also on the hardware block in terms of HDL, additional HDL that is needed to coordinate with other tasks and with our thread framework. This is all part of the thread framework. So the idea is that it is all designed in a way that we should be really minimizing the hardware engineering that is needed to do something like this. In other words, if you have a library of hardware accelerators that can be readily deployed in FPGA, you don't even need to see any time. You don't even need to see the Xilinx or the hardware engineering tools. You can basically treat all the things like a library and handle everything like a software development life cycle. Okay, so I guess I can skip on this, but it's one of our use cases and probably I don't need to tell you too much. Okay, conclusions. So Ampere aims to bridge the gap between model-driven engineering and the parallel programming model on highly heterogeneous hardware, as we have seen, by providing a development framework for CPSs targeting parallel heterogeneous architectures for increased productivity, compliant with current MD practices. We aim at providing an execution framework for efficient exploitation of parallel heterogeneous architecture, especially with a special focus on functional and timing constraints. We are going to validate the approach by integrating this Ampere infrastructure into relevant industrial use cases from the automotive and railway sectors, which do possess high performance computing and real-time requirements besides safety and all the other things I've been talking about. So thanks for listening, and I'm ready to take some questions.
Tommaso, thanks very much for the very interesting talk. We are running a bit out of time, but let's answer. There are a couple of questions. So one is from Fariha Baloch. What are the metrics for performance versus energy consumption?
Yeah, that's a very good question. So the idea here is that we are having a specific technically a work package, but anyway, it's an optimization piece of work that is going to deal with these trade-offs that have to be seeked between performance versus energy consumption. So you can imagine that, for example, in some use cases, we might have to trade off between, for example, the quality by which we do certain computations. So imagine a video processing applications because you have a camera on your device that is streaming videos. We might be able to dynamically, even dynamically if needed, but it can be even static. But we can have to trade off the quality of the video processing versus the energy consumption of the system, or we can even sometimes lower the frame resolution if needed. We may want to consider this kind of trade-offs. And in terms of metrics, that's actually a very, very good question. One possible way could be to associate a quality factor indicator to each different mode. For example, if I can go high-res, fully high resolution, I can have a quality indicator of 10. If I go half resolution, I go, 5 or whatever. And we can mix that with, for example, deadline miss ratios, or maybe we can have tardiness, we can have system slack time, or we might have a power consumption, as a estimated power consumption of the platform. So we can mix all this together in an optimization program, and that's typical. I mean, in the past, we've been dealing with this problem by combining these things into into an objective function that sums up different terms with different weights, so that we can optimize according to different objectives.
Okay, and another question: how easy is it for new developers to use Ampere for their work?
Yeah, that's a very good question. So we hope it's going to be easy, but as I said, this is an ongoing project. So there are a few things that we have available, a few bits across the various partners in the project. There are a few demonstrators that are already available and can be leveraged, but the full framework, we will need time. Of course, it's a 3 years project. We need time to put together, integrate all these pieces, and even solve some of the very tough challenges we have underneath. So hopefully, I hope it will be quite easy to use. So at least the idea, as I said, should be in the most, let's say, lucky cases, you could consider, for example, hardware blocks like libraries. Once you import them, you can use them, they get automatically deployed. Also another burden that the framework should be able to address is design space exploration. So how to automate, whether is it more convenient to make, to have a given type of processing function or control function, or I need to switch to something else, or I need to decide which function to use, what is best to respect a given timing of the system. Because if I run too late, if I complete my processing too late, then it may. So there are a lot of these things that are normally traditionally done, very manually by the performance engineering. There's a lot of this performance engineering job made by embedded system designers and implementers and developers. So hopefully we should ease this task a little bit.
Yeah, I totally agree. We are working on something similar, and I'll be happy to talk about it in the panel section at the end if you're available. I don't want to take any more time from the next speaker. So thanks very much.
Everybody, bye. Thanks everybody. I'm staying for the later session.
Our next talk is an invited talk about the portability and performance of real HPC applications in a virtualized environment. Our next speaker is Dimitris Delis. He's the person responsible for the infrastructure and the applications running on the Greek supercomputer, ARIS, on behalf of GRNet. So, Dimitri, if you're ready, the floor is yours.
Hi, I'm ready just to share the desktop. Do you hear me? First, you hear me?
Yes. Yes.
Okay. Thanks. It is slideshow. Okay. You see it correctly or no?
We can see your chat. I think.
Yeah. Something. Okay.
I'm not sure.
Yeah.
Can you go to the next slide?
No,
okay.
Okay. We'll work with this. You see the bottom line of the slides or no?
We can see that, I think. Yes.
Okay. In this talk, I'll describe some things about portability and performance of real applications that mostly run on HPC or are suited for HPC, and what happens and what may happen in the virtualized environment. Virtualized environment may be whatever. It may be virtual machines, but most of things that I show here are using containers. Although in almost in any sentence, bullet, and so I don't describe a certain container framework. Most of these refer to generic purpose. It is the same like in all frameworks, except few that are denoted. Also, this presentation is end user oriented. What the end user likes from or waits from virtualization, what may see, what is good, what is bad, what is lucky, unlucky, whatever. and some factors that affect the final result. Few things about why users ask virtualization. Then we'll go to details on the portability and performance. And before conclusions, some practices that one end user could do with support from administrator point of view. So one first category of users are the users that have a legacy application that depends on a legacy operating system, legacy libraries that are not available anymore. Or in order to reproduce some published results or check something that is 10, 20 years ago. I don't know if this legacy application dependent and so on makes sense to many of you, but I know that last 3 years I found at least 2 applications, user applications, codes that were breaking the rules of compilers 20 years ago. So you need a system that is at least 20 years ago, 20 years old. In these cases, virtualization is the only solution, a reliable solution, so don't discuss more about this. The other reason why users ask for or are interested for virtualization is the ease of use. I have to create my binaries, I deploy to any system, it is the same, I have my image, I transfer somewhere, I run it, I get my results, and I'm happy. If you had an executable, you have dependencies, dependency on versions, so you have an image, whatever it is. I'm referring to the term image, but it may be everything. You go to another system, you run your code. There's no time to build again the system. And on this new system, if you have dependencies, you have, if it's possible, to rebuild all the dependencies that are not available. There are some cases where users, user software depend on binary packages, mainly libraries, that cannot run anymore on recent systems. So you have to work with an old image, transfer to a new system, and then run. And at the end, these machine learning frameworks, I don't know if someone tried to compile TensorFlow or PyTorch and so on from source. First, it is very difficult and time consuming to compile that an end user cannot do it. So you get from somewhere, someone did it, you get the image, you run it, and you're happy. This is very common in some areas. Industry is one of these. In industry, you have some standards, you have a production of a product, whatever, you need to do this thing as it was performed 10 years ago. So it's a good way to keep running the same way, although the hardware changed. Now, let's go to the portability. Let's wear the user hat. I do the development, I do my testing, I create the image, all the requirements inside, I transfer the image, and I expect to run as it runs in my, say, laptop. We have 2 probably scenarios. The first is I have an old laptop and the run system is a new system 1 year ago. What may happen is it runs, okay, I'm happy, saves the time to compile, I transfer the image and I started to run. Or no, we'll see this is in next slides, especially if you pay for CPU time. This means for performance. if you reverse the ages of hardware, you have a fresh development machine and 5 years old RAM system. The probabilities are, okay, it runs, you're happy and lucky, and you get crash directly with typically illegal instruction. We'll explain later what this means. But this means that you have a binary that is for a new CPU, needs new CPU features that are not available in the old run machine. So, in case that it runs, I do my runs, okay, I get my results, they are correct, I'm happy. But someone else tell me that, oh, it takes too long to complete. You do some tests with bare metal. Bare metal is the reference. And you see that your performance is sometimes slower. It may be 2 to 10, 1.5, it depends. Probably it will be the same, but it depends on the application. When you compile a piece of software, the compilers do optimizations. It depends on the code, what optimizations the compilers are able to do. If you enable CPU features, then you optimize to use also these CPU features. So the clause on the CPU features of built and run machines are, if the features are very close, probably you don't see any performance issues. But it's something that we'll see later. In some cases, you may see with containers slightly 1%, 0.5% faster execution with virtualization. So why all these happen? When you start to build a package, typically the make files, the build systems in general, check the compiler, check the CPU, the characteristics of the CPU, of the memory. It depends on the software, of course, and use the corresponding flags in order to optimize for this hardware. When you use performance libraries like BLAS, Fourier transform, and other mathematical libraries, the build process of these libraries includes also hardware characteristics like cache memory size, except CPU features like SSC, AVX, AVX2, FMA, whatever. These are for x86 family of processors. Sometimes they run various versions of the same code using different features and select what is the best. So you have a library that is optimized to run on this building machine and the same type of machines. And of course, you can turn off the auto-detect of all these parameters and say, build my binary or library, whatever it is, for this CPU, these features with this level 1, level 2 memory. It depends on the package. This means that when you optimize for a recent, say, Skylake, and you go to run to an Ivy Bridge, you'll get illegal instruction because your libraries and executables use features that are not available on the run machine. So in this case, you have a problem. So if you need a fully portable image that runs on any machine, at least recent years machines, the same architecture, like x86, you have to disable almost all this hardware optimization. Taking into account this evolution of processors, features, and so on, These days is safe to optimize up to SSE2 superscalar extensions for x86 architecture in order to have a fully portable image that runs everywhere. But you have to pay the performance fee. Here is an example. This is from work that involves many other packages, but I present here this. GROMACS is a classical molecular dynamics package that is very popular in research areas. It can simulate biological systems, materials, whatever, with molecular dynamics. And some characteristics of this package, it has a small memory footprint with respect to the similar packages. It is very well optimized for memory usage. Sometimes with a large enough simulation systems, the memory footprint is less than 2 gigabytes for a full node, no matter how you run. It is highly optimized. It has the plain C kernels. It has kernels that support SSE2, AVX, AVX2, AVX 500, and so on. And also it includes multi-level parallelization. It can run serial, of course. It uses OpenMP parallelization, hybrid MPI and OpenMP, and on top of this, you can use also CUDA. So with one package, you can explore many areas of hardware. And here is the result. Here are the results. The results show the performance is a metric like we say gigaflops for one machine. When you compile agnostic to features, this means C kernels, you get the performance something like 0.18. When you enable SSE2, you run almost 5 times faster on the same machine. This machine that these numbers obtained is the same as a Haswell. When you enable also AVX, you have 6.1 times faster execution. With AVX2 and FMA, almost 8. And all these numbers, all these columns, obtained using virtualization. And the last column is the native, that is AVX2. You see that there is no difference in performance. So when you use the same features, the same optimizations, you obtain bare metal performance inside the container. The picture is the same when you use OpenMP and up to 40 threads per node. And also, the same performance is obtained when you use different virtualization environments. In this case, the numbers I present here are from Singularity, but the numbers are exactly the same with Docker. When you run on the same machine, the same optimization flags and so on, that is expected. Up to now, let's take the single node use. You can obtain bare metal performance using containers or any other virtualization. But you have this issue with portability. So up to now, we have the case of a legacy code, nothing to do, just run. If you need to run a code that is 30 years old, you don't care about performance. If you need a fully portable image that runs everywhere, you have to pay the performance degradation fee. Discussing with users that asked and were interested for virtualization, is this way of working? I need a full portable image that runs everywhere. This is what they have in their mind. They think that, okay, I have the image, I run it, and I'm happy. But, okay, if you pay for CPU on cloud, for example, and you use something fully portable, and you run 8 times slower than the speed that you could obtain, you pay 8 times more money. So you have to rethink. So what we can do? You can use virtualization and containers on a single node up to now. You have your image, you have your no CPU intensive libraries, graphics, whatever is not compute intensive. You have all these in your image. And you have also your source. You compile targeting the run machine. You have your binary, you run at bare metal performance. Another alternative that is a combination of portability and performance is to use these cross-compilation techniques. I need to build a binary on a different path for this feature set of CPU. Another binary on another path with other set of features. So, for example, with the picture you show with performance, you build one binary library and all these for SSE, one for AVX and one for AVX2. And you create a wrapper that at runtime checks the CPU, it has these features, so I'll set the environment that I'll spawn the corresponding optimized for this architecture binary. When we go to MPI, that is the next level of parallelism, on a single node, there are many applications that use MPI for parallelization, but not hybrid with OpenMP. Last decade, at least, MPI implementations use shared memory for inter-process communication on the same node. They detect that they are on the same node. So in this case, with Docker also, you obtain bare metal performance with MPI on a single node. The same happens with GPU. If you have your binaries compiled for GPU compute capabilities that are close enough to the existing hardware. For example, if you did your compilation, the GPU code 5 years ago, the compute capability at this year ages was 3.5, for example, and now you have a Volta, then you have an issue, but it is not too crucial for performance. So up to now, we covered applications that may fit on a single node. When we go to the multi-node applications, typically they use MPI for communication. MPI is the winner. As we saw in previous presentations, you need the host MPI run, or whatever is the name, probably other spawners. You bind some things, storage, dev InfiniBand, for example, and so on. In this case, you have your MPI application compiled inside the container. So you need to have ABI compatibility between the MPI that you use inside the container and the MPI environment on the host. Here with MPI, there's a problem with these, like Docker, that create their networks You have to do much more. You can do it, but it is not for the end user. Once you fix your these compatibility issues, there's another issue. You have your MPI inside the container, the outside MPI. Okay, they are portable. Probably the inside container libraries are not aware about these InfiniBand protocols, RDMA and so on. It is common. It depends on what you used to build your binary. It is common to use the InfiniBand interface on host, but not with, for example, RDMA or UCX or whatever, but just with TCP/IP. In this case, it depends on the communication patterns of the application. You may have significant impact on performance or no impact at all. It depends on the communication patterns. In general, what happens is small number of huge packages for communication and large number of small packages. Here is, again, Gromax on the same hardware. When you run with MPI on bare metal and on containers, this is with the Singularity that has a good handling of network and MPI. The performance degradation is significant. It is something like 3 to 4 times at high number of nodes with respect to the bare metal. And the reason for this, although on a single node you see no performance, it seems, but it is an image issue. On a single node, the performance is the same. But when you go to more than one node, you see a performance degradation. And although it uses the InfiniBand network, the traffic goes to TCP/IP. This software mainly depends on latency and not on bandwidth. So when you send large number of small packets with TCP/IP over InfiniBand, you have decreased the performance. So you get this performance degradation. If your application has a more convenient communication pattern, probably the effect is lower or negligible. What you can do when you build mapping the host MPI, you can install drivers, probably settings of InfiniBand, you map directories, libraries, all these from host. Yes, you can obtain with containers bare metal performance. This has the problem that when you move to another system that has no InfiniBand, has Omnipath, you have to do the same. Although this is normal for someone from administrator point of view, when you ask the user to do all this, it is not possible. It is probably easier to just port the application to bare metal or to whatever it is, instead of playing with these mappings that probably the end user, the application user, probably may not understand. So yes, we can, but end users in many cases cannot. So in this case, we need to sit together with users and administrators and make 1, 2 images or a few sets of the same image that may be used for in order to have performance. So let's go to conclusions. When you need just legacy code, we run, that's all. When it's fully portable, we pay the performance penalty fee. When you use the container, for example, virtualization as development platform, yes, this make the more efficient use of the hardware. And okay, for single node runs, discussed this. The only thing on single node runs is if, for example, you do development on an, say, CentOS 4, Red Hat 4 machine, and you use the system GCC, yes, then you have a problem that this GCC has no idea about AVX and all these features. So you are limited by the software on the building machine. And also one may build multiple versions of the same package and libraries and user wrappers to select at runtime what at the end at the runtime and at the run machine will use. For multi-node runs, the situation is more complicated. It needs more work with administrators' involvement. And you obtain also bare metal results. I think, yes. Thanks for your attention. And let me see. I'm out of time also.
Thanks very much, Dimitri. It was a very interesting talk. I see there is one question.
Yes.
Including multiple binaries in the same image may be difficult for distribution if the binary is large. What are your thoughts on this?
Yes. It depends on the application. When you use binaries that are not static and you have the majority of the libraries in shared as shared libraries, and these are the compute intensive libraries, you have just the same, not the same, one version of the library. Yes, the binary at the end have some size. Typical sizes depend on the applications, but usually there are few tens of megabytes for HPC applications. This is an issue, but it is not a huge space. It is a small space with respect to the rest of the contents of events.
Okay, another question is, can you elaborate on the use of wrappers for different hardware capabilities? To what extent can we automate such an approach?
Look, what may happen, I have something that I used in many cases. You build, for example, one application that installs in /bin/ in a prefix. You use a different prefix per feature set. One prefix for AVX, for example, one prefix for AVX2, and so on. And you create a binary directory that checks proxy CPU info, for example, decides somehow that it is AVX2 machine, and instead of run the application, because typically it's a shell script, spawns the executable, probably sets the library path to this non-typical prefix that holds the optimized for this architecture binaries.
Okay, I suppose that's a similar question. Any thoughts on how an admin can provide a suitable build environment?
Yes, obviously. The issue is when you go to another system with another administrator. I don't know if it is the same. Probably different hardware, mainly network hardware, OmniPath and InfiniBand or something new. But in general, yes, if the end user has something that's running, no matter the performance, quickly, I believe that an administrator can help to make it totally portable. But one has to something that compiles and runs no matter the performance. Then the administrator can be involved to make it better. But in most cases, users have something that runs, doesn't run at all. So yes, in general, it's possible, yes.
Okay. And the final from me, is there any of your work of anything that you have available in a repo or open source online that users can try?
This part of the results is part of a project for European Union. It is not yet online. It has to be online, but happened with this COVID-19. I asked 1 week ago if they have it somewhere, why it is not available, but not answer at all. Sometime it will be available online. It is an hpceurope.eu website. This is the document that has much more applications, applications that behave the same way, applications that have difference and significant difference in performance and so on. But in any case, you can contact by usual ways, not you, only you, but the audience at the typical, the normal addresses, support and so on at HPC.gr.
Great. So thanks very much for your talk.
Okay, thanks.
Let's move to our next speakers. It's actually the mini cluster we have about unikernels. Our next speaker is Simon from Mech Labs. He's a systems researcher working on virtualization and networking. He's the lead maintainer of Unicraft, an incubation project about unikernels. He's currently a PhD candidate at the University of Liège. Simon, whenever you're ready, the floor is yours.
Yes, thanks a lot for the introduction. Let me share my screen. So, just a second. Good. Can you see the slides?
Yes.
Perfect. So this is a really short overview that I want to give you to our open source project called Unicraft, which we are running now. I would say, I think it's 2.5 or 3 years already. I was also last year at this conference and was giving you a more deeper introduction to it. So this year I want to give you small updates and highlights what happened last year with this project. And maybe you're interested and want to try out or join us even. So first of all, let's briefly speak about what Unicraft is, or actually also what the unikernel is for those that hear that term the first time. So on this slide, you see a common software stack where you run, of course, your application with your libraries on a standard purpose kernel, and that runs either on a hypervisor or even bare metal. And in the unikernel case, you can imagine, of course, you run on the same platform, meaning on a hypervisor as a VM or bare metal. But we take the application and create or run it in a single and flat address space, and say that isolation is done by the hypervisor layer, and we only take the components of the kernel that the application needs. So meaning only drivers that are necessary for the application to run, and also only necessary that are needed to run on the target environment. So we get a really thin kernel layer. We get the application much closer to the hardware or the virtualization environment. And with that setup, we have quite a lot of advantages in doing specialization, which gains us performance and efficiency improvements, a really small trusted compute base because you know which components are in your whole OS image plus application, and the memory footprint is quite small. In the Unicraft project, we do everything as a library. So it's actually a unikernel built with a library OS concept. So we have decomposed OS functionality like a scheduler, like a memory allocator, or even VFS or file system support are each individual libraries, where you also have alternative implementations where you can choose from, or you can leave it out even, so you could run without scheduler. And that way, you can really fine-grained build your kernel layers underneath your application to what it needs. And the interesting part in Unicraft is also that each library is highly configurable. So you can really do specialization, let's say, take the TCP/IP stack, for instance. So you can really configure it with buffer sizes, etc., so that it really fits exactly the application you run. So you don't need to take care about the general purpose. We have a make-based build system. And similar to Linux, we use kconfig. Actually, we took it from Linux. So you have a menu-driven configuration of your unikernel. The application domains we see so far is quite widespread because it's still an OS, right? Let's say we have let's say 4 domains where we get benefits from, and depending on the target domain, you benefit differently from these properties. So, for instance, the fast boot time, because you're much faster with initializing the small software stack, is good for reactive VNFs, serverless, function as a service, IoT, and so forth. You get quite a lot of resource efficiency, also good for serverless, IoT, or even edge computing. You achieve high performance because you're binding your application much closer to the hardware. You get rid of system calls. You do only function calls, which is really good for HPC, really good for network function virtualization, mobile edge computing, and so forth. And also the mission critical market is interesting because of this small trusted compute base. So you have less code in your images, and you have a potential cheaper verification, which fits for automotive or industrial IoT cases. So now I'll run over some selected projects. We actually do much more than this, but I want to show you some highlight of what happened the last year. One big item we're working on with the Unicraft open source project is on supporting language runtimes. So we have a couple of them ported in the meantime, so you can write applications in C++. We have ongoing work on supporting Rust as language runtime, Go, Ruby, JavaScript, Python, and so forth. All with the main targets for serverless, function as a service, and it turned out for IoT, but also industrial IoT. To give you some numbers, for instance, a full MicroPython environment. So this is a Python implementation for embedded devices originally. You can build an x86 virtual machine image for Zen with 828 kilobyte. And then the only thing that's missing is your Python script on top. When we take the more standard Python 2 implementation, CPython, we get images of 3.9 megabytes, or taking the Go runtime, we have 555 kilobyte. So to give you an idea or an order of magnitude how much that is smaller compared to standard distribution, which usually is Linux, and you have some user space environment there, and then your language runtime on top for just running your application. We had a quite interesting demo, which I want to show you here in this talk, that we built together with the Mozilla Foundation. They were actually interested to get the WebAssembly runtime deployed not only in the browser, but also in the cloud and up to the IoT devices. And the interesting thing with Unicraft was we get a really efficient and small execution environment for WebAssembly. Because we don't run a full distro, we just run the kernel layers we need. That makes it suitable for resource, what's called, devices that have very little resources on the edge or on the IoT device. And there, usually, there's also the problem that the boot time is something that really makes a difference if you run a minimal OS or a full-blown distro. And this is what I want to show you in this demo, where we actually here, we have two Raspberry Pis. The top one runs a standard Raspbian distribution, and the lower one runs a Unicraft image that just shows you the boot time. So to give you a baseline how long it takes to boot them up. And now I'm going to press this switch. The machines come up. Unicraft is already there, and Linux starts doing the whole boot process. And this is something which is really a pain point for IoT. So if you have your intelligent light bulb or something like that, smart light bulb, you don't want to wait like minutes or a couple of seconds till the device is ready to use, right? The other topic we're working on is on high performance networking. So originally we come from the network function virtualization space. But in general, what you want to do here is removing the noise and overhead you get by the operating system to be, in order to utilize the networking hardware much better. So we did the first port of Intel DVDK. So Intel DVDK is a network data plane development kit. But also we ported applications like Redis, Nginx, and SQLite, which are widely used. More are coming. And I want to show you here some first numbers we got. The first number is here with the DVDK development kit. So usually in the NFV deployment, you had a full Linux distro running, and then on top you install DVDK and implement your application as DVDK, or your network function as DVDK application, and DVDK is bypassing the kernel. That way they achieve extremely high performance, but you still have the maintenance overhead and all, also maybe risk of some noise. They do actually quite a lot of tricks to avoid that, but you have a full Linux distro running underneath, and we were asking ourselves, can we get rid of that? And in fact, we can, even without killing the performance. So you see here a transmission test. The takeaway message of this graph is actually that we are able to keep the performance of DVDK, but removing the distribution underneath completely. Nginx, that was an interesting experiment. So we were trying a couple of different unikernel projects. One famous one is RUMP. There's OSV. Then we run Nginx as a Linux KVM virtual machine. Tried also with Docker. And actually RIA is the code name of the latest release of Unicraft. Was outperforming all of them in our experiment, except of a native Linux instance, which means it runs bare metal without any virtualization in between, which of course has even closer access to hardware. So we didn't do any network device path-through in this setup. So it's still going through Virtual and then to the outside world. We also started working on building AI prediction service. This is a bit more of an outlook. So we, you know, PyTorch, I guess, TensorFlow and so forth. We have at NEC a project that converts the models that you define in these frameworks into optimized code. So there's some mathematical reordering of instructions, some analysis of the AI model that you use, and it generates use C code or CUDA code or whatever environment you have in the end. So the result is quite small libraries that contain just your model and your parameters, and that's a perfect fit together with Unicraft, that, you know, where you select then just the drivers you need to get it running in order to build efficient AI prediction services for the edge, for instance, but also for HPC, because you're you have a much leaner software stack, and you're saving resources. Then also, Unicraft is actually easy to use. We tried to come up with a so-called tool that is called Craft, which improves the user and developer experience, especially if you want to start with Unicraft and want to quickly try to get your hands dirty. You get it from our GitHub page, and you have a few commands to build your first unikernel. First of all, you run craft update that fetches all the repositories, or actually this fetches all the index of all the repositories we have, because we maintain some libraries off tree of the main repository. With craft list, you get an overview of that. With craft init, you can select an already available application, and craft build is then taking care of the compilation of it. And there's even an integrated quick test command called craft run in order to run it on KVM. So, and I'm stopping here. Here are our resources, and I'm open to receive questions for you before we move on with the next talk from Stefan Lankes. So probably I need to close the presentation in order to see your questions. No questions? Ah, yeah, okay. So I have a question from Jim Leong. Can one log into the OS? That depends on your configuration. If you specialize it to an extreme, you can remove everything, meaning even no shell or telnet or whatever service. So there's then no login prompt for that. And you would use the hypervisor tools to analyze what's going on or monitoring the unikernel. But to make it a bit more usable, we are working on adding, let's say, either REST API driven monitoring interface, or giving you a shout. Next question from the same person. Is this a Zen guest only? No, it's not. Actually, we support KVM, we support Zen, we support x86 bare metal, and we have also, together with ARM, a port done for ARM SoCs. So we run on Raspberry Pi, we run on KVM, NOMARM, and so forth.
Hello, can you hear me?
Yes.
I have a question.
Mm-hmm.
So I was curious because you mentioned that among the components you can pull into your libOS approach, into your unikernel, which is like a library's approach. You mentioned also schedulers. Yeah. So for scheduler particularly, that's one of the critical things where you can't really, I mean, you need help from interrupt drivers to do it efficiently. So if you can just say a few things about scheduling in your Unicraft system.
So scheduling is implemented by a scheduling library. So we have one upstream for cooperative scheduling. We have another one for preemptive. There's a separation in terms of API. So there's a low-level API that does the context switch, that takes care about your target environment to do thread creation and so forth. But all the logic, you know, when to switch or how the queues are managed and so forth is a matter of the library that you choose for your unikernel. And we have also a port of pthread. So if you need pthread APIs, so those are also available. But you can run even completely without scheduling if you don't need.
And do you know whether there's any performance loss you get in scheduling using this library approach? Because I would expect you go into multiple, you know, you need.
So you need to imagine the libraries. Each library is just an object file in the end that gets statically linked together. So you have just function calls in between them, and we can. Since we're building everything in one image together, we can use really aggressive compiler optimizations like
but
link time optimizations and so forth.
My concerns are more into, for example, for preemptive or round-robin scheduling. You just, you know, you need hardware interrupt to come into.
Yeah, sure. But I mean, if you want preemptive, I think you have a good reason to choose a preemptive scheduler. So you are aware of these costs. If you don't willing to pay these costs, I recommend you take the cooperative scheduler, which
I guess
where the application is doing the thread switch and there's no timer setup done.
Sure. Okay, thanks. And also I had actually also a second question about the hardware architecture, that the platform you used for the performance, the networking performance benchmarks you showed us. So basically you made those 10 million packets per second, or no, 9 million packets per second, I guess.
Mm-hmm.
Was on what hardware exactly, and was it like a host-to-host test or?
The setup was a KVM guest sending out through Virtualization to the KVM host, which was a Linux instance, and then going out through a 10 gigabit interface and receiving on a second host the throughput. Of course, this was bottlenecked now with the 10 gigabit link. But in that test, what we want to make sure is that our Virtualization driver implementation is not slower than what you get with Intel DVDK, which is like the de-facto most performant. And
okay, sure. So you think the performance of the computing platform was not too much important in that in your setting? The performance of the processor was not very too much important in the test?
There was a slight hit, but this was even, we compared in that graph with a Linux guest. So you paid the same hit with virtualizing Linux and running DVDK in there.
Okay, good. Yeah. Because we made some extensive evaluation of the performance in various cases, with various model communication patterns, and we presented some of these also at last year VHCP. So maybe it could be useful to compare the results. So, you know,
yeah, definitely.
Full spec of the hardware and just have a look.
Yeah, it was a Xeon E5 something generation.
Okay.
And then this standard 10 gigabit Intel IGBE. I don't exactly remember the exact model name, but I think it's
yeah, possibly I reach you out by email to get some.
Yeah, sure.
Some more. Okay, thanks a lot.
Okay. So in order not to run out, I would like to hand over to Stefan Lankes, which is actually, he's working since a while also on the unikernel space. And is also with a target even for HPC. I'm really glad that he's here, and he's presenting now to us something written in Rust. So they ported their or re-implemented their unikernel to Rust, and he's going to tell us, I guess, about his experience and how that looks like. So thank you.
Yeah, thank you for the kind introduction. Yeah, my name is Stefan Lankes, and the work was realized with Jonathan Klimt, Jens Breitbart, and Simon Pickartz. And yeah, more or less you explained everything. So we do more or less the same, but we use completely up. We wrote everything in Rust. That's the main differences. Sorry. I jump over the slide. I think I have not to explain what is the unikernel and a library operating system, but maybe it's interesting to understand my background and the first project in this area and what to write a library operating system. It was Hermit Core, and I have a strong HPC background. So it was a mixture between multi-kernel and a unikernel. So multi-kernel is popular in HPC. So you run a second kernel side by side by a general purpose operating system, bare metal on the hardware. So for instance, Mac kernel is using it. It's a HPC operating system from Wickham Supercompute Center in Tokyo. And Mac kernel is more compatible to Linux, and my way was more to write a complete unikernel. But you could use it in a virtual machine. Every classical runtimes from HPC environment was supported, so OpenMP was there, PSET library, cross-compiler for C, C++, Fortran, and Go. So in principle, the classical runtime system for HPC. So the structure is more or less like this. I take OpenP runtime system from open source projects. I have also the C library, and I have only to write a small library which handles the interrupts, which schedules the threads, and so on. During the project, C is not, it's a good programming language to write an operating system. It's designed for an operating system, but it's of course error prone. And if we start today a new project, it would not use C. That was my conclusion. But the main problem was more the management of the code. So in the last, I started 4 years ago. So there's something like a toolkit for unikernels, but was not there. So I have to manage OpenP runtime, C library. If there's a new version available, I have to update my existing one, a cross compiler, and this was difficult and was a pain. One problem is that every open source project uses a different tool chain, different make files, C make files, and so on, what you want and what you wish. And that was the idea. We should switch the programming language, more or less. And of course, we should use the programming language that is more safer. And I started to write it in Rust. Rust has a safe memory handling. Of course, every new programming language has to do it. The basic concept based on ownership and borrowing. So there's always one owner of the memory reference, and of course you are able to borrow it. But if the owner is not do not need the reference, the runtime system automatically deletes the reference. And this comes more or less for free. It's not realized by a garbage collection. So it's everything integrated in the compiler infrastructure. Also good side effects. The runtime system is split in two different parts. We have a part which is OS independent. There is, for instance, support for string handling and so on. And a part for OS dependent support for creating a TCP socket, for creating threads, and so on. And if you register your own memory allocator, then you are able to reuse also existing queues, heaps, linked lists, which comes from the Rust community. and you have to do it not, yeah, you have not to write it by your own, and it's tested, it works, and normally it scales also because it's part of the Firefox, and the Firefox should be fast, so it's tested. The good thing for a kernel developer is you can bypass every fixed rule. So you can bypass your ownership and borrowing concept. You could use inline assembly. Maybe you need it. So that's especially important for an operating system kernel. That's a good feature. And in this case, you have to mark the function or the code section as unsafe. That means not that the code is unsafe, it means that the code is not checked by the compiler because he's not able to check it. That can be inline assembly, that can be using of a raw reference, a raw pointer. That could be also by calling a function as static library, which is not part of the Rust runtime system, for instance, the C library, and this is always unsafe. That's the basic idea behind it. And the good thing is there is a really good package manager. So every open source packages is published at crates.io. So if you define some dependencies, for instance, your parallelization library, you download it directly the latest version from crates.io and link it to your application. So I have not to maintain it. That was the benefit of it. So I started to rewrite the kernel completely in Rust, and now I have a user space which is more or less C++ maybe, and I did not support Rust application. Of course, this is, was not a good idea, so I changed it and integrate in a Rust standard library the possibility to talk to my library operating system. And this is not a huge problem because pthreads, newlib, yeah, it's a POSIX standard. It's of course supported from a Rust standard library. So I have only to modify it a little bit, and I was able to run Rust applications on top of it. But I have still no C code in my runtime system. So the pthreads, newlib, and principal, it's only a wrapper for my library operating system. So the next step was to remove it. So in principle, the standard Rust runtime called directly my kernel. And now I removed my complete toolchain. So there's no cross-compiler. There is no cross-linker for my old toolchain. Everything that comes with the Rust runtime system. And you are able to build it on every system where your Rust toolchain is running. So it could be Windows, Linux, macOS. It works everywhere. So you are able to build my kernel, yeah, on all systems. One point which was not mentioned is my IP stack. So I'm not a network expert. So my task was not to rewrite an IP stack, and so I used a C-based version, lightweight IP, and integrated in my Rust toolchain. And of course, the idea was also to remove this part of the kernel. And there exists already IP toolchain or crate for socket handling. It's called small TCP. It's able to run in a standard environment, but also bare metal on the hardware. And my motivation was to integrate this stack in the standard library. The interface is a little bit different. So if a classical Rust application use my TCP, the standard runtime system and the TCP stack in the runtime system, or not the TCP stack, the TCP interface, I have to rewrite a mapping between TCP stack and the Rust runtime system. I could put the TCP stack in the kernel directly in the library operating system. I could put it also in the standard library. I know it's more or less a mixture of both. Because my motivation was to move it in a higher level. Because in this case, for the mapping, I could use everything what Rust is able to provide for me. So I could use threads, I could use multi-producer, multi-consumer channel, everything what Rust provides you is usable in this stage. This was the basic idea. So the Rust application, if you want to send some data, send a request to the standard library. I could also draw, so standard library. The standard library call my TCP stack, and then the TCP stack is able to call the virtual driver in my library. That's the basic idea behind it. To organize the packets and to coordinate the transfer, there is a thread running in the TCP stack. So this is important for all receiving packets. So you receive some packets. They could be maybe an acknowledge from previous package, but also data for thread and the standard library. So the thread has to check it and then send maybe a response to the thread which is running in the standard library, so that he knows the data is available, and then they pick up the data from the buffers. So that was the idea, to use it and implement it in this direction. Yeah, but the performance was not so good. This is results from the paper. So for larger packets, I got more or less the same performance like a Linux. So that's Linux running in a virtual machine and sending data to another node where the server is running. For larger packets, it's okay, but for smaller packets, yeah, it's not a good solution. So I try to investigate what's the wrong way. Where's my slide? Yeah. So, sorry, some technical problems. So, so the problem was, in principle, he was running a thread. He is running also a thread waiting for the data. Interrupts arrives in this case, so data is available on the virtual drive. The data, the interrupt handler wakes up the thread. The thread is checking the package, knows the packages for the thread and waiting for the results. So transfer the signal in principle to the other thread. And so the reason is for the bad performance, the context switches. This is one reason. And the huge number of interrupts. And the second problem was also everything is built for common hardware architectures. So there supports vector instructions. And by context switch, the vector instructions or registers are not saved from the operating system. That's the typical way to do it. The operating system assumes that maybe the other thread is not using the vector instruction, and then you save time. And if the other thread is using it, the triggered an interrupt, and then afterwards I store the old value in the context of the previous thread. So for every virtual IO interrupt, I create more or less also one interrupt from the floating point unit, and this was a problem for the smaller messages. And the solution is more or less also clear. I have to avoid it. Sorry. So the solution is in principle to avoid context switches. So if a thread is using the IP stack and waiting for data, then in principle it's switching in polling mode and wake up waiting for the data, and only if the data or the threads, no thread is doing something with the TCP stack, then I'm waiting for the data in the receiver or coordinator thread. That's the basic idea behind it. The results are previous, not final, because yeah, I'm working on it. So it's a current solution, I use also not classical techniques to reduce the number of interrupts for network cards. So that's the reason that it's not comparable with Linux, but nearly. Good. So some basic performance evaluation from a Rust kernel. So I compared with a Linux system and running with KVM. CentOS is installed, and it's just installed, and SSH daemons is running in CentOS. So the machine got 4 gigabytes, 700 is already reserved. The boot time is 15 seconds. The image size is also a few gigabytes. The time to reschedule the system in the empty system is 1,500 cycles, and to get the process ID is also 1,000 cycles. And if you compare it with my kernel, of course, the boot time is clearly faster. The image size for the benchmark, which is running, was also small, 1.5 megabytes, and consumes 58 megabytes for my system. Scaling time and the evaluation of the PID is clearly faster. And one request was from a reviewer: what is the difference in performance from link time optimization or without link time optimization? And for micro benchmarks, there's no difference. The kernel is a little bit smaller, or the image size. This is with LTO support, this is without the LTO support. But in principle, for micro benchmarks, I have no differences. And also, the differences are small. So it depends, of course, on the application. But for kernel services, the difference currently small. Is now every Rust runtime or Rust application able to run on my Rust environment? Yes and no. In principle, yes. So if you have some dependency, for instance, in this case, Rain is a parallelization environment. You say, okay, my code based on Rain, please download it and link it to my application. That's working. But if you include a crate which bypasses the standard library, which is not forbidden, then of course, C library is missing. So if you call directly something like mmap, where you know in Unix environment it's working, in my case, it's not working because there's no C library. So it depends a little bit on the crates, on the dependencies, but in principle, it works on most applications. The second question was from one reviewer was, the share of unsafe code. Of course, you should avoid the uses of unsafe code, and sometimes you are not able to avoid it. For instance, if you want to configure some messy specific registers. So I listed for all my crates which are using, so I wrote only this part, the first line. All other parts comes from the Rust community. And so 3% is unsafe on my code. And this gives a hint, if you have some memory issues, you have only to check the unsafe code. So that's the basic idea. And of course, more or less the last slide. We are on a supercomputing conference. How good is the scalability? So it supports SNP. It supports something like Rayon, which is comparable with OpenMP. In this case, I wrote a matrix-matrix multiplication based on complete Rust code and have more or less the same behavior than on the Linux system. We are working on to close the gap, but it's work in progress. But the current state is already very good. And that's it from my side. In principle, it's possible to write everything in Rust. So for me, it's Rust a good language for system software. Everything is accepted from the Rust community. So every change was what I'd done for the Rust standard library to support my library operating system. It's already accepted. It's already part of the Rust compiler. You have to install it on your system, and then you are able to build a unikernel. Nothing more. But it's based on the nightly version on the Rust compiler. No, it's not possible to use a stable version, but my experience with the nightly is very good. Normally it runs very well. Sometimes there's not the latest version available, but in general, I have a good opinion about the nightly branch. And that's from my side. Thank you.
Thanks, Stefan. It was a really interesting talk. Are there any questions for Stefan?
I have actually one question, Simon. Stefan, your Rust written unikernel, would you port applications that are written in different languages, let's say Go or C++? Is that feasible to do with the Rust core components, or do you see some issues there?
No, it's a problem. I have also still my my cross compiler for the old environment, and I will to replace only the library, so the static library from my old environment, and then you're able to run C++ code, and also Fortran in Go code. That's possible. But in this environment, I use still the lightweight IP stack. It's not realized to switch also to the Rust version of an IP stack. But in principle, it's possible.
Okay, good, fair enough. Then I have one comment, maybe, if no one else has a question so far.
Yeah.
Regarding your context switch, we face the same performance hit actually there. And what we noticed is that you have on x86 this xsave instruction, which does the saving of all these extended registers and SSE registers with one assembly instruction. Of course, takes some cycles. But we tend to do that always on each context switch, since that is cheaper than getting trapped by an interrupt, and then deciding or enabling that you need to save the context. And we got some performance back with that.
Yeah, maybe it's, so I use also the instruction, but but I used the guideline from the Intel manual, and they suggested to do it in this way. And this was the motivation to do it. I have no comparison difference to your solution. So maybe it's a solution to solve it, yes.
Okay. No more other questions? And thank you, Stefan. Really thank you a lot for your talk. It was really interesting.
Yeah, thank you.
And I hand over to Yanis, I think.
Yes, thanks, guys.
Thank you.
So, Yanni, are you there?
Yeah. Can you hear me?
So Yanis is the CTO of Reax Technologies. Reax is a startup which provides a data engineering platform that helps data teams deploy their data, manage and deploy a workflow, let's say. Yanis is going to talk about converging HPC, big data and cloud technologies as part of the Horizon project. So, Yanni, the floor is yours.
Perfect, thank you. Can you hear me fine?
Yes.
And can you see my slides?
Yes.
Perfect, okay. Thank you, Tassos, for the introduction. So hello, everyone. Thanks for staying up this late for this talk. So yeah, my name is Jan Georgiou. I work at Reax Technologies, and this work has been done in collaboration with my fellow co-authors coming from different organizations in Europe. I will name I will name the organizations, not every person, just to simplify. So we have HLRS, PSNC, and Cineca supercomputing centers. We have ICCS Research Center, and we have 3 SMEs, Linuxscale, UBTech, and Reax, that have collaborated for this work. So as Tassos mentioned, this is work done in the context of a European funded project. It's called Cibele, and I'm going to go into some details afterwards. Basically, I'm going to talk about convergence of HPC, big data, and cloud. And we're going to see some application on how this convergence, how these technologies can actually help in and simplify in the data analytics for precision agriculture when using supercomputers. Okay, so high performance computing has been traditionally used for scientific computing. The major focus has been performance, and that's why they have been leveraging supercomputers and specific techniques, parallel and distributed computing techniques. On the other side, we have seen the rise of big data analytics. Those technologies have been mainly used for data-driven modeling and analysis engines, and their focus has been more on to flexibility and simplicity of programming. And so they have been using cloud data centers with more elastic environments in order to extract valuable insights through those analytics. Now, the convergence of the two comes in of high performance computing and big data comes in an era where we are seeing a digital transformation in multiple industries. One of the major, let's say, advantages of cloud computing has been the elasticity, and that was
on some part due to containerization. And we are going to see in the following slides some of the adoption, how this can be adopted also in high performance computing. Now on another note, big data analytics can be applied in various industries, and some of them are related to agriculture and farming. We can see that high performance computing can benefit big data applications, since large data sets can be processed in faster and with better accuracy. And this is something that we are going to see how we put forward through this work and through the particular project. So combining the two can actually enable, the step forward of agriculture and farming, which is precision agriculture and precision livestock farming. However, even if we are interested in having this convergence, there is a fair complexity in using high performance computing. There is a steep learning curve, and there is a specific expertise to acquire. So traditional big data and cloud technologies such as containerization and orchestration are mainly used in these technologies and bring this elasticity, but they cannot be used by default out of the box in high performance computing due to security and performance issues. So workflows that combine big data and high performance computing executions are still an active research topic. Okay, so this is the outline of my presentation. I'm going to do a brief introduction of the Cibele project, the context upon this work has been done. I'm going to talk to you about the architecture, the prototype architecture that we have been working on, and we have provided to bring this HPC abstraction and to simplify the usage of HPC through cloud and big data technologies. We are going to see how big data and HPC can be combined together through meta-scheduling techniques using Kubernetes. We are going to go through some details about the environment deployment that we have selected to use based on Singularity. And finally, we are going to see some experiments regarding precision agriculture and how we can use some deep learning algorithms based on multi-GPU scaling and how they perform. And finally, some conclusions and perspectives. Okay, regarding the Cibele project, so it is an EU-funded project. We are 31 partners in this project, and the expertise spans on different domains. So as I mentioned, we have supercomputing centers, we have experts from the agriculture, from livestock farming, and also expertise within software development and system software stack expertise. So basically, in this project, what we aim is to revolutionize how agriculture, aquaculture, and livestock farming is done. We have different pilots, different demonstrators that bring their data through different type of sensors, satellites, drones, base station sensors, and once we have these big data sets, we transfer them on high performance computing test beds, and there is where the data analysis takes place. So so the combination of high performance computing, big data, AI analytics, and cloud computing is what brings forward let's say this improved way of dealing with agriculture, with precision agriculture and precision livestock farming. Okay, so as I mentioned, there are specific high-performance computing test beds collaborating in this project, and I will name PSNC, HLRS, Bull, and Sineca. So they bring their specific platforms. Some of them are production sites, some others are smaller and more dedicated, but they are all used in the context of the project, and they deploy the same architecture in order to deploy different workflows of precision agriculture data analytics. On the other side, we have 9 different pilots from the agriculture and farming domains. They all have specific characteristics, and they all have the interest of being more of having a lot of data, of having the need to be run faster or to provide further precision, so that they can improve either their time to markets or the specific business metrics. So based on the same, let's say, these same characteristics, they all have a benefit of executing high performance computing. I'm not going to go into the detail into exactly what they are doing. It's not the point of the talk, but what I wanted to mention here is that those, you know, on one side we have the HPC test beds, on the other side we have the pilots, and actually what we want to do here is we want to make HPC, high performance computing, more accessible, and improve and bring ways to improve those agri-tech data analytics in terms of speed and accuracy. Okay, so going more into the detail of and the context of the paper and the actual contributions. So we have been based on the let's say on the common architecture of typical production HPC systems, at least in Europe, and at least based on, you know, the specific ones that we have in the project. So they usually have a static combination of big data and HPC partitions. Okay, on one side they have a big data partition where they can run some data analytics, and they can have some Spark jobs or PyTorch, TensorFlow, this kind of libraries, and they use you know, orchestration and containerization. And on the other side they have the high performance computing partition where they use it you know, as with traditional programming models such as MPI, etc. So this is general, more static, and what we want to propose here is a more hybrid approach. So we bring a prototype architecture where hybrid big data HPC executions are possible, and this is done by having we're going to see in detail the architecture, but high view is that Kubernetes manages a VM-based big data partition on one side, and then on the other side you have Slurm or Torque. We use those resource managers to manage the bare metal HPC partitions. Okay, now containerization is possible on both sides. On the big data partitions we have both the possibility to use Docker or Singularity, whereas on the HPC partition, we are compliant on the typical usage of HPC production sites where some of them, or perhaps most of them, now are willing to use Singularity for containerization. So this simplifies the task of elasticity at some level. Now, data analytics applications can be executed on HPC partitions using the Kubernetes API, and this is done through a meta-scheduling technique based on WLM operator. This software developed by C Labs, the company that develops Singularity. Singularity CRI, again, this is the container runtime interface for Kubernetes based on Singularity. And the multi-user support so that Kubernetes communication can be done with Slurm and Torque. So I'm going to go into detail into that because this, let's say, one of the principal focus of the work. And another part is the environment deployment techniques, which are based on Singularity and a specific repository with pre-built images in order to deploy specific big data and AI frameworks and build new applications based on those images. Okay, so if we go a little bit into detail into the architecture, so as I mentioned, Slurm or Torque is the resource manager on the HPC side. So we are not interfering in any way on the typical usage of HPC. Okay, this is how the production is done today on most of the HPC systems. You have a resource manager and you manage your bare metal nodes. We see now that more and more people are interested in Singularity. We saw a talk earlier today about Podman. The most typical, one of the most traditional approach for containerization in HPC is Singularity. So we go with that approach. And so that's on the HPC side. On the big data side, there is where we bring, so of course, Kubernetes is a cloud-based orchestrator, but is used more and more for big data analytics. It has the support of different AI frameworks, and even Spark and Flink can now run with Kubernetes. So it's kind of a de facto standard for cloud, and it's becoming a de facto standard also for big data. Now, in that area, what we do is we provide the ability to have both Docker and Singularity. So we have different, we have some workers within the cluster of Kubernetes deploying Docker, and some others using Singularity. And this is because we want to deploy specific services, specific cloud services, and it was much simpler to use Docker rather than transforming in Singularity, even if it's pretty straightforward, but in some cases we had some issues. So so yeah, we have this separation here, and of course we go through the Singularity CRI, the Singularity Container Runtime Interface, in order to deploy on the nodes, on the workers where they have Singularity Runtime. So now if we combine the two, and this is where this WLM operator comes into play, the thing is that Kubernetes is going to be used as a meta scheduler for the workloads coming from outside, so for the applications to be run, and if a specific usage is done, then following this WLM operator integration, the specific application can be run through this communication protocol from the big data partition to the HPC partition. The application can be run directly on the HPC partition and being controlled by Slurm or Torque. Okay, so the submission is done by Kubernetes, but the actual control and submission on the HPC machine is done by the actual resource manager. Okay, so the Kubernetes just handles the job, let's say, to Slurm, and he does everything. So we do not interfere whatsoever in any way on the HPC side. Now I'm going to mention some of the characteristics of how this combination, let's say, works. But let's go on this next slide to see it in more detail. Now, as I said, the reason of having this combination of big data and HPC usage through Kubernetes is to be able to use a common API. So the Kubernetes API can now be used to submit jobs through one single API on both partitions. Okay. So following the same API, following kubectl, for those that know Kubernetes, you can submit jobs on both big data and HPC partition. Now, this allows to do a resource abstraction, to do an abstraction on the HPC side, and also allow us to do a further abstraction by providing some specific services, by deploying specific cloud services. So when I mention cloud services here, you can imagine a workflow manager, for example, or a visualization, or a database. So these type of services can be executed, can be deployed upon the big data partition, being controlled through Kubernetes, and then through them, the data scientists can build their workflows and can submit their jobs on both, using both big data and HPC partitions. Okay, so how this works? As I mentioned, on one side we have let's say a Kubernetes orchestration to provide an adapted runtime usage for both cloud services and data analytics on the big data partition. And this is through Docker container, Docker CRI, Singularity CRI, and also a specific, let's say, configuration where you have your scheduling based on labels and node selectors, so that to place, to allocate the right application, the right pods on the right resources. Now on the other side, we have the what I mentioned before, the Kubernetes common API, where it allows us to run executions on both big data and HPC partitions, and this is based on WLM operator software. So this is for the communication between Kubernetes and Slurm or Torque. So initially, WLM operator has been implemented for only for Slurm. We have done an extension to provide that for Torque. This is also reported in another paper. Another thing important in this architecture is that the Kubernetes worker that has the Singularity CRI needs to have the Slurm or Torque login capabilities. And this is what is going to enable this the execution of jobs directly from that worker. Okay, and then the technique is that there is an automated creation of virtual Kubernetes workers through the technique of virtual kubelet. So a specific virtual worker is deployed for each partition or each queue, if we talk Slurm or Torque terms. And based on that, then you can deploy, you can direct your pod on a specific partition. Now, the communication protocol is based on a gRPC proxy. This is per user, and this is what limits a little bit the technique, which is somehow limited only for one user for the whole system. And this is what we have extended in a way by providing a multi-user support in that area through a dynamic adaptation of the user context by automatically reconfiguring both the virtual kubelet and the gRPC proxy to enable this the execution isolation, to enable monitoring, accounting, file sharing, scheduling, and stuff like that, which were not possible through the basic WLM operator technique. Now, if we see it a little bit through the schema, the technique, as I mentioned, the specific worker, so you can see worker 3, yeah, I don't know if you can see my mouse here. Worker 3 has the Slorm torque login capabilities, and through that worker, we can, where we also have this gRPC proxy, we can divert our jobs to the Slorm controller. And as we see, we have the creation of virtual workers based on the partition. So the red partition here goes on the specific CPU partition here, whereas the blue one goes on the GPU partition beside that. Okay, so based on that, you can direct your executions on specific areas of the HPC partition. Now, this is a simple example of how batch execution can be done. So for those that know Slorm, you can, and also Kubernetes, you can quickly understand the combination that has been done here. So Slorm has a typical SBATS execution method, and actually what we see here is the SBATS being inserted within a YAML, and this is what we have. So it's a pretty straightforward way for those that are that know about Slorm, and those that know about Kubernetes, they can see that it is the typical YAML file. Okay, so based on that, you can use the Kubernetes APIs or through kubectl, for example, and submit your job. Okay, here I see that there is something missing, but anyway, the important part here is to see how close to SBATS is the final, let's say, YAML that we use to deploy Kubernetes, a job through Kubernetes for Slorm. Okay, and of course here, this is a very simple example. You can imagine that a more complex example, the one that I'm going to show afterwards, for example, using specific singularity containers can be done. There is the flexibility within the tool. Okay, going on the HPC environment deployment, as I mentioned, we have this environment deployment tool, which is based upon Singularity, and the goal here is to be able to provide environment definition, portability, and transparent usage of the available system resources, such as accelerators, interconnects, storage, etc. And to do that, we provide specific pre-built images that will be adapted on the, let's say, on the versions of the libraries of the hardware that we have, and also we aim to have pre-built images for AI and big data frameworks such as PyTorch, TensorFlow, Horovod, etc. For related also with the specific libraries coming from the system resources. the goal is to have a general purpose way of building those images so that they can be used within a specific data analytics context, so that data scientists can build their applications and they can execute them through these techniques. Okay, so let me skip this. So we have performed specific experiments using real-life precision agriculture application. The one that I'm going to show is about automatic identification. Sorry, I have a problem with my battery. Okay, sorry about that. A problem with my battery. Okay, yeah. So, and the goal here is to have specific data coming from sensors, basically images that will enable crop yield prediction and the counting of wheat ears. And based on that, you can inform decisions for sales planning, etc. This application consists in training a deep learning algorithm written in Python and PyTorch framework, and we have deployed it in a specific test bed, in a dedicated test bed with BullNova, which is part of a BullNova cluster, featuring a Bull Sequana machine equipped with a pretty powerful GPU. And also this is on the HPC side, and on the big data side, we had a simple virtual machine node with 4 CPUs and 8 GB of RAM. So to go fast on the results, basically it's just to show the interest that we have on passing from a typical, let's say, big data usage on a more high performance computing usage. So in both cases, we have used Singularity for the executions, and we can see a performance improvement on one side from the small VM to the full, let's say, GPU bare metal node of 100 times orders of magnitude, whereas the scaling of GPUs, we see 10 times orders of magnitude. So let me pass on the conclusions. We have proposed a prototype architecture for the execution of big data analytics upon supercomputers, and basically we provided ways to bring a convergence between big data, HPC, and cloud software stack, so that we can abstract and simplify the usage of HPC. We have used Kubernetes as a high-level orchestrator and common API to allow this deployment of data analytics as HPC jobs, and we also provide an environment deployment tool based on pre-built Singularity images and specific big data and AI frameworks. Now, these mechanisms are used as basic building blocks to enable this HPC abstraction, and also as the way to deploy those higher level cloud tools, so that data scientists can find a more friendly environment in order to execute their applications, build their applications, and run them. And the code is going to be made publicly available at the end of the project, so it's still ongoing work. And some perspectives We are going to propose different pre-built images for big data and AI frameworks to support various types of HPC hardware. As I mentioned, we are using for different supercomputer centers with heterogeneous hardware. So this is we have to adapt on those on the hardware that we have there, and we are going to perform end-to-end experiments combining the workflows of hybrid big data and HPC executions. We want to provide further optimizations in the multi-user support of the Kubernetes integration with Slurm and Torque, and some of the adaptations that can be done here can be related to the new Slurm REST API. Now, another part of the work which has not been detailed here, but it's still ongoing, it's towards the support of specialized big data frameworks, such as Spark. And with having Kubernetes as the resource management or the big data partition, we can deploy Spark applications on Slurm clusters through a specific technique where we do not interfere on the normal execution of HPC. We just use low priority jobs and best effort execution.
Yanis, I have to call in a little bit the time now, so you'll need to wrap it up because you're over time already, 5 minutes.
Perfect. I'm done. Thank you.
Any questions? Okay, if there are no questions, then again, thank you, Yanis. If there are no questions, then we'll move right on to Andreas Stockmeier, who is gonna present service function chaining in the network function virtualization arena, which may or may not come into play with new ways to link HPC centers. Not that there are too many. There are not too many CERNs out there who employ high rate links in the scale of the research networks, but maybe Andreas can tell us more what his MPLS service function chaining using SRIOV, that is, can potentially bring us. Thank you. It's about your turn now. Andreas, you can get started.
Sorry, wait a second. Just share my screen. Sorry, it's not quite working the way I intended it to. Really? Okay, I'm quite sorry. Zoom just crashed when I wanted to share my screen. I hope it's working now.
Yes, it does.
Working fine.
It's working? Fine. So, hello, my name is Andreas Stockmeier, former employee of the University of Tübingen, and I will present the service function chaining framework based on P4 and SRIOV. So first, I'll give a short overview about the principle of service function chaining, followed by a detailed instruction to our system. So first, I'll explain the motivation behind the system, followed by an overview of the components. I will then explain, of course, all the components in detail. So in traditional networks, all components are built in hardware and hardwired together. For example, an ingress switch is connected directly to a firewall, which is then connected to an IDS, and so on. So such a system, of course, is not very flexible and does not scale very well. To solve the scaling problem, network function virtualization is used, where hardware blocks are replaced by virtual functions built in software and running on commodity hardware. This not only allows us to scale better, but also reduces cost, since in most cases, open source software can be used in case of proprietary boxes. To solve the scaling problem on the network size, on the network path, we have to redesign the network. So we need one network where all functions are directly connected, and the whole forwarding has to be done in software. This also means all packets that arrive at an ingress need to be classified and then need to be assigned a path through the network that defines which functions they traverse and in which order. And so a service function system consists of 3 components. The classifier, which tags all ingress packets based on specific criteria. The operator can choose them freely. Most often 5 tuple matches are used. The service function forwarders, switches or routers that are able to read the tags attached to the packet and forward the packets to the next service function defined in those tags. The service functions themselves are just a piece of software running on commodity hardware and fulfilling a specific task. So for example, a firewall. How the packets are tagged depends on the type of service function chaining system. It can be realized using segment routing, so for example, SRv6 or MPLS, or it can be done using a special network service header like it's discussed in the IETF. Of course, there are many more options how to solve this, but those are the most common ones. Here we have a small example from RFC 8595, which is an RFC that defines a system where both types are used. So at the ingress, a packet gets a label for each service function it has to traverse and a context label with more information for this service function. So when the packet arrives at the ingress node, it's tagged based on a lookup table at a classifier. In this case, it has to traverse just 2 functions. It is then forwarded to the first service function forwarder, which has a look at the uppermost label and then forwards it to the first service function. If it returns for them from that service function, the label is popped. Service function forwarder A sees there's another label. It's not responsible for that one. So it moves, it forwards it to the second one, which then sends the packet to service function B. And from there, it's delivered to its final destination. So after we built a common understanding of service function chaining, we'll now continue with an in-depth explanation of our approach. So first, we'll start with the motivation. Why do we need yet another system if there are already so many in discussion at the IETF, most of them not even having a prototype yet? The main point is for those traditional service function chaining systems, we need a lot of special hardware, especially the classifier is a huge task if you want to achieve high throughput rates. To allow using this in a big network, we need a lot of fast storage. So for good classifiers, either they are expensive if they have enough fast storage, or they are slow. We don't want either of that. And it's not done with that, because then we still have the service function forwarders, which also depend on the system that's used. So there is no off-the-shelf hardware that allows using those systems at the moment. This all of this makes SFC only practical for large operators that are willing to invest a whole lot of money. With our system, we want to eliminate both of these problems. So we developed an all-in-one solution for classification, network management, and VNF orchestration. We use P4 for classification, MPLS for the forwarding plane, and libvirt and LXC for the VNFs. Just to keep in mind, using libvirt and LXC for the virtualization is just to make it easier to demonstrate it. The virtualization backend can be swapped easily at any time. This approach is built to use as much legacy hardware as possible in order to keep the system cost effective while still leveraging the full bandwidth available. So in fact, nearly everything that's present in a current data center can be used with our system and still achieve the best performance that's possible with the network components already present. So here we have the components of our system and a simple example data center. So all packets from the internet are delivered to a P4 ingress switch. And then for simplicity reasons, and because the slide is a little bit small, we only have one switch in our whole data center. Then we have 3 servers that run a whole bunch of VNFs and a single orchestrator that manages the whole data center. We start by explaining the most simple component in our system, forwarding plane. To allow utilization of legacy switches, our forwarding plane consists of plain MPLS label stacks. This approach is similar to the segment routing MPLS draft presented at the IETF. However, our MPLS labels do not need to contain additional information apart from the label ID. So this means we can use legacy hardware that can work with MPLS at line speed. The only operation a switch has to do is pop a label and forward a packet. We assign each VNF slot the servers and each networking hop a unique MPLS label. So basically we have a static network configuration where labels do not have to be changed once they're initially set up. The forwarding itself then can be done with any switch supporting MPLS. So basically every 100 gigabit switch that's on the market today can do this in line speed. Let's make a short example. We just randomly assigned our MPLS labels. We say the link between the ingress switch and the forwarder gets label 100. Then we say labels 101 to 110 are reserved for server 1, 111 to 120 for server 2, and 121 to 130 to server 3. And we have a packet that arrives at the ingress switch, and our matching says it has to go through VNF 1, 11, and 23. Therefore, the ingress switch now has to put a label stack on that packet that ensures the packet traverses all VNFs in the correct order. So the label stack consists of labels 100, 101, 111, 123, and 100 again. So just plain MPLS forwarding, label 100 tells the ingress switch, move it to the forwarder. Label is popped, therefore label 101 is now the uppermost label and the packet is forwarded to VNF 1. So after VNF 1 finished processing the packet, it is returned to the forwarder with label 111 now being the uppermost label, and the packet is forwarded to VNF 11. Same happens with label 123, which results in the packet being delivered to VNF 23. With now only label 100 left, the forwarder returns packet to the ingress switch, which then sees there is a packet coming from inside the SFC network, but having no labels. So therefore, all VNFs are processed, and it can be finally moved to its final destination. As we see, most of the load is already done by the ingress switch. The normal switches only have to do plain forwarding. Any incoming packet in our system is classified by its 5-tuple, consisting of source and destination IP, source and destination port, and the protocol. Each 5-tuple corresponds to a label stack in a lookup table, which is the crucial point with traditional classifiers. We implemented the prototype on a barefoot Tofino edge core switch. To keep the code small, we limit it to 10 MPLS labels per stack. This limit is just artificial. You can modify the code at any time to allow a greater amount. When using jumbo frames, of course, a much larger amount of labels per stack is possible. The Tofino is able to process packets and assign the label stacks fully in line speed of 100G. So there's a latency from far less than 1 millisecond and no slowdown. And since the upper limit of the MPLS labels is defined, we don't need any recirculation, which would lead to a decrease of performance. And last but not least, if we're using IPv4 and 10 MPLS labels, the Tofino Edge Core allows for up to 100,000 SFCs to be stored at the same time. So the space should be sufficient in this case. The third part of the system is the VNF integration. So in our demo, a VNF can either be deployed as a virtual machine or a container, but in practically it doesn't matter which virtualization technology we use. We just implemented it using libvirt and LXC because there are nice Python APIs for that. Deployment is solely managed by the orchestrator. Each server is a pool of MPLS labels directly aligned to the virtual functions of the network card, which can be assigned to newly deployed VNFs. So each virtual function is already linked to an MPLS label, and therefore we always know which MPLS label is assigned to which VNF. Each VNF gets the packets through a virtual function from the network card. This is done by using traditional VMDQ and SRIOV. So we have a deterministic and well-known label for each function, no matter where it's deployed. The forwarder sends a packet to VNF by just sending it to the server using the correct VLAN tag for the virtual function and waiting for the packet to come back. Inside the virtual function, we use the Linux MPLS router kernel module to handle the MPLS stack. The orchestrator acts as a central controller, managing all three parts of the system. SFC definitions can be done by the customer itself or an administrator by simply providing a list of functions and the order in which it should be traversed. The orchestrator then allocates the resources on the server and calculates the corresponding MPLS label stack. The orchestrator is also responsible for the whole network management. It configures the P4 switch whenever an SFC gets added, deleted, or modified by providing lookup table entries with the 5-tuple match and the correct label stack. It is also responsible to configure the forwarders, but this only has to be done at the initial startup or whenever the topology of the data center changes. So for example, adding new servers, failing of a node, and so on. In a normal data center, this is static and should change rarely, if ever. The last part the orchestrator has to take care of is the deployment of the VNFs. They can be either deployed as, in our case, as containers or virtual machines, and are allocated to a server with 3 resources based on computing power, memory, and storage needed. The orchestrator has an overview of all 3 resources over all servers and tries to leverage them as good as possible, including rearranging the VNFs if needed. Now coming to the prototype. The orchestrator prototype is written in Python. The configuration is for the SFCs is stored in a JSON file containing a list of the binaries that should be executed, the resources they need in terms of CPU cores, system memory, and storage, whether they should be implemented as container or VM, and the order in which they should be traversed for each SFC. This information then also can be used for billing purposes for customers. In a production-ready system, of course, this wouldn't be a list, but one need to write a nice web interface. The orchestrator provides a southbound interface to the Tofino to populate the lookup table. To deploy the VNFs, we use the libvirt and LXC APIs because we already had some, or we're already familiar with them, but this this can be changed with some lines of code if there's something that suits the operator more. The customer can provide own binaries for the VNFs on a public NFS share. These programs only need to follow some conventions, so they need to interface a TAN interface called TAN0, which accepts plain IPv4 packets and returns IPv4 packets. The VNF runs this program at boot up, forwards all ingress traffic to TAN0 after stripping all MPLS headers, and all packets coming from TAN0 get the corresponding MPLS header attached and are sent back to the forwarder. So in this work, we present a service function chaining system using plain MPLS segment routing. This may seem strange at the moment because MPLS label stacks can add a large overhead to a packet. But when keeping in mind that in the normal internet where packets come from, we have a fairly small MTU, while we can leverage jumbo frames in data centers, the size is not the main problem. The main advantage we have with MPLS label stacks and a static configuration is that we can always operate in line speed and therefore have no slowdowns on the network side. We tested it with 100G, but of course this was just the limit we had with our hardware. Basically, if we have a P4 switch that allows for 400G, it should be no problem either. So our system basically combines SDN with as much legacy hardware as possible while still remaining a high throughput. So if we already have a data center that has a high capacity, only a single, or depending on how much redundancy you want, 2 P4 switches need to be bought. Everything else can be done by whatever the data center already provides. So all of the modern switches with a high throughput already know MPLS, and we leverage commodity servers. So this makes the system very cost effective while still allowing for a good performance. We provide a demo orchestrator that takes care of managing the whole system. So managing all the servers, deploying the VNFs, managing the networks, and configuring the switch. Therefore, this is basically a full all-in-one system, but still keeps overhead at the bare minimum and only relies on well-tested and open source software. This concludes my talk. Questions, please.
Any questions?
I have one.
Sure.
Can you hear me?
Yep.
Yeah, my question is about what is the typical timing requirements you have in this forwarding plane, for example, for invocation of a single virtual function. So you say the virtual function in your prototype example was deployed as an LXC container with libvirt, etc. So what is the typical reaction time you need there to invoke such a function?
In our traditional networking cases, the reaction time is not that important. So a reaction time with 1 or 2 milliseconds is totally fine. And we reach around 1 millisecond when using SRLV inside a VM.
Okay, and do you need to resort into DPDK and stuff like that, or it's not needed?
That depends on the use case. There sure are some VNFs where DPDK would bring a great benefit, but DPDK itself is out of scope for this work. So we provide a backend where you can choose whatever virtualization technology you want to use. And we provide a demo with libvirt and LXC. But you're right, for some use cases, DPDK, of course, provides a way better experience. And it wouldn't be hard to implement it within our demo orchestrator.
And I had just a very minor curiosity about the packet size you used in the results you show on the paper, because I see in gigabits per second. That, what are the packet sizes here? Are these small packets or huge packets? Or
the 100 GB we used typical website traffic. So we tested it with packets starting from 100 byte to 1,400 byte payload.
Okay, thanks a lot. Thank you very much.
You're welcome.
Any more questions? Then last question maybe on the orchestrator. So this acts as a network admission control also. Is this correct?
The network admission is not directly part of the system. So basically, if we have a packet that's already, it's indirectly, if we have a packet that's forwarded to the ingress and there is no match, then the packet is dropped. So yeah, you can say it's a whitelist basically. Okay, this was the question already. Then again, thank you very much for the very good talk. Are you gonna, well, I know already. So that brings us to our next speaker, who is joining us from IBM Watson, where he is a member of the research staff, and his short summary is that he works at the intersection of AI, containers, HPC, and cloud infrastructure. Please join me in welcoming Silam from IBM Watson. Silam, please go ahead.
All right, so you can hear me, right?
Yes.
Okay.
But we cannot see you.
Oh, you cannot see me. All right.
Yep.
Let me put the video. Can you see
now
me?
We can see you, yes.
All right.
Very good.
It's actually a perfect time for me. I'm in New York. It's 6 p.m. I know for some people.
You shouldn't have said this in this round.
I am sorry. I'm sorry. But yeah. Hello, everyone. Thanks for the opportunity. I'm really excited to talk about this particular topic because I've been working on this for 5 years or so, and I have given this talk actually at a few other places. So I'm interested to hear actually what kind of questions you have and actually make it live discussion. So if you have questions, feel free to interrupt me. I won't take it offensive. As in the intro, as mentioned, I'm a research staff member at the TJ Watson Research Center. I'm one of the architects that actually built the IBM Kubernetes service, as well as the IBM Deep Learning as a Service, which is the underlying AI training service for the IBM Watson services. Currently, I focus more on the cloud infrastructure, where we are building HPC capabilities on top of IBM public cloud. So this is a culmination of a lot of observations I had over the years in building and managing and operating those services and scaling them. So I try to distill them into a few bullets. If you have questions, I'll be glad to go into more details in the talk. Okay. So with that, let me go to the outline. So when I got the invitation, I looked up the, actually I couldn't find the agenda, so I couldn't look up the agenda itself, but I did some queries and look at the past years. And what I found was actually a lot of the audience that come to this specific workshops are actually from HPC, high performance computing. So I thought I will start there actually. That's a good place to start because a lot of AI happening in the cloud is really some form of HPC in reality. the AI pieces haven't completely converted into more cloud native AI. So there is a mix of actually existing HPC, take it and put it in the public cloud, and then there is some transformation that's happening. So I'll start with the HPC infrastructure, and I'll try to juxtapose that with public cloud infrastructure and show you the critical differences across the entire stack, going from storage to network to compute to application stack. And that should give you a good sense for actually what are the critical differences. We'll look at what is the AI infrastructure that's available across the clouds. Well, I'm from IBM. I try to give a very fair view of the rest of the clouds so we can do a fair comparison. Then I want to get into really the critical challenges as I see them across the stack. As I said, in the software stack, the compute layer, the networking layer, and the storage layer. In particular, on the networking layer, I think the previous talk is a perfect segue, because I think that's one of the areas where cloud needs a substantial improvement still to make really large-scale AI more commodity. It is possible to do large-scale AI today, but it's mostly a stunt rather than everyday use, right? And then we'll get into some conclusions. I have a couple of projects which I can mention where we're doing some work in both the storage and the networking pieces, but it's not important. We go into those details depending on the time, right? So let's get into start with the place where you guys are very, very familiar with, probably the HPC side. So the left-hand side of this picture is actually an extremely traditional HPC cluster, right? So you typically start with some kind of a distributed file system deployed on some kind of fairly high performant storage, whether it's a single box storage or multi-node storage, but you have some kind of a distributed file system. I would like to say GPFS, but I'm sure there is Lustre and there are a bunch of other distributed file systems that are typically available in these kind of environments. And they're also connected through most often, more often than not, through some kind of an InfiniBand high performance network interface to the compute nodes. And the compute nodes themselves are typically connected through that kind of an interface. Compute nodes in really large scale systems tend to avoid having local disk or local persistence. But recently we started into using local disks as kind of a scratch space. So there is typically some kind of either SSD or NVMe, but that's really ephemeral kind of storage. And then you have an AI software stack and a job manager on the top. So you typically have your GPU, CUDA libraries, and things of that nature that are typically configured on all of these nodes. And you have a job manager, and as an end user, you deploy a job, and the job manager places on one of these compute nodes, and you go on computing, and you basically point, for your information, you point to the shared file system where you have the data, and the data gets read. You start computing, and if there is communication, that goes over this high performance interconnect. So there is nothing new on the left-hand side picture. But when you move to actually using cloud, and I don't know exactly how many people here actually use cloud to do any AI. If it is a live session, I could have asked it. You could raise your hand, but I have no way to do that now. But anyways, it's probably good to kind of start at the bottom, right? So when you move to cloud, there are people that actually try to take this kind of a system and put that into the cloud. It's never a good idea. It's neither scalable nor performant, and it's going to cost you a lot of money. The right way to actually do this is try to leverage the cloud native services. So if you go to cloud at the storage level, typically you get 3 or 4 different storage models, right? So the most popular one is the Cloud Object Store. If you have a lot of data and you want to keep the data for a long period of time at a cost-effective price, and in many cases actually high security, Cloud Object Store is the place, right? So many cloud providers provide bring your own key kind of mechanism. So that means once you put the data and you provide encrypt with that key, the provider doesn't have the key, so there is no way they can actually retrieve that information. And it's usually the cheapest model, not necessarily the high performing, but usually the cheapest. So typically when you start deep learning or machine learning with large amounts of data, the data movement actually goes from a distributed high-performant file system first into an object store. I'm not saying this is always the case, but this is the common pattern that we see, right? Then you also have block stores. I heard a noise. Is there a question or? Okay. I'll keep going until somebody raises their hand or something like that, right? Then you have block store, which tends to be more expensive than object store, but better performing. And not every cloud has a file store, but they're getting, and these file stores tend to be more NFS kind of file stores, so not necessarily really high performance distributed file systems. But you do have file stores, and the way to think about it is the volume is much bigger in object store, much cheaper, then followed by block stores, followed by file stores, and these could be interchanged in terms of their cost and performance characteristics. Also, a number of cases, and in fact, for deep learning AI kind of cases, you might actually deploy a custom file system using either locally attached storage or using one of these block stores that is more appropriate for your own particular AI environment. Okay? And those services that you have available in the cloud are typically connected through some kind of an Ethernet, right? So it's the InfiniBand kind of networking is still not pervasive in the cloud, and I doubt actually a lot of cloud providers are going to adopt that kind of a model, because the Ethernet, both bandwidth and latencies have substantially been increasing quite dramatically, and the new network protocols are allowing you to write actually low latency applications in the cloud just using an Ethernet kind of model. So you typically have these nodes connected over either a 10 gigabit, 100 gigabit, 25 gigabit, 80 gigabit, there is all over the place kind of networking. And then you have more often you have actually virtual machines. So the GPU capability that's available in the clouds very rarely is made available as bare metal. There is very few clouds that does bare metal deployment, but most often it's actually virtual machines. The bare metal part is kind of, is going back and forth in the spectrum, and you'll see that in a second. So once the capability is virtualized through VMs, and some, like in the Watson service, for example, we take this all the way into containers. So we deploy, I got some survey.
Actually, I wanted to ask a question because you had HPC Ethernet in there, and I actually made a poll out of it. So this goes to all the participants. So maybe we can cycle back to it later. Sorry for the interruption.
Oh, okay, no problem. I will say that, right? So you either deploy usually your machine learning, deep learning, AI training on these virtual machines, bare metal, or as I mentioned, containers, and then on top you'll get a job manager. So there is a substantial difference in depending on which cloud you are using, how you are using the AI models in those. You may be running, if you're, for example, go use a Watson service, you may be, your code is actually running inside a container, accessing a GPU that is itself is sitting on a VM, which in itself is sitting on a bare metal, and your data may be coming from an object store. There are cases where if you are using SageMaker, for example, there are cases where you're directly running on top of a VM, accessing the data either from an NVMe storage or an object store, so on and so forth. So that it increases the level of kind of depth in the software stack that you use to actually access the GPUs. And similar things happen for cross-node communication and so on, right? So hopefully that gives you a good idea on the comparison between on-prem systems and HPC. So let's take a quick second and take a look at, what does cloud mean? So the one another critical difference I would like to mention, when you look at an on-prem HPC system, this tends to be, and more often than not, tends to be a centralized location, right? Somewhere, either it's Summit or CR or Livermore Lab or something like that. There is one location most of the time where the system is located. When you think about cloud, you really have to think about it as a geographically distributed system. right? That's a very important point. So in the case, this is just an example from IBM Cloud. You can go to any cloud and usually look for Azure locations or IBM Cloud locations or Google locations, Google Cloud locations. You'll get a chart like this that shows you where the data centers are. Now, not all the data centers are the same. Not every data center has AI capabilities. Not every data center has GPUs. But typically, you'll get the list of these data centers where you have the AI capabilities. When you are providing these AI capabilities as a service, which we do as part of like Watson, then you are thinking not about how to orchestrate the workloads on a single data center, but actually across data centers, right? Because there is multiple reasons. One, your capacity can be aggregated if you orchestrate the workloads across data centers. There are cases where customers prefer running their services in, for example, European customers prefer running their services and data and keeping it in Europe. Americans like to keep it in the US. We also get reliability and availability by actually allowing customers to submit the jobs to a central queue and then deciding where we would run, either it's in the US or it's in the US South or US North, or depending on which geographic region we have. So when you think about job orchestration, scheduling, load balancing, traffic management, data replication, it's important to keep that. I'm sorry, I'm going to close this. It's important to keep that in mind. That is a key distinction between how workload orchestration and job management and optimizations that we typically do in HPC systems, right, is very, very different from what you have to do when you're thinking in a distributed cloud kind of model. Okay. So let's take a quick look at actually the AI capabilities available across the different cloud providers. So here I don't intend to go through the entire list. These slides will be available for you so you can take a look at them. But I list here AWS, GCE, Azure, IBM, Alibaba, another big cloud provider that's emerging, as well as Oracle Cloud. In fact, AWS actually has a capability called on metal. So I should have add that. But what you see, the common trend is actually the GPUs. It looks like the entire public cloud is actually standardizing around 8 GPU form factor, which is where IBM Cloud will be going soon. But I can't yet say that until we really have that. We have a 4K80 2V100 GPU nodes, bare metal and VMs. Same thing with Oracle Cloud and AWS. But you also get GPUs through VMs as well as containers. So you can deploy a container service in some of these clouds, and you can request GPU nodes and GPUs associated with those containers. And in many of those cases, those containers and GPUs are actually coming from a virtual machine, which it itself is running on a bare metal. On the networking, so that's on the compute front. On the networking front, it is really a jigsaw puzzle, right? So you anywhere from 10 gigabit network, which is a pretty big increase, to 30, 20, 25, or dual 25 gigabit networks. I expect very soon these nodes will be more close to 100 gigabits, but that's kind of where we are, right? So you don't see any real InfiniBand kind of networking in this. And then the storage, they are all comparable in one way or the other. Typically, they all provide some kind of an object store, all provide some kind of a block store. They call them differently, and a file store, and host attached storage. What we are noticing is the industry is actually getting standardized around the storage called NVMe. There are some older deployments with SSDs, but we see actually a lot of movement around whether it's host attached NVMe or actually network attached NVMe. That's where the industry is going. Okay. So let me just quickly go through, given these, the stack and the comparison, I'll just quickly cover what are some of the challenges for AI in the cloud across software and compute and network and storage. And I'll try to make this a little quick because I feel I'm running a little behind. So as I said, the first challenge, and actually for a number of people that run AI training on-prem, is actually the shocking combination of bare metals, virtual machines, and containers that you get on the cloud. And has both pros and cons, right? So if you have, bare metal configurations tend to get more complicated. If you have virtual machine, you could then customize the execution environment for the particular user if they need TensorFlow or Caffe or one version of libraries or another. Something similar with containers as well. So that flexibility you will get a lot, but then you're going through multiple layers of virtualization that may cost in terms of communication performance and so on. When we started actually this journey about 3 years ago with the Watson services, the accelerator support in containers was actually abysmal. At that time, GPUs were not supported by Kubernetes. There was minimal support for GPUs even in Docker. There is a NVIDIA Docker that was kind of in the alpha state. But over a period of time, that has gotten better. But still there is more work to be done. Topology aware scheduling and things like that are still missing. And some of the accelerators, like if you have FPGAs or if you have InfiniBand networking, things like that, there is still some gaps in that space. So as I mentioned, the topology aware scheduling and placement, when I talk about topology here, I'm not talking about topology on a particular system with 8 GPUs and how do you place the task so that it uses the GPU that is attached to a particular NUMA node, but this is actually topology at a data center level, right? So when you want to run a large scale deep learning service, you need constructs like placement groups, which enable the cloud provider to place your tasks in the closest possible set of racks, right? So because if you go ask for 10 nodes worth of either GPU or non-GPU nodes, if you do that one at a time, typically they get placed all over the place in the data center. And as I said, they could be in a multi-zone region, which means they could be actually in multiple physically different data centers, or they could be in a single zone, but even within the zone, there may be hundreds of racks and they're all over the place. So you need constructs like placement groups, data center aware scheduling. This is getting matured. Almost every cloud provider is actually providing constructs like these, but it's still not to the point where it's universally available, right? On the networking side, the unified and high bandwidth networking between containers, VMs, and bare metal, there is still a lot of gap in the kind of performance that you can get when you're inside a container versus inside a VM versus a bare metal. And it is also a function of how your workload might perform. I'll show you an example where if you're in a VM and you knew actually you're in a VM, you could do optimizations that actually enable you to exploit the underlying hardware fully than if you are actually running in a bare metal, right? Also HPC-like scheduling. HPC is known to have this kind of gang scheduling, for instance, and those facilities are still lacking, especially more so on the containers than in the VM-based clouds. So on the compute side, I think if you have done any AI training, you would realize in a lot of the cases, actually the GPUs are getting more and more powerful, but the computation don't always need the entire GPU. There is a lot of cases, both for training and inference. We have examples where we know for sure we need only a third of the GPU or a fourth of the GPU, but you cannot place multiple untrusted customers on the same GPU. And that resulted in a huge amount of GPU underutilization. So GPU virtualization has been a hot topic for a long time. And finally, it looks like NVIDIA is going to support GPU virtualization with the A100. Again, the devil is in the detail. So we need to see how efficient this virtualization is going to be and how end customers can actually exploit it. But that's actually a good step in the right direction. GPU pass-through, again, so many of you probably know the NVIDIA GPUs are connected through this interface called NVLink, and that is an NVLink between GPUs. And in fact, on IBM power systems, we also have NVLink between the GPU and the CPU. And those links sometimes make it hard actually to do a pass-through of GPUs into virtual machines, especially when you want to carve those GPUs out into one GPU per VM or 2 GPUs per VM. 3 or 4, those links are hard to break, and as a result, so you will not be able to do that in a safe fashion. If you actually go to AWS, you get 1, 4, or 8, and there is a reason for that. Then on the flexible GPU partition, again, as I mentioned, this partitioning of this capability is really important. In the case of containers, really first-class support for GPUs in the container runtime system. It's getting better, but I think there is more work that needs to be done. There is quite a bit of work going on in the GPU space to be able to transfer data from the GPU directly into the, from the storage directly into the GPU and the other way. But exploiting this across actually VMs and containers is still in the early phases. That's another area where I think some work is needed actually, so that GPUs and storage can communicate directly, especially storage like NVMe storage, and avoid passing through the CPU. On the networking front, as I mentioned, I will not repeat this again, but it's important that we think about actually how cross data center networking, data center aware networking is really important in being able to schedule large scale deep learning training jobs on the cloud systems. I also mentioned that on the QoS and SLA enforcement at the fabric, actually the talk before me was a perfect segue. What we find is actually there is different levels of QoS SLA enforcement at the fabric. When I say fabric, network fabric, that results in actually a lot of interference if you are running high throughput jobs in the cloud fabric. Right? So if you don't have proper QoS enforcement, you may be traversing on the same paths, and then your traffic is interfering with other traffic, and that results in not in interference at the GPU or the compute level, but actually interference at the network level, and that shows up in how well you can scale. The isolation of that traffic from the compute traffic as well as the network traffic and IO traffic is really important at the fabric. Another thing is, as I mentioned, obviously you can do a large scale GPU training or large scale AI training on the on-prem infrastructure where you have this kind of dedicated networking. But think of cloud as a massive multi-tenant environment. So that means you're chopping that environment up and giving up to many, many users. So you don't necessarily want to have actually the same kind of InfiniBand rigid networking that's available in the on-prem systems. So if you look at Amazon, for example, there is a nice work that they are doing on reliable datagram kind of protocols, where you make the networking more reliable, but also deliver low latency, high bandwidth. I think there is innovation there that needs to be done at the networking substrate to actually deliver high bandwidth, low latency networking by redefining some of our networking protocols. On the storage side, the real challenges are actually orchestration, data orchestration. As I mentioned, in the on-prem case, you typically put the data in a shared file system and you're done, basically. And if you're running at a scale where you're not able to, the shared file system is not able to deliver the performance, you might use a cache and you cache the data and then you can go from there. But in the cloud case, as I said, typically your data is likely in the object store. So you need to have an efficient orchestration that gets the data from object store into some kind of an intermediary store and then feeds the data into the GPUs. And when you do that, now you have two levels of data orchestration, and you have to worry about the life cycle of the data, security, compliance, regulation, and so on. So that is what motivates actually this kind of work in high performance multi-tenant caching with the appropriate security and life cycle. And the last time I spoke to at the supercomputing, almost every national lab in the US has actually a project on how to do caching for AI. So you will find plenty of papers on actually looking at this problem. Even in those cases, the perfect way to actually cache is not use another layer of storage servers, but actually cache it using host attached storage. So there is a lot of emphasis and work going on in the cloud provider space to provide like NVMe as a host attached storage, be it ephemeral, and then provide that either a local file system on NVMe that provides the cache, or actually deploy a distributed file system on there. Of course, securing that data and orchestrating that data between on-prem, edge, and the public cloud is another challenge for storage for the AI in the cloud. Obviously, you won't have AI without data. Right? data locality aware scheduling and workload orchestration, this is another important aspect. So once you, when you are running a service, like a Watson service, for example, an end user may be deploying the same job hundreds of times, right? If you're doing hyperparameter tuning or you're doing other kinds of space exploration, you will be running the same job many, many times. But from a scheduler perspective, every new job is a different job. So it actually schedules that job on any node that's available. But if you are dealing with a lot of data that was already cached, you really want to get to a point where you are now scheduling based on data locality, not necessarily based on the available free resource. So with that, I will kind of pause. I think I have only 1 minute, so I'll pause. There is some more material on kind of the NVMe information here and some data caching work we have done, but I'll pause there and get to my conclusion. So in summary, what I want to say is there is significant differences in infrastructure capabilities and software stack across HPC and public clouds, whether it's from file systems or interconnects or disk or just the pure compute. The challenges span across software, compute, and network. And I think the work that's happening around the storage and the networking are getting to a point where we could do large scale AI in the public cloud, but there is a ton more work that is left to be done. And hopefully I gave you some ideas on some of the challenges. I'll pause there. Any questions?
Oh, hi, this is a very nice overview. Thank you for that. I was wondering that whether you can elaborate on the S3FS. I noticed in your comparison that seems the IBM is the only one listing that capability there.
Yeah, I mean, S3FS in general is available, right? So what we did was once that capability is enabled, it's actually open sourced. You can use it on other cloud providers. We haven't gone and actually done any kind of significant analysis with S3FS on AWS or anything like that. The APIs IBM Cloud has is S3 API. So, so the analysis there was just, if you are for people that don't know what S3FS is. So S3FS makes the object store objects look like files within your system, but you uses a caching mechanism. So when the first time you touch the object, it'll actually automatically cache that object in the local memory, either local memory or local disk. And then over a period of time, it will push those objects back into the object store. So it provides a nice way to cache the objects, but obviously your mileage may vary, right? The performance you get is only the performance of the object store. An object store is not built to access random files, random access to files with a very high performance. Does that answer your question?
Oh, yes, absolutely. Yeah. And we are interested in S3FS mostly because of the near infinite scalability.
Yeah, absolutely.
Yeah.
So if you're dealing with a little bit of data, S3FS is the right way. So you don't need to maintain another layer of storage.
Yeah. Thank you.
Any more questions? Any more questions?
Wow, I'm either clear or I put everybody to sleep.
No. This very good, and you touched on quite a few of the dimensions in there for learning. If you do it beyond what you called a stunt on a large scale, so I think it's a very healthy and refreshing notion on that it needs some normalization towards making it repetitive on a large scale rather than the one-time thing. One question on the distributed file system versus object storage. So obviously caching you mentioned quite a few times. GPFS was also looking at the word frequency, mentioned it quite a few times now. GPFS has got this AFM facility. Do you see this in the cloud context as the way forward, or is there something else maybe?
I think it is one, right? It's going to be a collection. I think it's one. It has its own challenges in how you deploy GPFS. We in fact support GPFS on AWS right now. And there is work going on in my team to look at this from an IBM cloud perspective. And AFM is certainly one, but I think there is more. It's not going to be just that.
Okay. Any other questions? We're already over. But yes?
I have one very quick one. I'm curious to know about whether you see just this big push towards having, let's say, bigger and bigger computation. So let's say increasing more and more the throughput in cloud systems, or do you see a market and the requirement also of people requiring low latency, even for relatively small tasks? So low latency is also a form of high performance, but you need different mechanisms normally to just get really low latency and predictability generally within a single machine and within a data center.
Yeah, I'm seeing both actually, right? Obviously, it's going to be somewhat business driven, what workloads where the cloud provider is making the revenue, and that's going to dictate how they evolve. But there is a significant improvement in actually the throughput and latency characteristics of what you can get from clouds. If you take 10 years ago and today, I would say there is substantial increase, and it's going to continue to get better.
Yeah, exactly. So, for example, DynamoDB is one of a few database systems which has a model that is focused greatly on the guaranteed performance, like on booked performance. But I'm not sure how much the model is really being pushed by other cloud providers.
Yep, absolutely. I think again, it's a function of I think the demand. It's a true market, right? This is not like the DOE-HPC where government is funding and so we can build whatever kind of system we want to build. This is going to be dictated by what the industry needs, what the customers need.
Thanks a lot. Great talk.
Yep, thanks a lot.
Great talk also. Silam, thank you very much. And we move on to our next and final talk, which is actually a brief lightning talk. We have Sergio Inserte from UGI, who will talk about GPU scheduling, a thorny topic, and we look for all the answers. Just to introduce Sergio, he's a postdoc at Multiphase Fluids Research Group at UGI Spain. He's interested in HPC workload characterization and machine learning for industrial applications. Sergio, please go ahead.
Hi, I'll share the screen. Okay, share.
Please share your video also because.
Yeah, okay.
Very good.
Now
we can see you, yes. And your screen, yes. All good.
Okay. Okay. Hello, everybody, and thanks for attending this talk. I also like to thank the committee for counting on me to give the last talk of this fantastic workshop. It is an honor. And special thanks to those staying late at night. I promise to try keeping you awake during the next 15 minutes. Let's start. I'm Sergio Inserte from UT in Spain, and I'll present a mechanism for managing GPUs in cloud environments named GSAS, that stands for GPU Scheduling as a Service. This work was published in the AIII Access Journal on July 2018 in a collaboration with our colleagues from the University of Valencia in Spain. OpenStack is a well-known cloud infrastructure that can be used to provide private, public, or hybrid IaaS. It relies on a set of logical elements named shared services, such as, for instance, scheduler, networking, compute, or image manager. Each one of these elements is implemented as a set of distributed components that exchange information. Several efforts to include GPUs in OpenStack architecture has been made. For instance, deploying virtual machine with access to GPUs via PCI pass-through. In this research, we combine a series of existing technologies in order to cloudify GPUs in OpenStack. GSAS is a shared service for OpenStack, which provides the necessary logic between the cloud infrastructure and the GPU in order to deploy could-enable virtual machines. GPU scheduling as a service is responsible for the management and assignation of GPUs to the virtual machines. From a bottom-up approach, here I present the technologies that allow the cloudification of a physical GPU. The first of them is AirCUDA, which provides remote access to the GPU from any host. With more detail, as we can see in this scheme, AirCUDA logically detaches GPUs from their host and makes them accessible through the network by any node in the cluster. Then ROTVR provides a dedicated GPU network and security of access to the GPU via IP masking. The resource mesh is responsible for scheduling and assigning GPUs to the virtual machines. These two key components are the core of GSAS. Finally, OpenStack deploys the CUDA-enabled virtual machines with cloudified GPUs. This scheme shows the interaction among GSAS components. Here we have two nodes for OpenStack where GSAS runs, and 4 compute nodes. Among the compute nodes, we find 3 different roles. Compute GPUs, where the physical GPUs are hosted. Compute Air GPUs, they are nodes with remote access to the GPUs, and compute nodes non-related to GPUs. Unlike the other roles, this kind of nodes cannot deploy CUDA-enabled virtual machines. These kind of nodes are only for regular virtual machines. Notice that compute hosting GPUs run AirCUDA, the AirCUDA daemon in order to provide remote access to the GPUs. Furthermore, compute related to the GPUs, the compute Air GPUs, are connected to a GPU dedicated network thanks to ROTVR ports, as we can see in the scheme. Okay, continuing with the previous scheme, we find that GSAS provides 4 ways to enable GPU computation in virtual machines. These working modes can be grouped twofold. On the one hand, to remote and to local, and on the other, to shared and to exclusive. Let's describe the remote exclusive, the first one. In this mode, cloudified GPUs are assigned to virtual machines running on different hosts. Similarly, remote share means that several virtual machines, no matter where they are hosted, can use the same cloudified GPU. Regarding local modes, the first one is local exclusive and deploys virtual in the node where the GPUs are physically hosted. And finally, the local share is the same that the previous one, but a cloudified GPU can be shared among different virtual machines in the host node. Here, we have the activity diagram of the process of launching GPU-enabled virtual machines. The process is composed of 3 stages. Firstly, the request, where the resource manager determines if it is possible to satisfy the requirements. If there aren't enough GPU resources, the request is aborted. Then GPU resources are pre-allocated, and OpenStack creates and activates the virtual machines. Finally, and concurrently, cloudified GPUs are created with the requested configuration and the cloudified GPUs are attached to the virtual machines. For instance, this command shows how we can launch a virtual machine, deploy it in the GPU compute. In the GPU compute, it means locally where the GPUs are hosted. The virtual machine has attached 8 cloudified GPUs of 4 gigabytes of memory each one, and with shared utilization. We have evaluated our prototype with a test bed of 5 nodes and 3 switches, 10 gigabit Ethernet switches. One of the nodes, the front end, has installed OpenStack with Jesus and Ercuda. The remaining 4 nodes are compute nodes. Concretely, three of them, these 3 compute, are ready for deploying CUDA-enabled virtual machines, while the last hosts 4 GPUs, which can be cloudified. In fact, they will be cloudified. Furthermore, in order to reduce the workload, this node has been excluded from the list of nodes that can deploy virtual machines. So it acts like a pool of GPUs. When it comes to the virtual machines deployment time, we have distributed the GPU memory in order to assign up to 75 cloudified GPUs to a single virtual machine. Results show that virtual machine boot time is not affected by Jesus until we assign more than 62 cloudified GPUs. As we've seen before, Jesus methods run concurrently to OpenStack actions because the boot time is affected because this time is ruled by the first and second stage times, the GPU check-in time, the initial check-in, and the virtual machine configuration time, plus the maximum of the concurrent processes in the third stage, the deployment time of the virtual machine and the Jesus management. Another application we've evaluated is MQDA-Meme. MQDA-Meme is a distributed application for motif discovery in biological sequences. Although MQDA-Meme can only use 1 GPU per MPI process, thanks to cloudification, GPUs can be shared among the MPI processes, allowing the spawning of more than 4 processes, originally corresponding to the 4 available physical GPUs in the setup. Apart from that, we have deployed 2 different scenarios. One, the intranode one, it's one virtual machine with 12 cloudified GPUs, and the internode scenario that with 12 virtual machines with one cloudified GPU each one. We can see how the time decreases as the number of processes increases, so it scales. And notice that the internode scenario performs better, assumably because virtual machines are deployed in 3 different compute nodes, so the workload is distributed. In this case, we've assigned 1 gigabyte of memory to each cloudified GPU. So in conclusion, Jesus allows us to automatically orchestrate the adaptive assignation of GPUs to the virtual machines. They provide GPU access security via IP masking, and a dedicated network for the GPU traffic, isolating the virtual machine expected traffic. Sharing GPUs provides versatility and can increase the performance of some type of jobs. But the final conclusion is that communication networks are crucial for the use of this kind of technologies. So thank you. You have any question?
Any questions?
Hello, I have a question. No matter if it is local shared or remote shared, with what metric you decide that this GPU can be shared among processes, RAMs, whatever?
Okay, do you mean that the scheduling of the resources to the job?
Yeah.
Okay, we have implemented for policies. We have the one best performing is the last fit. It tries to reduce the fragmentation of the memory of the GPUs. It's like the GPU. It's what rules the scheduling in this case. So we are trying to reduce that fragmentation.
Okay, and in the case that say one application that runs on GPU use small portion of memory, and on the other hand use all SMs on GPU, what happens there?
Okay, you mean that you request less memory than you really need?
Yeah.
Okay, good question.
But you ask for a whole computation with a small memory footprint.
Yeah. Okay, in this version, what I'm presenting right now, it will crash. But during the ISC, a new version of Ercuda has been presented, and it has controls of the memory of the application. So in that case, the job wouldn't crash. Yeah.
Okay, thank you.
You're welcome.
I have also a question.
Yeah.
Hi. So thanks for the presentation. That was quite interesting. And my question is about the data movimentation, because as you mentioned, the critical point of the whole system is the networking bandwidth towards the moving data. And specifically, as far as I know, typically in GPU workloads, your application tends to fetch data from some places, bring it locally here, and then it will try to offload to the GPU the computations, for after, of course, moving data in the, your Good copy, etc. But the key point is that typically the computations tend to move data first locally on my physical host, and then start the GPU task. Now, the problem is if the GPU is not here, but is a remote GPU, then it's probably a waste of time. I mean, do you have any optimization that allows you to just, move data where it's actually needed finally in the GPU, or I don't know if there's anything like that?
Well, Ercuda is implemented over InfiniBand, so you can use all the semantics of InfiniBand, and RDMA, for instance, if you mean that. Regarding
you mean for
optimization,
high performance movimentation, yeah.
Yeah. Everything implemented in InfiniBand, you can use it in GSAS.
Okay, I was actually wondering about whether you could some way, if you need to fetch, for example, time series data and from a storage, and it's a remote storage, so you fetch data remotely to your virtual machine where you're orchestrating the computation, but then your virtual machine sends the computation to the GPU that is actually a remote GPU. So basically you're moving data multiple times, and probably you could save something by just, I don't know, some way orchestrating the data movimentation. But that's only applies if you can do straight some GPU kernel computations without additional processing, etc. Of course. So
no, yeah, you get the point. These kind of technologies, yeah, are really network dependent, and also there are applications that has execution patterns that are not really friendly with this kind of remote-leadness. Okay. So an application that could leverage this technology could be applications with maybe with just with few transfer of data and long stages of computation. But if you have maybe a series of data, I'm not sure if it would work as expected. I mean, the overhead would be high.
Yeah, sure. Okay, thank you. Is this all open source, this modification to OpenStack, this new component, the G?
Yeah, it's open source.
Cool. Thank you. It's very interesting.
Thank you.
And the last question from me. If I remember, at least 2 years ago, Arcuda was working only with InfiniBand, or it supports also, say, Ethernet, Omnipath, whatever?
Okay. Well, as far as I know, it started with supporting InfiniBand, but also Ethernet, not Omnipath. And right now, I think that maybe, I mean, Ethernet, it supports Ethernet for sure, because it's this version. And I'm pretty sure that InfiniBand also, but not Omnipath, if you mean that.
Yeah, I know for InfiniBand because I used Arcuda.
Ah, okay.
In the past, I don't know if it supports generic network interfaces.
Yeah, I can say that Ethernet, it works over Ethernet.
Okay.
Thanks. At least this version. I don't know if newer versions have dismissed Ethernet.
Okay, thank you.
You're welcome.
Okay, let's give them the hour, unless there's very last question. Anybody?
Okay.
One more? No. Okay, then thank you, Sergio, very much for this talk, and we move to our panel discussion now, whereby we have to reconfigure ourselves a little bit in terms of mode. We've got a bunch of panelists and we've got a bunch of attendees left at this hour, which is actually quite surprising given the hour. Now, usually as the way it works is that there are a couple of discussion topics, and then the panelists, they get thrown at with topics, and then the panelists answer as good as they can, and sometimes there's some interaction between the panelists and sometimes to the audience. Now, given the electronic form, we can maybe pull the two together a little bit. That is suggesting here to pull the attendees into the panel and to make this discussion as much as Zoom allows us to do. Now, we've identified two starting discussion points. Why only two? Because it's almost 1 o'clock Central European time. Now, these 2 points are, and again, this is just the suggested points. We can drift one way or the other, or add one or delete one. One would be that we expand a little bit on the pipeline side of things from David before, where the hacking point is where do you stop with Kubernetes from a hands-on perspective. So what's the practical? It doesn't economize anymore to podify things and to make it Kubernetes clean. And on the second side, Tassos, do you want to expand?
Sure. Yes. So on the unikernel point, the main question is, since it is an academic project still, there is no real product based on unikernels, as far as I know. So one of the topics could be, what do we need to, what is still missing from the unikernel ecosystem to be released as a product, to be useful for the enterprise, for HPC, for stuff like that.
So let's start with this maybe right away. And I'm looking at Stefan Lankes and Simon here. To the provocative point is out. So it's nice, it's fast. Build up, tear down, it's fast. But what do we make out of it? Please go ahead. Yes.
So maybe from the Unicraft project side, we see actually that issues since a while, that it was more research in the past, and we also were thinking that you know, for getting an adoption, you need to go a bit more the enterprise path, or however you want to call it. And this was for us at least a reason to get a bit more serious about that, and started as an Linux Foundation open source project. And also to get more companies also on board, because you need to start at some point with something, right? And need to find your partners and make the thing more attractive. I think it's a bit in a difficulty that it is an OS, and people really don't care overall about OSs. And OSs are free. So you need to make traction and also make it easy for people to use it. So this is also one reason why we try to get existing software also running on it, right?
Okay, so do you think that that the serverless hype could help unikernels to get a boost on this context?
So I think unikernels are definitely a right fit for that use case. It's yes, more meta. Who is putting the engineers to maintain and develop the unikernels for that, right?
Yeah, I'm quite curious that Amazon, who is the leading the provider of AWS Lambda, is not working with unikernels, and they are still working with the Linux kernel offering the AWS Lambdas.
Yes.
I'm really curious why they do that.
Yeah, this is, I think it's a good question, but I think this is a lot of business behind and money, and where is the actual pain point, and how much is visible to the customer, and do they really have an issue with the security, or let's say they don't care, maybe, right? So maybe the pain point is something else, and it also, of course, so far, and this is what we're trying to change, there's no open source unikernel project that you can just pick and is major enough to support all the cases. So that also needs to be built up first.
Yes, I agree.
Would there be any HPC code or part thereof probably which would have some affinity to unikernelize some lightweight something operation which could be abstracted into it and would fit the lifespan of a unikernel?
So maybe Stefan can answer that. What I think is the big problem of unikernels were so far in general that they more or less were throwaways, that you developed it once for your specific application. And then you had the next application, since you start specializing or just implementing the things that the application needs, start doing the whole task again from scratch. Or you have this, we had in the past a couple of times this question of your unikernel runs now in Zen, but I have a KVM in my infrastructure. Can you provide me a KVM image? And then you start from scratch again. So and I think probably a similar thing is happening, or is also problematic for HPC, because you're also working with hardware accelerators, which need different drivers and so forth. And you may want to build an unikernel for your environment, but it doesn't necessarily run then on another HPC data center, something like that, because maybe different accelerators are used and so forth. And we think, but this is like, you know, this the idea behind the Unicraft project so far is the only way to get out of that trap, more or less, is to build a basis where people can contribute back their ports or pieces of ports, in our case, in terms of libraries, so that newcomers don't have to re-implement the whole ecosystem and maybe start with one library, and then that's the only gap they have to do.
A little bit more practical. What let's say a typical pattern is scatter, gather, and let's HPC it and say every single one is claims about 200 gig memory, and there is one lagging one, and they all come together in an MPI barrier operation, and they all hang in their OS and taking all this memory. Some things like this, putting them into this smaller something, and tearing them down as soon as possible. Just trying to.
I think for HPC, you're right. Just minimizing the kernel layers, just for the sake of the memory footprint, probably doesn't matter that much in that space. That matters maybe for IoT and other use cases. But what matters here more is you want to reduce the noise that comes from your operating system, because you want to have control over what the kernel is doing, but besides and interrupting your compute task. You want to be as close as possible to your hardware, so you can avoid system calls and turn it into function calls and shorten stacks there. I think these points are much more important, at least for the HPC space, than speaking just about smaller images.
You're onto something. OS noise matters, and so you have some things to go for. Yes, you do.
If I can make a comment, there's been also quite a lot of effort in the Linux community to reduce the OS noise when possible. So as far as I know, there's been in the last decade quite a lot of work on the isol CPU's boot parameter, for example, for trying to leave you some CPUs isolated so that they could get as little OS noise as possible while still being able to run user space applications. So that's stuff typically thought for HPC, so I'm not sure how much the OS noise is still really so much. I mean, if it's still the kernel noise, or if it's matter like, you know, a bloatware OS distribution that is the real problem. You know, where you start thousands of services that you don't really need just because you like to install a standard distribution. And that's really, you know, creates a lot of unneeded software that is running, and a lot of unneeded processes that are running besides your HPC workload.
Yes, and needs to be maintained, right?
And yeah, that needs to be maintained.
So I think the other plus is that you have full control over the stack, much more on the fine-grained side. On the other side could be also scary also, because you start to deal with really low-level details and need to decide what goes in and what goes out. But yeah, with this scheduling example, right? With these highly flexible unikernels, you can really build them without even provide them a scheduler, or take a scheduler that fits best to the workload. Maybe it's a cooperative one that you want, so that the application logic is doing the thread switch, and you don't have anything else there then anymore running in that space. So no timer interrupt to do the preemption or something like that.
Yeah, the scheduler element is being one of the components where the community is particularly sensitive, because it's so performance critical. So also while doing research on, you know, for several years on different, you know, real-time CPU scheduler, especially deadline-based scheduling for the Linux kernel, any approach barely based on the idea of a dynamically loadable kernel module integrating a scheduler was already like not good, because, you know, it's not really very compact, integrated in a very compact way into the rest of the memory layout when you boot up the kernel. So for example, that piece of the picture, the CPU scheduler, has always remained something that is statically compiled into the kernel. There's no way to make it really, you know, modular, dynamically modular. IO scheduler, for example, is kind of different.
Yep. I'm sure if you then take a unikernel, you can get that control back, right?
It would be cool, for example, if you just need our deadline scheduler, that's the stuff we've been pushed into the main kernel, the sched deadline, then you could actually perhaps, like, you know, extrapolate only that piece of software. But I mean, I know it's very complex, that part of the code, but you could actually use only the scheduler, and, you know, just forget about all the other stuff you have on, or the other scheduling policies you normally would have on a Linux OS.
Right. It's also from the NFV perspective, what also works quite well there is run to completion, right? You get your packets, you process them until you're done before you're touching the next ones. And that it's also quite beneficial if you don't get interrupted while you're doing the processing at pretty high network rates.
So actually, one of the issues about keeping the Linux compatibility or the Linux kernel and the noise that you guys mentioned is between the user and the kernel space switches. So in the single address space world of unikernels, you at least in terms of I/O, you get a lot of benefits by removing these mode switches. So the OS noise is actually referring to this part too, and you have all the security stuff from the hypervisor itself. So there's no actual reason you need to use, because there's no multi-tenancy in a unikernel. You don't need to use the separation of user and kernel space.
That sounds kind of scaring in the idea. I mean, from the viewpoint of an application, you know, running. I mean, if I think of a web server, you know, serving thousands of users on, I don't know, something like a WordPress system, I don't know, a document management system, where I think, you know, the operating system security features still play a role in guaranteeing that everything is safely isolated, robust, secure. Albeit, you know, of course, if you handle user role and access privileges, etc., at the application level, it doesn't matter. But when you go really, you know, isolating different activities, different processes, daemons, so that, you know, if anyone crashes or whatever it does, you know, it cannot really screw up the whole.
The idea there is actually that you go more the microkernel approach there. It's just that your hypervisor becomes to the main kernel, and processes are spread into decoupled VMs.
Okay, so they will become microservices, so that you will have a different unikernel instance hosting each one of these microservices. Yeah.
Yes,
yeah,
yes.
fine.
So that would be rather the model, right? Yeah.
And that's the reason you need a more lightweight hypervisor. And it seems that the hype is that. I mean, with Firecracker from Amazon or Solo 5 or Rust VMM, I don't know. All these hypervisors are focused on near instant spawn times, on jailing all the execution environment using specific Linux kernel C groups and namespaces and stuff like that. So it's more of creating the sandbox inside which a small microservice will be running.
There's actually a lot of interesting stuff that was happening, especially when you mentioned Solo 5 and Firecracker and so forth. We did some research in the past regarding how fast you can spin up virtual machines and how can that compete against the process spin up and so forth. And there was, but this is just a side comment now. Interesting to see that originally hypervisors weren't built for running as tiny VMs that are more or less just processes. You know, you had limitations like that you had to assign at least 4 megabytes of memory, otherwise it doesn't boot because the tool stack of the hypervisor would decline it. And then the bookkeeping of simple things like the VM ID took ages. When you start running 1,000 or even more virtual machines on the same hypervisor, because the algorithm was never optimized for running that many virtual machines. Most was maybe 12 or 10 virtual machines, and then the algorithm was fine. So there's a lot of potential in the whole stack to optimize. But as also our research showed, this is definitely possible. It's just a matter of writing the proper tools, shrinking them a bit down, use more optimized algorithms for the VM creation process. And this is also what you probably see with the work of Solo 5 and also Firecracker as well.
Yeah, so the Rust approach with Firecracker seems really interesting. I was curious. I would like to ask Stefan to comment on this. We were doing some work on a backend for the Firecracker team. So we saw that there's no way to safely link C++ libraries, which I'm no Rust expert, I'm no language expert, but it was really strange. I mean, is it a language limitation, or it's a project limitation? These guys don't want to link to C++ libraries. If Stefan is online.
He's not there.
Oh, Stefan, you're muted. I clicked ask to unmute, but I cannot unmute him remotely. I guess this would be not as a feature they desire.
You never know what's going on the other side.
quite a good feature, the one that you can unmute.
I guess he's not there.
Okay, given the time, you gotta move it into off the research sphere at one point because you're clearly onto something, but it's gotta find its applications. Yep. Going on with the last discussion point, and this probably very much less long than the first one. We had, that is David touched on the EBI perspective that doing a, and I'm not paraphrasing, doing a completely clean Kubernetes setup for pipelines is maybe not practical at times. So the question to pose would be where, David, would you see the how do you say, denomination line between where or the line where you say it's economical still to do Kubernetes, where does it stop for a typical pipeline in your domain?
Yeah, you're absolutely right. Yeah, it's starting from scratch doing so-called cloud native implementation is not always desirable. First of all, I see that HPC and the cloud compensate with each other, so that if I had a crystal ball, I would say that in the far future, we will see both HPC and the cloud technologies working together. Like in today's conference, we already see that people are using Kubernetes to invoke the jobs from the HPC backend. And there are also a lot of technologies to try to burst from the HPC side into the cloud as well. So time moves on that we will see both of the sides will interact with each other and closely integrate with each other.
Would you see that picking up on bursting? Would you see, given that we had a talk on this before, and they took the very approach that the Kubernetes holds state, that bursting towards HPC would take the form of the pod being scheduled on an HPC worker, and that's it. It goes back to the Kubernetes local one, and HPC's role is basically that of a high performance backend.
Well, that's current, if I could use the word maybe offensive, like primitive implementation is. I'm sure time goes on that people will figure out ways to intelligently explore the capabilities in HPC and make sure that they make good use of all the features that Kubernetes will probably never try to implement. This is really just a time statement. It's really just what currently we have, what currently we thought we could do. Combining with EBI's, our own experiences, we do both kind of projects, migrating from the HPC to cloud we call it a lift and shift. We essentially are taking the pipelines as close to the original form as possible into the cloud. In the beginning of a couple of charts that I showed was that we use the Slurm on GCP and we use CycleCloud on Azure, etc. That's the so-called lift and shift project we've been doing. And we also do this so-called cloud native implementation as well. The decision point is less, at least based on our experiences, is less of a technology, more of a project driven. It's more by the what kind of project schedule and budget and also the willingness for the particular project team wants to pick in favor of one solution over the other. A lot of time it's like that. If I had to say that whether there are factors that on the technical perspective to affect the decision was more of if it's more of a transactional workloads such as web services, we tend to suggest that project teams to do the cloud native implementation, because that's what the strong suit where the Kubernetes is. That's basically what Kubernetes was originally designed for and also extensively developed for. For the batch processing, we still think that the Kubernetes has way to go, has room to grow. That's one of the reasons that we looked at it. We looked at the job framework. We looked at, yes, it has all the basic things there. However, just like nobody does the programming in machine language, or almost nobody these days. We need something at the higher level to give people more convenient ways to implement the batch jobs. And that's why we to pay a lot of attention to try to find out the new projects going on and try to enhance that kind of aspect. So we find and decided to do prototype and investigation with Kubeflow. And it turned out that Kubeflow does fulfill its promise pretty well. And especially that with the new requirements of the machine learning pipelines, because and these researchers, they're new kids on the blocks. They're pretty much being trained by object storage is the norm, and pretty much being trained by the container. That's their starting point. So that's the perfect fit. And while doing that, we noticed that the Kubeflow's job framework is really good. And that gives us an inspiration that, okay, let's try to see that how really well let's implement a pipeline for the classic genomic pipeline, see really how well it's doing. And it turned out that it's quite promising.
Okay, we have got somebody. I'm sorry to pick on you without having been asked, but you just, David, you just mentioned a key word, and I believe we have somebody from Riken here. Could this be? I was wondering time zone wise, but Mr. Konishi? No, because there's some context to BLAST, so the sequencing BLAST, and I guess would have been nice. Now, anyways, any other notions? Please go ahead.
No, actually, that was pretty much what I was going to say. So there were questions from the other attendees, or there were comments. Yeah, as Michael said in the chat, it's open mic. Yeah, please voice your opinions, agree, disagree, and your comments, etc.
So maybe I have just probably I'm not getting too much the context of this. So I didn't understand whether this let's say tipping point where you say it's worthwhile to try out the Kubernetes way, or maybe you want to try something else, or I mean, does it depend on I mean, is there advantages you get in terms of ease of orchestration, maintenance of the cluster, or is there advantages in terms of performance you get in the end, or what else, or advantages compared to alternatives? Because yeah, maybe I didn't get well what is the comparison point here.
Yeah, I think you're right. It's not you didn't get it. It's that I didn't talk about it. It's more of my fault. One thing that I can think of is that because Kubernetes is dealing with the containers instead of the VMs. For example, that in a batch processing job, if we're using something like Slurm in the cloud, when the job is done and the VM will be idling for a few minutes and then it gets shut down. And if we want to start a job, we have to create a VM to get started with. But in the case of Kubernetes, what it needs to do is to start a container or shut down a container, which the overhead is much lower. And also that with Kubeflow, I noticed that they even reuse the existing containers. When a job is done, they just stop the container. And if there's a new job coming in that requiring the same container, it's going to start it up. So when the container is shut down, the cost is really the storage of the container, which is quite small. That's the efficiency that I can think of. So if the kind of efficiency that is what you want, and perhaps going to the Kubernetes and Docker is probably the right approach compared with.
We have got Podman also. Please, that's something to very much consider. Yes.
So that's compared to a classical virtualized infrastructure, so with virtual machines.
Yeah.
So in this regard, also, if you think about an OpenStack with going with a container plugin or module, whatever it's called, it's pretty much similar, right?
Yes, I agree with you. Yes.
Albeit for my personal experience, at least setting up a small OpenStack cluster looks like a real burden with tons of different services to get configured right.
Yes. Talking about it, I had whenever it gets from play to serious with Docker, it gets serious. How would you? I'm not sure what your experiences are, but do you think you're flexible to switch to another container runtime in terms of your users or so, or is this image immutable, so to speak? Yes.
Let me try to understand the question.
You mentioned that you have got users which grew up, quote unquote, in the container world, which is a good thing to hear. Now, obviously, they know Docker. They know the Docker commands, but if there were to be other container runtimes which have like the Podman a very much compatible syntax, do you think that's conceivable to at least pluralize?
Oh yes, absolutely. Docker is the dominant one at this point, but I can see that it's not going to last forever. And let's say that a lot of other technologies like Singularity, and we've been talking about a lot, and also the Podman, and I think they're going to take a significant share from Docker. Kubernetes has a quite flexible architecture. It does support the additional container runtime. It requires those runtime specific particular libraries to be available on the hosting VMs. In the case of Singularity, that they require you to do a manual installation first, and then to place and then Kubernetes to Kubernetes, it just knows that to pick up the Singularity container on that particular VM. And I think that I don't know, I never tried it, but I think that for Podman, it's probably the same story.
Good, okay.
Yeah, that was a point I wanted to mention as well. If you have something like Kubernetes in place, you don't really care about what runtime you have at the lowest level. And there's a really nice talk where I think it was one of the maintainers of Containerd or something like that. I can look it up, but what he did, he compared like all of the possible runtimes you could put below Kubernetes, and he was trying to give a demo for this and showing all the different runtime and just starting up a container with this. So in the end, with some abstraction as Kubernetes in place, the runtime basically just goes away and becomes unimportant.
That's a good point. Yep. Yep.
Yeah. Yeah.
Okay. It's 1:33. Yes, please go ahead.
About the runtimes. So one extra point could be that on the low level part of the runtimes, we could have something that could run a container, a VM, or a lightweight VM, a unikernel process. So there are a lot of places where the container runtimes can be optimized, depending on the kind of application and use case that you are deploying.
I'm not sure. Can you specify in Kubernetes right now which runtime to where on the?
And that's the really interesting part. You can have a hybrid setup with each pod spawning a lightweight VM with Kemu Lite or with Firecracker. You could have another pod spawning Nabla containers, which is kind of a process, not really a VM. And you could have your own runtime on another pod that could spawn a Kemu VM, a fat VM. So it's really interesting what use cases could be bound at this setup.
Yeah, I just noticed that somebody posted a message on the chat. Whoever you are, can you please speak up? Oh, it looks
that was
pretty
me.
interesting.
I was just looking up the reference I was pointing out.
Okay.
Phil Astos from IBM was trying all the available runtimes in Kubernetes one could possibly ever want to use.
Okay, that's very interesting. Yeah. Yeah, I'm gonna take a look at this video afterwards.
It's really entertaining. He
Yeah.
was trying like a dozen of them.
Oh, wow, that itself is a lot of effort, I would imagine. Oh, okay, it's a CNCF presentation. Yeah, it's probably a big size of a pretty big size of work by itself.
If you open the video and go to 2 minutes 47 seconds, he uses Docker shim with Docker D. He uses Containerd with the cryo with the cry Containerd, and he uses runc with cryo, and he uses Kata with in combination of Containerd and Firecracker in combination with Containerd and then Singularity. So in the end, he has like 6 different runtimes.
Oh yeah, that's right. Yeah. Interesting. I was wondering whether he compared the performance and security aspects of these container runtimes as well.
Probably not. I think this talk was basically just about showing off and what is possible. But what I can imagine in the future, that you have like one queue or something, or one cluster with each runtime, and you pick the runtime that basically just fits your job the best. For example, if you need additional isolation, you use something like, what is it, Firecracker or Kata or something like that. And if you use something more that's related to HPC, you probably use Singularity or something.
Yeah.
But the interesting point here is that we have this sort of flexibility, and we're not forever stuck with Docker or whatever's the new kid in town in a couple of years.
Yeah, that's right. The Kubernetes architecture is completely pluggable. A lot of things can be replaced, but of course, got to with extra effort.
Yeah, and that's one of the main points I see a bit problematic about Kubernetes. Everybody wants to use it, but you can spend quite some time there setting it up and getting everything figured out until you're up and running. A bit like when you deploy your OpenStack installation for the first time.
Oh yes, yes, yes. We spent so much effort to get things working.
Yeah. But well, for the cloud providers, it's a possibility to sell like their hosted Kubernetes installations. So I guess they're lucky as well. It's too complicated for everyday users and just deploy their own cluster in the afternoon or something like that.
Yeah, that's right. Yeah, yeah. Both like Google, Amazon, they all, I don't know about Microsoft. Microsoft, yeah, they both have the container service. Kubernetes service. All you need to do is to throw the container at it, and it's going to run. You don't have to set up the Kubernetes itself yourself.
Yeah, you basically just use it. It's there, sitting there, waiting for you, and you pay for using it. And you don't have to care about how to set up it, how you going to update it, and so on.
Yeah, yeah, that's right. KubeVirt. Oh, nice. Alexander, can you please speak up? I saw you posted a message saying that it's worth taking a look at KubeVirt. Can you elaborate on that?
I think he has got some Zoom issues, so we won't get the message here. Anyways, any other last notions? Because keep looking at the time, and we're breaking records. Well, then Anastasia and me would like to thank all the participants, all the panelists, all the speakers, Red Hat for all the participations today. It's been quite an extraordinary day. I think we in terms of format, this was quite a success actually. I don't want to give all the numbers, but they're extraordinary, I can tell you. And the number of flight hours we saved, this really makes you think. Very good. Again, thank you for your all of your participation. It was a great workshop, and hope to see you again next year in whichever format it may be. Thank you again.
All right, thank you.
Thank you, Michael.
Yeah, thank you for hosting and organizing and everything. See you next time around.
Okay, bye.
Bye-bye.
Thanks a lot also from my side. It was really nice.
Thank you very much. Bye.
Thank you, everybody. Bye-bye. And good night.
Thank you very much. It was a wonderful workshop. Bye.
We're working on a graceful shutdown of the recording here, so in case anybody's wondering.